Welcome to Java for Beginners. My name is Zachary Kingston, and I'm excited to be your instructor. In this course, we'll be learning the programming language Java, which was developed by Sun Microsystems in 1995, but has stood the test of time and remains highly relevant and widely used to this day. Whether this is your first foray into high-level object-oriented programming languages like Java, or if you've been programming for some time and you're just looking to add Java to your repertoire, or even if you've never touched a line of code in your life, this course is designed to accommodate you. We're going to move quick, and we're not going to shy away from heavy subjects, but we're going to begin this course from the very ground up and learn about the concepts behind object-oriented programming as we go. So what exactly is Java? Java is a high-level, general-purpose programming language. What this means is that rather than being created to accomplish one very specific task, Java allows us to write computer-readable instructions in an open-ended environment. Because it's not really feasible or even desirable for every computer system to have its own specialized programming language, the vast majority of code is written in high-level general-purpose languages like Java. Java is also what we call an object-oriented language. While we won't get into the specifics of objects and classes until a bit later in this course, know for now that objects allow us to define modular entities within our program that make it much more human-readable and much more manageable to create large-scale software projects. A firm grasp of object-oriented concepts is absolutely essential for any modern software developer. Lastly, Java was designed with the intention that it be a write-once, run-anywhere language. That means if you and I both have systems with Java installed, even if our systems are not normally identical, for example, if I'm on a Windows machine and you're on a Mac, a Java program on my machine that I give to you will still run essentially the same on your machine without having to be recompiled. Compiling a programming language like Java is the act of taking the human-readable code that we've written and converting it to an interpreted machine-friendly code that unfortunately is usually not very friendly for humans to read or write. To do this, we use a program called the compiler, which takes in our code as text and converts it to the machine code. Traditionally, we would have to recompile a program for every system that it was going to run on, because all systems have a different idea of what their machine code should look like. Java circumvents this issue by compiling all Java programs to the same type of interpreted code, called bytecode. A compiled Java program in bytecode can be run by any system in which Java is installed, because when you install Java on your system, you install with it a Java virtual machine that's specific to that system. It is this machine's responsibility to convert that bytecode into the final instructions that head to the processor in that system. By making it the system's responsibility to do this final conversion, Java has created a write-once, run-anywhere language, where I can hand you a Java program and you can run it on your machine, being fairly certain that it's going to run in the same manner that it did on mine. This impressive level of cross-platform support on a language as powerful as Java is has made it one of the software developing world's go-to tools for quite some time. In the modern day, Java is used to develop desktop applications, web servers, client-side web applications. It's the native language of the Android operating system, which operates on Android phones and tablets. Java has been used to write video games and is sometimes even ported to smaller devices without a traditional operating system. Java remains a huge player in today's technical world, and I'm looking forward to learning it with you. Welcome back. In this video, we're going to write our first Java program. But before we can start coding away, we need to set up an environment that is Java development friendly. To start off this process, let's download a Java development kit, or a Java SDK. This kit contains libraries and executables that allow us to do lots of different things with Java code. Most importantly, with our SDK installed, we'll be able to compile Java code and then run completed Java programs. You may already have Java installed on your machine. However, unless you've explicitly done it, you probably haven't installed a Java SDK. The version of Java your average user has installed on their machine is called the Java Runtime Environment, or JRE. This allows the execution of Java programs, and Java programs won't run on environments without the JRE installed. But the JRE doesn't contain any real development tools, which we're going to need. The good news is, a Java JRE and a Java SDK can exist harmoniously. The Java JRE is really just a subset of the SDK, and so if we only have the Java development kit installed, which we're about to download, we're also going to be fine. If you have downloaded the Java development kit in the past, when we actually go to install this kit, Java will let you know that it's already installed, and you can skip this portion of the video. For everyone else, let's download ourselves a development kit. To begin with, pause the video and navigate to this URL at the top of my web browser. Okay, we're going to be using the Java SE, or Standard Edition Development Kit, maintained by Oracle. To acquire this kit, we simply go to the Downloads tab, express that we would like the JDK, scroll down, check out the license agreement, might be another good time to pause this video, eventually accept the license agreement, and then we're going to download the version of the SDK that's appropriate for our operating system. For me, that's this guy. Once your download has completed, install it as you would any other program. Choose the default options when appropriate, and make sure to take note of the directory to which you install your development kit. Okay, with our Java development kit installed, we technically have all the tools we need to start writing Java programs. However, we'd have to compile them through a command line, which can look a little different on different operating systems. So to keep everything simple, let's start learning Java by writing our Java code in an integrated development environment, or IDE. This is a software program of its own that helps us write, compile, and run Java programs. We're going to use the NetBeans IDE, which is awesome because it is free, open source, and is going to operate just about the same on Windows, Mac, and Linux environments. To acquire this IDE, head to the URL once again at the top of my web browser, and then you'll see this page. Because we've downloaded the Java Standard Edition Development Kit, that's the version of NetBeans that we're going to download here. NetBeans should start our download automatically, but if it doesn't, we can click here. Once again, we're going to install NetBeans as we would any other program, choosing default options when appropriate. Most likely, NetBeans will locate the Java development kit on our machine. If it doesn't, it will prompt you for the directory in which you installed the Java development kit. Hopefully you got NetBeans installed and booted up without any hassle. And now you're ready to write some Java code. So let's do that. We're going to go File, New Project in NetBeans and choose Java Application as our project. Make sure this Create Main Class option is unchecked, as this will create for us a essentially blank project. And give your project the name Hello World. Here, you can declare what location you'd like the project's folders to live in. Once you've done that, click Finish, and NetBeans will set up a file system for us. We can navigate this file system just like we were in a standard file system explorer. The source packages file is where we'll be writing our code today. And you'll notice under this libraries file, the JDK is linked, allowing us to access all of its many library resources. All right, hopefully you got NetBeans installed and booted up without any issue, and now you're ready to write your first Java program. So let's do that. NetBeans will manage the file structure of our programs for us. But first, we need to tell NetBeans that we're ready to begin a new project. To do this, we click File, New Project, and choose a Java application. We're going to need to give our project a distinctive name. Let's call this one Hello World. And then we can choose a location to put the file. Because this is our very first Java program, we should probably start from as close to scratch as possible. So let's uncheck this Create Main Class option so that NetBeans gives us pretty much a blank project. And then we'll click Finish. You should see this Projects, Files, and Services tab like I have here. Let's look in the Files tab. Whereas the Projects tab is a bit of an abstraction, the Files tab shows us what's actually contained within the file system where our Hello World project lives. Most importantly, this source file here has no files in it. That's because there's no source code associated with our project, and so right now it won't do anything. To remedy that, let's right-click on this file, choose New, and Java class. We're going to name our Java class Hello World, just like the name of the project, because it is our main class where the program should be entered and start from. Everything else is going to work just fine here for now, so let's click Finish. And NetBeans will create hello world.java for us. A .java file is essentially a text file, but it should only contain Java code and comments. When we told NetBeans to make this file, it took some liberties and added some code for us already. You'll notice that some of the contents of this document are completely human readable. These are what we call comments. Any text that appears in a Java file between this \* opening bracket and * closing bracket will be completely ignored by the compiler. We can write whatever we would like in here, and it will not affect how our program operates. For now, let's just delete these comments so that we can deal purely with our Java code. Java code, like the English language, is read top down and left to right. Even if our project contains many files and many classes, we still need to start reading and executing our code at a specific point. We named this file and class Hello World the same name as our project because we would like it to be special and contain the public static void main method. That's quite the mouthful of jargon. for now, just type it out and know that this is the area of our code from which our Java program will begin reading and executing. In fact, we have to add a little more jargon here. String bracket bracket args. Once again, this will become much clearer as we begin to learn Java. Just know this is the starting point for our Java program. Are followed by opening and closing brackets. One of the great things about working in an IDE is that it will highlight which brackets correspond to each other. The brackets allow us to place code within other areas of code. For example, our main method is contained within the Hello World class, and the Java code, which we're about to write and execute, is going to be contained in our main method. This line 4 right here, which currently contains nothing, will be where our program looks to start reading and executing Java code. Our goal with this Hello World program is pretty modest. When it runs, we'd like it to print some text to this output box at the bottom of our screen. When we downloaded the Java SDK, we acquired a library of useful functions, one of which will do just this. This is the println, or print line, function. When our Java code executes over this function, which it will do right away because it's the first function in our main entry point, the Java code will print some words to our output box. Functions are followed by an open and close parenthesis. Inside these parentheses, we put information that the functions need to complete their task. Println, of course, needs to know what we would like it to print. In Java, a line of text is contained by 2 double quotation marks, and we call it a string. Let's have our program print Hello World. You might have noticed that NetBeans has been yelling at us for a little bit. There's a light bulb and red dot here, and some red jittering under our text, a lot like we had made a spelling error in some text editors. And that's really what we've done. We've made a syntax mistake. There's something clearly wrong with our Java code, and NetBeans knows it. There's actually 2 things wrong. The first is that our code doesn't end with a semicolon. Java doesn't do a good job of reading spaces and carriage returns. So we need to put semicolons at the end of every functional line of code, for the same reason that a Morse code operator would send the message stop at the end of every line. Now, NetBeans has become a little more satisfied. The jittering has decreased, but there's still something wrong. The issue is that functions in a programming language, just like files on a computer, have a location where they exist. NetBeans isn't sure where to find the function println that we've attempted to use. So we simply need to tell NetBeans where this function exists. The full path to the println function is system.out.println. Let's get rid of these extra spaces I created there, not because they would affect the way our program runs, just because it doesn't make it look quite as nice. And now we've written our Hello World program. So what do we do with this? Well, as we know, our computer can't read this Java code directly. It must convert it into a computer-readable language. So executing this code becomes a 2-step process. First, we're going to ask NetBeans to build our project. This means that all of the code within our project will be compiled and converted to computer-readable code in a essentially computer-readable project. When we press the build button, we'll see a bunch of text in our output box down here, and hopefully this nice build successful, and then the time it took to build the project. Once we've built our project, we can press this run button right here to execute our code and our print line statement. NetBeans will then give us this pop-up box here. When you execute a program outside of an IDE, you execute it by launching one of its executable files. Because we're in an integrated development environment right now, NetBeans wants to be sure which of our files we would like to be the entry point of our program. We only have one option here because we've only written one Java class. So let's confirm for NetBeans that Hello World is our main class, and the main function in Hello World will therefore be where we start executing our Java program. Then when we hit OK, our output box will tell us the program has begun to run, and our program then prints Hello World to the output box as we intended. And there you have it. Now we're Java programmers. Of course, there's more than a little bit left to learn. In fact, Hello World in Java is probably the scariest program you'll ever write. Java is extremely powerful, and the reality is we simply can't hope to appreciate all of its intricacies while writing our first program. The really good news is that from this point on, we need to take far fewer leaps of faith, and we can begin to build a very solid understanding of Java by taking a step-by-step approach. I'll see you next time. Welcome back. As we write more and more complicated Java programs, we're inevitably going to make some mistakes. Some of these mistakes will be significant logic errors or misunderstandings on our part that we might have to further educate ourselves before we can solve. But especially while we're starting out programming, we're going to make a lot of small, silly errors that are really easy to fix as long as we know where to look. Fortunately, Java compilers are designed to point errors out to us when they come across them. To see this in action, let's simply make our Hello World program incorrect by removing the semicolon from the end of this line. Now NetBeans red jitters the line to let us know that it's pretty sure something's wrong, but we can ask our compiler to take a shot at it anyway. If we attempt to build this project, we don't get the compilation successful message we otherwise would. Instead, we get an error message. This error is semicolon expected, which is a pretty handy and self-explanatory error message. Of equal importance is the number after the colon in this message. This lets us know on what line the compiler came across this error. In NetBeans, if we click on an error message, the IDE will highlight that line of code. If we add in our semicolon, then our program builds successfully. That's all there is to it. Of course, not all error messages are quite that self-explanatory. For the sake of argument, let's create a slightly more complicated error. What would have happened if we forgot to insert one of our parentheses in this program? When we press build, we get not one, but two errors, even though we really only made one mistake. Our first error is not a statement, and then it lets us know the line that it doesn't understand. If we look at this line for a little bit, we're probably going to notice that we're missing a parenthesis and be able to fix this error. But what about the second error? We got semicolon not expected again, even though in this case, we really do have a semicolon there. Well, once one error has occurred in the program, the compiler's ability to understand the lines of code gets shattered very quickly. when we're debugging our code, the general rule of thumb is to address only the top error on our list. That's the first error that the compiler came across in our code. We might be able to glean some helpful information from errors further down, but more often than not, there's simply going to be errors generated by the first syntax mistake we made. Nothing too mind-blowing here, but I wanted to point this out to you because being able to track compiler errors can save us a lot of headaches while we're learning to program. While we're talking about NetBeans, let's quickly go over one other IDE feature. Let's say I wanted to write a new line of code, and I'm going to use something from the system library. Once I've gone system dot, NetBeans can suggest valid responses for me. Only one of these, of course, is going to be what I'm looking for. The NetBeans compiler has a lot of helpful features like this. If you're the kind of person who thinks code completion is awesome, go ahead and turn or leave these tools on. You can do that by going to Tools, Options, Code Completion, and checking the features that you'd like. If you'd rather NetBeans behave a little more like a text editor, go ahead and uncheck the features. And there we go. Lots of house cleaning in this video, but hopefully quick and not too painful. Thanks for watching. To create even modest Java programs, we're going to need a way to store and manipulate information. Our chief resource when doing this is the variable, and that's what we're going to be taking a look at today. To begin, let's create a new project in NetBeans. I'm going to call mine variables. And this time, we'll allow NetBeans to create the main class for us, so that we can get coding as quickly as possible. I'm going to delete these comments here just to keep everything as readable as possible. And now we're good to go. The first computers were little more than calculators, and Java, of course, retains this functionality. For example, Java can evaluate this statement 1 plus 1, which of course will evaluate to 2. However, Java is pretty complicated and designed to do a lot of different things. So we need to provide context to our commands. Here, if we tell Java that we'd like it to print the result of this statement, our program will run as expected. In addition to some others, Java can perform all of the basic arithmetic operations. It can do addition, subtraction, multiplication, for which we use the star, not the X on our keyboard, and of course, division. If we run this program, we'll see 4 print line commands, all of which give the proper evaluations of these statements. We can, of course, change these numbers to be any combination of numbers we see fit. We could, for example, run our program with the input of 2 and 3. Changing these lines manually, of course, is kind of a pain and quickly becomes infeasible if we're writing very complicated programs or dynamic programs that take user input. Fortunately, programming gives us a way of storing and retrieving data. This is called the variable. To declare a variable in Java, we first have to specify what kind of variable we're going to be using. Variables come in a number of different types. In this instance, we're going to be content using simply whole numbers. That is, numbers that do not have a specified decimal place and aren't fractions. And in this case, it's appropriate to use one of Java's primitive types. These are essentially as base level as you can get with information in the Java programming language. Just about everything else we work with in Java is built out of the primitive types. To declare a variable of the integer primitive type, that is whole numbers, we use the keyword int, all lowercase. Once we've done that, we then need to give our variable a name. This is a unique identifier that we'll use to access this piece of information in the future. Each variable in our local program should have its own name. Let's call our first variable x and our second variable y. We've just written two perfectly legitimate lines of Java code. If we run our program, we're going to see the same output we did before, but behind the scenes, Java will also be setting aside memory space for our variables x and y. This allocation doesn't affect our print line commands because the variables are not referenced in them yet. So let's store some information in our variables. To reference a variable once we've created it, we simply reference it by the variable's name. It's important that we not try and reference our variable by typing int x again, because rather than accessing the existing variable x, this is the command for Java to create a brand new variable x all over again. Once we've referenced our variable, we can change its value by using the equal sign. So let's set x to 4 and y to the number 3. Our print line commands currently operate with two explicitly declared integers, the numbers 2 and 3. Since x and y are also integers, it stands to reason that we can simply replace the existing numbers with the variables x and y. When our Java code comes to the variables x and y, it will look to see what integer value they have currently been given. It will find the numbers 4 and 3. So, if we run our program, we should expect this first print line statement, x plus y, to evaluate to 4 plus 3, which then of course evaluates to 7. And that's exactly what occurs. So here's something interesting. The last line of our program, in which we divide x by y, isn't quite evaluating as we might mathematically expect it to. In this line of code, x has the value 4, declared in line 9, and y has the value 3, declared in line 10. 4 divided by 3 is 1 and 1/3, but our program is simply outputting 1. That's of course because 1 and 1/3 is not a valid integer value. Integers are only whole numbers and never fractions or decimal place numbers. So, to keep us working with integers, Java simply rounds down any calculations that have fractional portions to their nearest whole number. If we wanted to be working in an environment where we could have fractional results, we would need to use a primitive type other than integer. Anyway, now that we've set up our print line commands to take integer input instead of explicit numbers, we can modify the behavior of all 4 lines of calculation simply by changing the value of these integer variables. For example, if we wanted our program to run on the inputs -10 and 5, integers can be negative, they just can't have fractional components, all we need to do is change the values we give to our variables on lines 9 and 10. If we run that quickly, we see the expected results. Okay, awesome. We've just learned the very basics of working with both integers and variables in Java. In the last couple of minutes here, let's go over an edge case and learn a little bit more about how Java thinks. You might remember from earlier, I was talking about how Java sets aside memory when we declare new variables. This is one of the huge advantages of working in a high-level programming language like Java. Java abstracts away, or does automatically, most memory management for us. Oftentimes, this lets writing programs be simpler, and we can write shorter, cleaner, more easily readable code. Of course, it is important that we appreciate what's happening behind the scenes, lest we run into issues. For example, whenever Java sets aside memory for an integer variable, it's going to set aside the same amount of memory for all integer variables. That means there's a maximum and a minimum value that Java could ever conceivably store in an integer variable. That's these two numbers right here. Maximum integer value, minimum integer value. So let's do an experiment. What happens if we attempt to store and print out an integer variable that is one larger than this maximum value here? To start with, let's simplify our program. We're simply going to assign a value to the variable x and then print it out. If we attempt to assign a value one larger than possible to the variable x, NetBeans is going to yell at us. It's got some logic built in that attempts to stop us from making this very basic and common mistake. If we were to attempt to compile this program, we would also get an error. However, we want to make this mistake in the name of science, so we're going to trick NetBeans. We're going to set the value of our variable x to the largest possible integer value. And then in the next line of our code, we're going to set the value of x to be one larger than x is currently. Actually, there's a nifty little shorthand we can use for this. X equals x plus 1 is equivalent to x plus plus. Okay, so when we run this program, which will sneak by the compiler and the NetBeans, and do our addition at runtime, we should attempt to print out an integer value one past the largest integer value Java can store in a memory location. When we run this program, we get this very, very, very negative number. This number happens to be the smallest number that we could ever store in an integer. This makes a kind of visual sense. We've gone so far positive or to the right on our integer number line that we've arrived at the leftmost or most negative point. Of course, in a mathematical sense, this could get pretty confusing pretty quickly. It's unlikely that we're ever going to write programs that will need integer numbers larger than this value. However, if we do, we certainly need to be aware of this issue and circumvent it by, for example, using a variable type that can handle larger values. The long variable type is pretty much just like an integer, but more memory is allocated for it. So when we run this program, we will get the mathematically accurate result. When we're simply counting and manipulating whole objects, integers are fantastic. But sometimes we need to deal with numbers in their more mathematical sense, and we need a data type that will allow us to express ideas that are not entirely whole numbers. Floating point numbers, or floats, are a Java primitive type that allow us to express numbers that have decimal points and fractions. In this video, we'll be modifying some float and integer variables side by side to see how they are similar and different. So let's start by declaring two variables, one an integer and one a float. As we know, once we've declared these variables, we're free to modify and assign to them in future lines of our Java program. Let me quickly show you that we can also modify and assign to these variables in the same line that they're declared. So on line 7, where I have declared my iNumber integer variable, I'm free to immediately give it the value of 5. You'll notice that if I try and do something very similar with our float variable, NetBeans is going to yell at us. And in fact, if we attempt to compile our program, we're going to get a legitimate compiler error message. When we use an explicit number in Java, that is, typing out the digits rather than working with a variable, that value still has to be given a type in Java. When we type out a number without any decimal places, the type that it's assumed to be is integer. So our assignment on line 7 works just great. However, a number with decimal places is assumed to be this type called double, which we'll talk about a little later. It's a sister type of float, but it's not quite the same. So what we need to do is tell Java to treat this 5.5 here as a float type number. To do that, all we need to do is put an F after the digits. Okay, to make sure we've gotten that syntax all right, let's give our program some super basic functionality. Let's use system.out.println to print in sequence our integer number and then our floating point number variable. When we build this program, our compiler error has gone the way, and when we run it, we see the two assigned values as expected. Nothing too exciting there. Now, rather than assigning explicit values to our variables, let's do some basic arithmetic so we can see how integer and floats, when modified in Java, behave differently. In Java, both floats and ints are primitive types, the logical building blocks of the programming language. That means that we can compare and modify them using mathematical operators like division. We know that if we attempt to divide one integer by another, we'll always get a whole number as a result, even if the rules of standard mathematics don't make that the expected result. If we divide a floating point number by another floating point number, however, we'll get a more mathematically accurate result. Sometimes, Java will let us do things that might not be such a good idea. For example, instead of attempting to set the value of our floating point variable to one floating point number divided by another, we can instruct Java to set its value to one integer divided by another. Because the computation on the right side of our equal sign occurs before we change the value of our floating point variable, we're going to see the same phenomenon in this 5 divided by 4 as we see when we divide 5 by 4 above, because both of these 5s and both of these 4s are integer variables. So when we run our program here, even though f number remains a floating point number, as we can tell because it prints out with the decimal place, its value is still set to the rounded down whole number of 5 divided by 4. Solving this problem is pretty straightforward. We simply need to change one of our integer values to be a floating point number. And now the computation will know to proceed with decimal place division. This becomes a little trickier and more important to navigate properly when we stop working with explicitly declared numbers and begin working with variables. Let's declare two integer variables now. I'll just call them iNumber1 and iNumber2. And rather than attempting to set the value of f number to one explicitly declared number divided by another, we'll set its value to integer variable 1 divided by integer variable 2. And we'll just print out the result stored in f number. When we run this program, because once again we're dividing one integer by another, we're going to see the rounding down phenomenon. The value being stored in our floating point variable is 0.0, the rounded down result of 5 divided by 6. If we were working with explicitly declared numbers, we would solve this problem by changing one of these two numbers to be treated as a floating point number, simply by putting a decimal place and an F after it. In this context, that's not an option, because rather than thinking that we're asking it to treat I number 2 as a floating point number, Java now believes it's looking for a variable called I number 2f, which certainly doesn't exist within this context. We can achieve a similar result, though, by using what's called a cast. This is a command in which we ask Java to treat a variable of one type like it is another one. Here we're circumventing Java's natural inclination to treat I number 1 and I number 2 as integers. We're stepping in and saying, you know what, Java, treat this number here as a float. And we're assuming some responsibility when we do that. Java is going to attempt to do what we ask. But if we've chosen poorly and attempted to cast one object to an object that it cannot be, our program will crash. Fortunately, we're working with primitives here, and the primitive types know how to act like another type. So, we can cast the variable I number 1 to temporarily operate like a floating point number by prefacing it with parentheses float. Now if we run our program, we'll see the expected result of 5 divided by 6. And that's a pretty solid introduction to working with floating point numbers, which we're going to use just about any time that we want to be working with numbers in their mathematical sense, rather than as integers for counting whole objects. In the last couple of minutes of this video, if you're feeling up to it, let's quickly talk about the double. The double is a sister type to the float. It provides a greater resolution. Double numbers can have even more decimal places, basically, but they take up a little more memory. At this point in time, using doubles or floats is almost always a style or personal preference decision, as unless you're working with complicated software that must run at peak memory efficiency, the extra memory space taken up by a double is not very significant. Let's see. To illustrate how doubles work, let's change our two integer numbers to be doubles. Right there, I've just changed the names of the variables, so the logic of our program hasn't changed at all. But here, when we change the declaration of these variables from declaring integers to doubles, now the logic does change. Anyway, when we explicitly declare a number with decimal places, it defaults to being a double. And now we need to fix line number 9. Line number 9 is an issue because dividing by a double is going to return us a double result. We can solve this issue in two ways. First, we could cast d number 1 and d number 2 to floating point numbers and then divide them. However, dividing our two double numbers by each other is a perfectly legitimate operation. So why not allow that to occur as it would naturally, and then cast the resulting double to a floating point number, preserving a greater amount of our resolution. Just like in algebra, we can break up conceptual blocks of our program that we would like to occur before another block using parentheses. Now if we run this program, we get an expected result. Thanks for watching. A good portion of our time on any software development project is going to be spent teaching our program to solve the types of problems it comes across on a regular basis. As programmers, we too will run into certain problems time and time again. Sometimes we're going to have to code our own solutions to these problems and hopefully save them for later use. However, more often than not, someone has run into these problems before, and if they've made their solution publicly available, one of our options is to leverage their solution for our own gain. In this video, we'll be using the math class library, which is bundled with the Java development kit, to solve some math problems for us. To start this video, create a brand new NetBeans project and enter the main function. We're going to write a very simple program. Let's declare a floating point number variable and give it a value. Don't forget the F at the end of our explicit number to let Java know that we've declared a floating point number. And then let's use system.out.println to print this value to the screen. Okay, there we go. Now, with this program, we'd like to make it really easy to raise our floating point number to various powers. So, if we simply wanted to square this number, I guess we could just print out the value of number times number. If we wanted to cube it, we could print out that value. And if we wanted to raise it to the power of 6, we could do something like this. Of course, this gets unwieldy pretty quick, and there's certainly a better way. Let's leverage the Java math class library to help us raise numbers to varying exponential powers. Now, I've just told you that the functionality we're looking for lives in the math class library. This is the kind of push in the right direction you should expect to get from a Google search, or if you're an experienced software developer implementing a specific API. Unfortunately, that's not quite enough information for us to start using the functionality of this class library. We don't know the specifics of how it works, or even exactly what functionality it offers us. To find this out, we're going to have to look at its documentation. Here's the documentation web page managed by Oracle for the libraries found in our Java development kit. Among these libraries is java.lang, which contains the math class that we've been looking for. Once we've navigated to the class library page, we get two things. First, we get some human-friendly text write-up about the library, its history, what its intended uses are, very meta-level stuff. If we scroll down, we then see the functionality and methods implemented by the library. This is the nitty-gritty and where we'd like to be. One of these functions should stick out for us. It's the pow, or power function, and it returns the value of the first argument raised to the power of the second argument. In short, it will allow us to raise numbers to an arbitrary power. Let's split up our screen here a little bit so that we don't have to flip back and forth too much, and get back to coding. Alright, let's employ this power function to modify the value of our variable number on the line after we've declared it. We're going to do something along the lines of number equals pow, but we need to know a little more information. How exactly do we employ this power function? Well, if we click back to our documentation, we'll see that when the power function is declared, in addition to its name, there's also, between these two parentheses, two arguments specified. These arguments, double A and double B,
are the two pieces of information the function is requesting before it can operate as expected. Our job, in order to use this function, is to replace the requests AA and B with actual variables or explicit values so that the power function can do its thing. Our documentation tells us that AA should be replaced with the variable or value that we'd like to raise to the power of a B. So let's replace the first type argument with our variable number, which is what we want to raise to an arbitrary power. You'll notice that I get rid of the double specifier when I do that. This specifier exists to let us know what type Java is expecting. On that note, number is a float, not a double, and that's going to give us some trouble, unless we simply change it. Now, we don't have a pre-created variable to replace B with, so let's just use an explicit value like 4. In theory, the power function now has all the information it needs to go ahead and run and raise the value of our number variable to the power of 4. However, NetBeans is still giving us our red warning sign. Right now, that's because NetBeans, and Java by extension, doesn't know where to find this keyword POW. For the same reasons that we need to specify a full path to system.out.println, we need to specify for Java the full path in which it can find the power function. That's the same path we followed to get to the power function in our documentation. So we're going to specify java.lang.math.pow. Now we're pretty much good to go. We need to erase this madness here and only utilize the number variable once in our println statement, and now we should be able to run our program. You can plug it into your calculator if you want, but I'm pretty confident that our program has just outputted the value of 4.321 raised to the power of 4. So this is great. We've just employed external code to not only make our program easier to write, but also to keep it very human readable. It required much fewer lines of code than it would have otherwise. One thing that's not superhuman readable about our program is these long paths to functions like pow and println. Is there a way we could shorten them? There certainly is. If the makers of Java had wanted to, they could have allowed us to call this function by simply typing math.pow in all instances. This, unfortunately, would have some unintended side effects. For example, if two libraries linked up to Java both declared a math.pow function, Java would not know which one to use. So by default, we're expected to link to libraries directly and explicitly. However, if we'd like to just be able to type out something like math.pow, we can import a library into the local space that we're working. We do an import command above our class and main function declaration, and all the import command takes as input is the path that we'd like Java to look for when it comes across a keyword like pow that it doesn't immediately recognize. In order to allow us to employ the easier syntax math.pow in our program, we simply need to import java.lang.math. There is some special syntax for imports. Let's say we wanted to import all of the class libraries in java.lang. We could replace .math with .star, which translates to .everything here. I should probably note that for those of us working in NetBeans, this import is done by default. But we're going to do it explicitly here because you may have to do it working in other Java environments. Thanks for watching. Programs that manipulate numbers are all well and good, but oftentimes we're going to want to be able to work with text and words as well. To help us do this, Java defines the character, or char, primitive type. Characters are the smallest entity of text that you can work with on a computer. We can think of them to start off with as single letters. Let's start building our program by simply defining a single character. We'll call it character 1, and we'll assign to it the value of uppercase H. Just as we have to use some extra syntax when defining a floating point number explicitly, we need some extra syntax when defining a character. To tell Java that we're explicitly declaring a character value here, we surround the letter we would like to assign to our variable with two single quotation marks. The single quotation marks, as opposed to double quotation marks, let Java know that we're working with a character, a single letter, as opposed to trying to use an entire string. Characters can only have single entity values. If we attempted to assign the value of high to this character, NetBeans and Java would both let us know that that's not a valid option. Now, let's move on and write a somewhat convoluted program that will nonetheless work pretty well for our example purposes. Let's define 5 characters. We'll call them characters 1 through 5, and we'll give them values that when printed together will show hello. In the second portion of our program, let's use system.out.print to display these values to the screen. System.out.print works just the same as println, except that it doesn't add a carriage return at the end of our line. Actually, let's have the last command be println, so that our output is separated from all the additional text presented in our console. So if we run this program, it greets us. It says hello and then additional text. So that's pretty straightforward. Now let me show you something that will give us a little insight into how our computer thinks about characters. It turns out that we can set the value of character 1 not only by explicitly declaring capital H between two single quotation marks, but also by giving it an integer value. Each possible character value has a corresponding number that we can use in lieu of it. If we replace our single quotation mark capital H end quotation mark with the value of 72, we're still going to print out capital H ELLO. If we were to use the value 73, 1 greater than 72, instead of a capital H, we'll now get a capital I being the letter that follows H in the alphabet. Make sure you don't put the 72 between your single quotation marks. Best case scenario is that Java recognizes that 72 is not a valid character. That looks more like 2 characters. And then our program won't compile. If we were using a single digit number, our program would compile just fine, but we would get the completely unexpected 7 ELLO word. So how do we figure out the numeric value of characters? Well, there's a universal lookup table, the ASCII table, which maps characters to their numeric values. In this video, we've been dealing with columns 1 and columns 5, which have the decimal number and the character that they map to. You'll notice that while many of these characters are letters, others are keyboard symbols, numbers, and other things like tabs. As far as programming languages are concerned, new lines, tabs, and backspaces are all character elements. To see this in action, let's try replacing some of our characters with the decimal value 9, which should correspond to a tab character. If we replace the middle 3 letters of our word with tabs, we should expect as output H, 3 tabs, and then O. Thanks for watching. Let's talk about strings in Java. To begin, create a new NetBeans project and enter the main function. Then let's declare two variables, a character called C and a string called S. Right away, it becomes clear to us that string is something a little different. You'll notice that NetBeans did not choose to color code blue our string keyword, as it would have done if we were declaring a variable of a primitive type. This is, of course, because string, unlike character, is not a primitive type. String is what we call a class. Classes are the backbone of object-oriented programming. Just as we can declare variables of a primitive type, we can declare variables of a class called instances. Right here, our variable S is an instance of the string class. Unlike variables of primitive types, instances of a class can contain their own special methodologies and functions declared by the class of which they are an instance. In this video, we'll be using some of these string-specific methods and functions to manipulate text. But first, let's take a look at what makes strings so special. As we know, we can pretty much use interchangeably our character variables and our character literals. Same with just about any other primitive type. Strings also map interchangeably with the string literal, which is like a character literal but uses double quotation marks and can contain many or no characters at all. Most Java classes do not map to any sort of literal, and the ability for us to manipulate string literals through the string class is what makes it so valuable. Another thing strings can do that most Java classes cannot is make use of the addition sign operator. If we declare three strings, we can set the value of our third string to be one string plus another string. We can even add a string literal into the mix. If we then print string number 3, we'll see these three strings added together in much the manner that we would expect. So I promised you that strings had functionality not seen in a simple primitive type. To employ this, let's navigate to the string class in our Java documentation, which lives in java.lang.string. As with the documentation for all Java classes, the string documentation contains a method summary, which will tell us all of the functions we can call on an existing string object. If we scroll down in the method summary, we'll come to the toUpperCase function, which converts all of the characters in this string to uppercase. Let's employ this function now. Back in NetBeans, we now need to determine where the best place in our program to employ our toUpperCase function is. We know we need to employ the function after line 8, because before line 8, the value of S3 is not yet finalized. We could employ the function on the line immediately following 8, or we could use it as part of the line where we print out the value of S3. Instead of printing out the value of S3, we could, if we wanted, simply print out the value of S3.toUpperCase. If you'll remember from our documentation, the toUpperCase function requires no arguments. It knows that it's being called by S3, and that's all the knowledge it needs. But we still provide the double empty parentheses so that Java knows we are in fact making a function call.
If we run this program now, we'll get the uppercased version of the string as we expected. But it's important we understand what's going on behind the scenes here. Line number 12 is not modifying the value of S3 and then printing out that value. Rather, our print line statement evaluates S3.to uppercase and then prints out the string returned by that function. To see that the actual value of S3 is not modified by this function call, we can print line the value of S3 again and see that it keeps its lowercase components. If we had wanted to permanently modify the value of S3, we would want to do that on a previous line, and we would set the value of S3 to the function's result. To confirm that we're all on the same page, let's employ one more methodology from the string class. If we head back to our documentation and scroll up, we can find the string's replace method. Unlike our toUppercase method, which took no arguments, replace takes 2 characters as arguments. The function will return a new string where all instances of the first character we give as an argument have been replaced with the second character we gave as an argument. Let's utilize this function on our first print line. We'll go s3.replace and give our function 2 characters as arguments. Let's replace the character G with the character O. If we run our program, of course, nothing happens, because by the time we've gotten to line 12, there are no lowercase g's left in string 3. There are only uppercase g's. Now if we run our program, we see the replacement happen on the first instance of print line, but not on the second instance because we haven't actually changed the value of S3. Excellent. You should now be well equipped, as long as you have the Java documentation handy, to call all sorts of string methods. If you spend a lot of time working with strings though, I anticipate that you're going to run into a common problem. Let's take a look at it quickly. I'm just going to comment out all the code we've written so that it doesn't run at all, and essentially write a brand new program here. I'm going to declare a string, and then I'm going to have our program print the string to the screen. But the value I'm going to assign to this string is going to be a little tricky. I'd like our program to print out the text, "The program says hello world." And I'd like hello world to be surrounded by double quotation marks. The problem here is that putting double quotation marks inside a string literal confuses Java. When it reads through our program, the first full string it sees is "the program says:" space. And then this double quotation marks tells Java that we've ended our string. This is, of course, not what we want. Fortunately, there's a system in place for us to tell Java that we'd like a character to be treated as a character literal instead of the special functionality that it might otherwise have. To do this, we put a backslash in front of the character. Now, when Java reads through this string, it will read "the program says:" space, see the backslash, and know to treat our double quotation mark as double quotation mark the character instead of double quotation mark that surrounds a string. When we run our program, we will not see these backslashes. They themselves are special characters. If we do want to see a backslash in our string, we need to preface it by a backslash of its own. And that's Strings 101. Thanks for watching. Programs that perform the same action every time they run are all well and good. But most interesting computer programs do something a little different each time they're run, whether it's because they got differing input or even because a user is actively interacting with them. Today, we're going to explore the very basic conditional if and else statements. To start this off, let's create a new Java project in NetBeans. I'm going to call mine conditional statements. And I will allow NetBeans to create the main class for me. To keep things clean, I'll get rid of all of our comments. And now we're good to go. To allow us to write more interesting programs, we're going to quickly learn how to do some basic user input in Java. At this point in time, we don't have the knowledge base to fully grasp the intricacies of what we're about to do. But we should be able to have a basic understanding of what's going on and certainly repeat the process on our own in the future. While writing to this panel down here is kind of a simple fire and forget process, reading input in Java can be a little more complicated. User input is put into a buffer that our program accesses when it's prompted to. Therefore, we need to declare a variable that will allow us to access this buffer when we need to get some new user input. For this, we're going to use the scanner class. Let's call our new instance reader. NetBeans yells at us here because scanner lives in the package java.util, which we need to access explicitly. We can do that in the line here, or of course, we can always just import the java.util package. Okay, here's the part where we kind of have to take a leap of faith and jump a little bit ahead of what we're really ready to completely and totally understand. We need to assign a value to this reader variable of type scanner so that it links with this window down here where our user will be entering their input. To do this, we're going to set its value to the value of a brand new scanner object. But this scanner object is going to be created with a type argument, that of system.in, which happens to be the link to the input stream our users will be using. Like I said, this is some heavy-hitting stuff, and we certainly shouldn't expect to understand how this works on the low level right now. For now, know that reader is connected with our input stream down here, and our scanner reader has the function next, which allows us to access the input that the user has just entered into the stream. Like most functions, this function simply returns that input, so we're going to have to create a string in which to store that input. Once we've done that, we can use our printline function to print that value back out to the console. Let's see that at work. When we run our program, nothing appears to happen. But in actuality, our console here is waiting for some user input. If we type into this console and hit enter, it will echo right back at us. We can make this a little nicer to use by having our program prompt the user for input rather than simply waiting quietly. Okay, at the beginning of this video, I promised you we'd learn about conditional statements, and we're about to do that. But first, let's make a quick modification to the user input portion of our program. Rather than acquiring a string, it's going to be a lot easier if we learn conditional statements working with a user-provided integer value. So let's change the value or the type of our input variable to an int. Reader.next returns a string, but there's a similar function called nextInt that will return an integer. We're certainly not going to bother putting any error handling in our very simple program, so know that if we accidentally provide this Java program with anything besides an integer, the program will crash. So what exactly are conditional statements? Well, conditional statements allow us to send our program down different paths, executing different lines of code depending on whether or not something is true or not. In today's video, we'll use conditional statements to print different responses to our user, depending on the value of the input they give us. Specifically, we'll let them know if the value they've given us is less than, greater than, or equal to the number 10. To start this process off, let's set up our output cases. If our user provides us input that is greater than 10, let's print out more. And if the user provides us input that happens to be less than 10, let's print out less. Of course, if we run this program right now, it will reach lines 15 and 16 and simply print out more or less, both of the lines. What we need to do is use conditional statements to make sure that only one of these two lines executes in any program run through, and that the proper line executes, of course. You may have noticed that the default project NetBeans created for us divides our code up into segments that have these brackets around them. We can further divide our code into segments using brackets of our own. Convention dictates that once we've created a new set of brackets, a new segment of code, we then add a tab before everything between them to make our program more readable. Once we've sectioned off our two print line statements, we're now ready to provide cases that must be true if these statements are to run. To do this, we preface our new sections with the Java if statement. If is a Java keyword, and it's followed by two parentheses, between which we put the statement to be evaluated. If Java determines that the statement we write between the parentheses is true, the code in the following brackets will execute. If Java determines that the statement is false, the code in the brackets will be completely skipped. This if statement, we're going to give essentially two pieces of input. We're going to give it the variable input, which if you remember contains the integer value that we got from the user, and we're going to give it the explicit value 10, which is what we're comparing it to. Java understands the greater than and the less than comparison operators. So if we make this if statement, if input is greater than 10, then this system.out.println command will only run if the user has provided a value that's greater than 10. Now we need to provide an if statement to make sure that our program doesn't always print out less anyway. We could use the less than operator to ask our program to print out less whenever the user provides input that is less than 10. That would be good in almost all cases, but if our user provided the input value 10, our program would print out nothing. To fix this, we can use the less than or equal to operator to ensure that our program always responds to the user input. Now, let's quickly run our program to make sure that it works. There's our prompt for input. Let's start by giving it a value greater than 10 and pressing enter. There's the more response and no less response. That is what we expected. Our program doesn't loop, so we're going to have to run it again to test the less output. And this time, let's give it the value 10, which should trigger our less than or equals. Ta-da! However, it turns out that there's a slightly easier way to write this program.
When we write a conditional statement, or rather a pair of conditional statements, in which we're always going to execute one of the two code blocks, it's probably a good time to make use of the else keyword. The else keyword must follow a bracketed if block, and then is followed by brackets of its own. The else statement will evaluate to true and execute the code between its brackets only if the code between the previous if brackets was not executed. If we run this program, we will get the same results as we did before, with one less bit of logic code to write. Let's end this video with a brief run-through of what other operators we can use in our if statements. And then we'll take a look at what to do if we need to compare items that are not primitives. In addition to the greater than and less than operators, we can also make use of the equality operator, which is true if the items on both sides have the same value. Make sure when you're using the equality operator that you do not, by accident, use the assignment operator instead. In some instances, your program won't compile, but other times it will compile and you'll get very weird results. If you'd like to use the opposite of the equality operator, you can use not equals, which returns true if the two items do not have the same value. It's important that we not attempt to use these operators when comparing instances of a class. We should only use them when we're working with primitives. To show this, let's modify our program so that we now take a string as user input. We'll see if this string is equivalent to this secret password code, and if it is, we'll print out yes. If it's not, we'll print out no. Now, you'll notice that NetBeans is giving us a warning here. And in fact, if we attempted to compare strings with some different operators, NetBeans would let us know that our program is probably not even going to compile. That's because Java does not expect us to compare instances of a class with these operators. Instead, classes should expose functions that allow us to compare them logically. Almost every object in Java has a few functions for this purpose. One of the most common is the equals function, which takes an object of the same type and lets you know if they're equivalent. This function returns what's called a Boolean type, which is a primitive type of its own that can have a value of either true or false. Our if statement understands how to evaluate this Boolean type. Let's run our program quickly, and let's start by inputting a bad string. And then let's input password to see our program work. That's the basic of if-else statements. I would encourage you now to play with some of the comparison operators that we looked at and try nesting if-else statements within each other. As a very last note, you may sometimes see if statements without their following brackets. This is valid syntax and is basically the equivalent of putting the entire statement on one line. Thanks for watching. Welcome back. In this video, we're going to further explore how Java handles complicated conditional statements. To begin with, let's write a very simple Java program. We'll start by importing java.util so that we can get some user input via a scanner object. And we'll link that scanner with the system.in input stream so we can use this window down here. Once we've
done that, we're going to need to get and store some input from the user. So let's create a new string and assign its value to whatever the user gives us. To keep things interesting, let's give ourselves two more string variables to work with. We'll call them S1 and S2. We'll assign the value of our first string variable to ABC and the value of our second string variable to just Z. Because this video is about conditional statements, we're probably going to need one of those. So let's create an if-else block. Here's where we'll evaluate our conditional statement, and we'll set ourselves up some output so we can see what's going on. If our conditional statement evaluates to true and we enter this portion of the block, let's simply print out true. And if the conditional statement evaluates to false and we skip this portion of the block and instead enter the else portion, we'll print out false. Now it's probably time to write our conditional statement. Let me introduce you to a new string function, the contains function. The contain function takes as input a sequence of characters, of which a string qualifies. And as output, it gives us a Boolean value, which means it will either output true or false. So our if statement should understand the result of this function and evaluate to the same. To test out our program, let's start really simply. We'll provide our contain function with the value stored in string 1, which is ABC. So if we run our program and provide it with ABCDEFG, which does contain within it the string ABC, we get the true result because input.contains evaluates to true, and we enter this portion of our if-else block. If we were to run and provide some gibberish that does not contain the string ABC, we instead enter the else statement of the block and return false. Nothing too crazy there. But let's say we wanted to make our program a little more complicated. What if we want to check and see if our input string contains both strings S1 and S2? There's a couple ways to do this, and we'll take a look at some others. But probably the simplest for our purposes is to use a complex conditional on this line. Java allows us to evaluate multiple true or false statements, or Boolean objects, at once using the AND or the OR conditional operators. The AND operator gives us a true result when all conditionals compared with the AND operator have evaluated to true. The OR operator will give us a true result when any of the conditionals compared with the OR operator evaluate to true. In our case, we want to know if our input string contains both the contents of S1 and the contents of S2. So we're going to use the AND operator. This operator works by simply providing two conditional statements on either side of it. So we're going to run our input.contains function on both string 1 and string 2. If this function and this function both evaluate to true, our conditional statement will be true as well. Let's run our program. The string ABCZ should evaluate to true in both cases. And when we press enter, we see that that is in fact the case. Were we to provide only the valid string Z, we get a false result because our AND operator evaluates false and true, which evaluates to false. Were we to use
the OR operator, this string here would in fact give us a true result because we only need one of these functions to return true now. Boolean logic can get pretty crazy pretty quick. For example, we can put at the end of our Boolean condition here the statement and false. True and false in Java are keywords. In fact, they're explicit values, just like a number or a single character would be. The keyword true evaluates to true, and the keyword false evaluates to false. Any single conditional statement ANDed with false will always evaluate as a whole to false. But curiously, if we return to our original statement here and run this program, providing it with the most valid possible input, we're going to get the true result. That's interesting because if Java had chosen to evaluate this statement and then the and false statement, we would have gotten a false result. But instead, Java seems to have chosen to evaluate this statement and then the OR statement. This can make things confusing pretty quick. Fortunately, just like in algebra, we can ask Java to do operations in a specific order. We do this by surrounding blocks of our code with parentheses. Blocks of code within parentheses will evaluate before Java leaves the parentheses to evaluate against something else. So, after we've surrounded our OR statement with parentheses, we're now computing the OR statement and then ANDing that result with false. We will now see that our program always evaluates to false here. So complex conditionals can get pretty complicated pretty quick. If we come across something like this in code, especially if it's code that we haven't written, it can take us a good while to figure out exactly what's going on. To help us with this, we have the Boolean variable. Boolean is a primitive type in Java, and a variable of the Boolean type can have only one of two values. It can be either true or false. We can set the value of our Boolean variables to be any conditional statement. So, if we wanted to simplify how our code looks in the actual if statement, we could go ahead and store these Boolean values before we actually evaluate the if statement, keeping everything much more compact and readable. That's the nuts and bolts of complex conditionals in Java. Remember that the name of the game is keeping our code as simple and readable as possible. A really long conditional might feel great to write, but oftentimes there's a more elegant solution. See you next time. Welcome back. In this video, we're going to take a look at the switch statement, which is another way that we can modify the control flow of our program. To begin, let's create a new project in NetBeans, and at least on my end, I'm going to get rid of all of these comments. To demonstrate the power of the switch statement, we're going to start by writing a program using only if blocks. Then we'll convert the program to one that uses switch statements. To begin, let's simply declare a variable x. And here's our goal. If the value of x is 1, 2, or 3, we'd like to print out the responses red, blue, or green, respectively. If x is not one of those numbers, we'll just print out a default response. Doing this with if blocks is pretty straightforward, if not a little tedious.
if x equals 1, system.out.println red. And then we'll pretty much just copy and paste this block of code and modify it for the blue and green cases. For our default case, we simply want to check that x is not equal to 1, x is not equal to 2, and x is not equal to 3. Let's give our program a very quick run through, and we get the expected results. This is a simplified version of something we might logically find ourselves doing in the course of writing a bigger program. While we put together this at a pretty decent clip, it's easy to see how this problem would become extremely unwieldy if we were dealing with many possible cases of x. And it's also pretty difficult for someone to read and figure out what's going on here. The solution, as you've probably guessed, is to use a switch statement to control our program's flow instead. When we want to execute different lines or blocks of code, depending on the value of an individual variable, the switch statement is extremely effective. Let's now rewrite our series of if blocks using a switch statement instead. The syntax looks like this. We first declare that we're going to use a switch statement, switch being a reserved keyword in Java. And then we provide the name of the variable that we'd like the switch statement to act on. In this case, x, because we're going to execute different blocks of code depending on the value of x. Then, just like we were using an if or an else statement, we're going to create a new segment of code using 2 brackets. Now, instead of creating a series of unwieldy if blocks, we create separate blocks in our switch statement using the case keyword. After each case keyword, we give a prescribed value, and the following code will execute if the value of x matches with the value of the case keyword. So, just like when we were doing our if blocks, if the value of x is 1, we'd like to print out red. Writing separate cases for each of the possible values now becomes much cleaner and easier to read. Switch statements also have a special case, the default case, which we pretty much always put at the end of a switch statement. This case will only execute if none of the other cases have executed. And it means that we don't have to write that complicated Boolean logic for our last if block. If we run this program, we're actually going to see every possible output execute. That's because we've forgotten to do something very important. Switch statements allow us to create complicated logic trees because once a case starts executing, it will continue to execute, even through following cases. Because we're writing a very simple program where we only want a single case to execute, we need to explicitly end the execution once we enter a case and finish the code. We do that with the break keyword, which exists on a line of code all by itself and simply steps us up and out of the case that we're in. Now if we run our program, we'll see the expected results. In addition to falling through from one case to another, we can increase the complexity and the power of our switch statements by adding multiple cases on a single line. Because the cases freely fall through to each other, doing something like case 1, case 5, case 7 means that this block of code will execute if we provide the number 1, 5, or 7. So there's the quick and easy of switch statements. One comment before we go though. Switch statements essentially compare the variable or explicit value we're switching and the cases using the equality operator. If elements cannot be compared with the equality operator, the switch statement will not work properly. As of Java SE version 7, you can compare strings with the equality operator, and so you can use them in switch statements. This was not always the case, and it's often still a good idea to avoid using strings with the equality operator and in your switch statements because it destroys the backwards compatibility of the code you're writing. Thanks for watching. Welcome to the introductory lesson on loops. At the end of this video, we'll have command over Java's while and do-while loops. I'm pretty excited about this because loops allow us to execute a block of Java code over and over again, as many times as we see fit. This is a pretty cool step in our learning process because the ability to perform small tasks many times in rapid succession is one of the things that makes computers better at certain tasks than humans are. To begin this video, let's create a new NetBeans project, enter the main method, and simply declare an integer and give it a value. You can choose any positive value. We're going to ask our program to print out the phrase "Hello World" a number of times equal to the value of our integer. To do this, we'll employ a while loop. While loop syntax looks a lot like we're writing an if statement. We begin with the reserved while keyword and follow it by 2 parentheses, inside which we're eventually going to place a conditional statement. Just like it was an if statement, the following block of code will only execute if our program reaches our while loop and evaluates its conditional statement to true. What separates while loops from if statements, however, is that when the end of the while loop's block of code is reached, our program will basically jump back and execute this line of code again, evaluating the conditional statement and re-entering the while loop's block of code if the conditional statement is still true. Let's start off by setting up the logic for our while loop. We have the number of times we would like our loop to execute stored in the value of integer I. But we're going to need a way to communicate this to our loop. Well, any loop that is not going to run infinite times is going to need to make some control flow changes within the content of the loop. In our case, let's change the state of our program each time the loop runs by decreasing the value of I, so that when I reaches 0, we will have ran the loop 5 times. If that's the case, that means that we only want our loop to execute when the value of I is greater than 0. Let's pause quickly and take a look at this line of code here. I equals I minus 1 is a perfectly valid statement. But there's a shortcut we can use that's a little faster and easier to read. We can use I minus minus to decrement the value of an integer variable by 1. Once we've set this up, the only thing left to do is place the functional code inside of our loop. That's simply a print line statement that says, "Hello world." Now, let's run our program and see what happens. There we go. 1, 2, 3, 4, 5 hello worlds printed to our window, just as we intended. Often, we allow small programs like the ones we're writing here to end when there's simply no more code for them to execute. However, while we're working with loops, we're probably going to make the mistake of accidentally creating an infinite loop and running a program that has no end. When this happens, we're going to need to turn our program off manually. In NetBeans, there's a handy little stop button right here. If we're running a program through a command prompt, Control-C is a common command to cancel the execution of a program. Now that we have a handle on basic while loop syntax, let's try something a little more complicated and much more dynamic. The program I have in mind is going to need some user input. So let's import java.util and set up a new scanner. Rather than gathering user input right away though, we're going to collect new user input every time our while loop successfully executes. Each time we gather this input, we're going to need somewhere to store it. So let's create a new string whose purpose will be to store the value of the newly acquired input. This variable's value will change a number of times throughout the execution of our program, because at the beginning of every while loop, we'll be assigning it a new value. Were we to simply execute this program, it wouldn't be very interesting for us, the user, because the old values of our input string would constantly be getting lost when we assigned it a new value. So let's create another string whose purpose is to store all of the concatenated values that we've gotten from the user. Then at the end of our program, we'll print out the value of this string so that the user can see we've been storing their input. To add the value of input to our all string on this line, there's a couple of things we can do. We can add strings with the addition operator just fine. So the statement all equals all plus input, with all and input being strings, and that being a plus sign, is perfectly valid. However, when we're adding something to itself and working with a primitive or a type that can act like a primitive, as string can, we can also use the plus equals operator, which performs the same function. We also cannot forget to re-implement our decrement of the integer value I so that our program doesn't run for infinity. Now, if we run this program and provide 5 strings of input, we'll see them all spit back out at us as expected, which is pretty cool, but I've got bigger plans for this program. Actually, if we'd only wanted to write the program we have right here, a for loop, which we'll learn later, might have been completely appropriate. But for what we're about to do, while and do while loops are pretty necessary. What I'd like to do is get rid of our counting variable in this program. Instead, we're going to allow the user to tell us when to stop executing our program. When the user sets the value of input to the string stop in all capital letters, then we'll quit executing our while loop and print out all of the strings they've given us so far. So we only want this while loop to run while the value of input is not the value stop. You'll notice that we're getting a precompiled error.
and we'll get a full-on compiler error if we do attempt to run our program. That's because our program knows that when we attempt to execute this conditional statement for the first time, the value of input will not have been set. Even though the non-existent value of input is not equivalent to stop, it's very bad form, and in the case of a string here, not a primitive, not possible for our computer to access any of its methods before it's been given any value at all. One inelegant solution here would be to give input a start value, like we did with all. But there's actually a better way. Once our loop has executed for the first time, we know that input will have a proper value given by the user that may or may not be stop. So, what if instead of checking our conditional at the beginning of our loop, we checked it at the end? This is in fact an option. Do-while loops operate just like while loops, but the first time they run, they won't check to see if a conditional is true. They'll simply run through, and then at the end, check their conditional statement. We do need to put a semicolon at the end of the conditional statement on the back of the do-while loop. I just mentioned that because I'm always forgetting it. Now, if we run our program, we can give any number of strings and then type in the string stop to see everything we've typed so far printed out to the screen. As a last little note, with just about anything followed by its own code block, you'll see syntax like this, where you have a keyword and maybe a conditional statement, and then brackets on the following lines. Or you might see the brackets start on the same line as the keyword and conditional statement. Both methods are completely valid. And in fact, this here with everything on the same line is probably quickly becoming more common. For the course of this video, I'm just going to spread things out onto as many lines as possible to keep everything easy to follow. Thanks for watching. I encourage you to play around with the program we've written here. Try executing loops that you think will push the boundaries of how much information a string can hold, or play around with loops that present an enormous amount of information to the screen. This is stuff that computers do that we simply couldn't with pencil and paper, so it's pretty neat. See you next time. Welcome back. In this video, we're going to take a quick look at for loops. We use for loops to solve a common problem in Java in a very semantically elegant manner. For loops are appropriate when we're going to be iterating a variable to count how many times we've looped. To start us off, I've written a very basic program using a while loop. It prints the values 1 through 100 to the window on our screen. Once you've hashed out in your mind how this while loop is working, now we're going to write the same loop with a for loop so that we can see how the for loop is more elegant in this particular instance. Let's comment out our while loop so that we can still see it without having it execute any of its code, and begin writing our for loop instead. The basic syntax for a for loop looks very similar to a while loop. We have the reserved keyword, 2 parentheses in which we'll put some information that the loop needs, and then the code block that we're going to loop through. Unlike a while loop, which just takes a conditional statement between these parentheses, we're going to provide our for loop with a bunch of information. Because the for loop is designed to handle a specific case, once we give it all this information, it will know exactly what to do with it.
This alleviates the need for us to handle code outside of the loop and manually increment or decrement inside of the loop. It keeps the functional bit of our code, our print line statement, and in more complicated programs, the more complicated information that may be here, more isolated. Our typical for loop takes 3 pieces of input. First, we need to declare the variable that we're going to be incrementing or decrementing to count the number of times we've looped. In this case, we'll use an integer I, and we'll give it an initial value of 0. We follow this initial statement with a semicolon. This is not a function call, it's special syntax for the for loop. The second piece of information the special syntax requires is the conditional statement that we need to evaluate each time we're going to restart the loop. If this conditional statement is ever not true, then our for loop ends and we continue resuming our code after the for loop block. In this case, our conditional statement will be the same as it was for the while loop. We want our last iteration of the for loop to be when I is equal to 100, when we'll print out 100. Once I is no longer less than or equal to 100, it's time to exit our for loop. Just as the first piece of information we specially gave the for loop saved us from having to handle a variable outside the scope of our loop, the last piece of information we give the for loop takes the place of us having to manually increment or decrement our counter inside the scope of the loop. This is the modification special code, and whatever we provide the for loop here will run at the end of every loop. In this case, we'd just like to increment the value of I at the end of each looping through. I think you'll agree that this program is much cleaner than our while loop. Now, let's just check that it performs the same task, printing the value of 1 to 100 to our screen. Oh, I actually made a mistake here. We started our I off at 0 instead of 1. Now we will print the value 1 to 100 to the screen. Were this statement to execute at the very beginning of our for loop, the 0 would have been correct, but this executes at the end. When we're working with large numbers and incrementations in Java or any programming language really, we call errors like what we just ran into off by 1 errors. Off by 1 errors are those kind of little logic mistakes that even experienced programmers can run into if they're not paying attention or just look the wrong way, for an instance. Learning to recognize the symptoms of off by 1 errors, for example, one more line outputted than expected, will allow us to track them down and find them much more efficiently. Thanks for watching. In this video, we're going to learn about Java arrays. Arrays are Java's most basic and commonly used data structure. Data structures are tools that allow us to store and access sequences of information rather than using individual variables. Variables are great when we have one specific piece of information that we need in our local programming space. But data structures are used when we want to store large or complicated sets or series of information. We're going to start this video in some visual learning slideshow mode, and then we'll jump into our NetBeans IDE to write some actual Java code and make use of arrays. Let's begin by taking a look at the syntax behind declaring and initializing an array in Java. This line of code right here will cause to come into being an array with enough space to hold 7 characters. To the left of our assignment operator, this syntax looks pretty familiar, not unlike the syntax we would use when declaring any other primitive or object. We begin by telling Java what type of element we're going to declare here. In this case, we're declaring a character array. The empty brackets let Java know that rather than creating a single character variable, we'd like to declare an array type variable. Because our array is a variable just like any other. We'll access the elements of the array through the array's variable name itself, not through the individual variable names of the elements, which, thanks to them being stored in an array, we don't need to assign. Once we've told Java what type of array we're going to create, we give our array variable a name. I've just called this one array_var. To the right of our equality operator, things look a little different. You may have seen the new keyword used in the past when we need to create a new instance of an object, not a primitive element. When we create a primitive element in Java, Java knows exactly how much memory space is needed to store the primitive element, no matter what its value is. However, objects and arrays can have many different size requirements. Because a single array variable can be assigned to arrays of different lengths, we're going to need to tell Java how much memory to put aside for each of these different length arrays when we create them. When creating an object or an array, therefore, we use the new keyword to tell Java that it should set aside memory space to place what we're about to cause to come into being. And that thing is a character array of length 7. I wanted to start off with a slideshow so that we could do this learning visually. After declaring and initializing our 7-character array, what exists in our program's local memory is something like this: a block of memory large enough to store 7 individual characters, and whose location is accessed by our program when we call the array_var variable. This allows us to run lines of code like this one. Our array_var variable gives us access essentially to 7 different character variables. When we don't want to assign a new array to our array_var variable, we're probably going to be accessing these character variables as individuals. We do this simply by using array_var's variable name and then following it with brackets and then the index of the individual character we'd like to access. Remember, when our computers count indexes, they almost always begin with 0. So in Java, our 7-character array has indexes 0, 1, 2, 3, 4, 5, and 6. If we execute this line of code here, setting the value of index 2 in our array_var to C, we will take the 3rd block of memory and assign its value to the character C. Sometimes, when we declare an array, we just want to go ahead and assign values to all of its memory blocks right there in the code explicitly. When we want to do this, rather than using the new keyword and having our computer space out the new memory space by telling it how long the array is, we can explicitly declare an array, like we were explicitly declaring a primitive type using this syntax here. This syntax here will create an array of length 7 simply because 7 elements are declared. And of course, it will map the values accordingly. Now, let's jump into some Java code and put arrays to work. All right, I think it's time to employ our newfound knowledge and write a computer program. Arrays allow us to manipulate amounts of information that would be unwieldy to deal with at the individual element level. So we're going to jump right into the heavy hitting stuff and create a cool computer program. If you need time to catch up logically, feel free to pause the video. Arrays are a big logic step, and if you haven't worked with something like them before, it can take a little time to wrap your head around. The good news is, if you make it through arrays in Java, you're probably going to be just fine with anything else the language can throw at you. The program I would like to write will print the English alphabet to our screen. We could, of course, do this all by ourselves, by just doing something along the lines of this, but that's pretty mind-numbing and it's not going to teach us much. Instead, the program that we're going to write here is both going to learn, store, and print out the English alphabet. To do this, we're going to need to employ our newfound knowledge of arrays, our existing knowledge of how characters work, and map to integer values on the ASCII table, and we're going to need a single for loop. Let's set aside a position for that for loop and begin our programming by declaring and initializing a character array in which to store the characters of the English language. So we tell Java that we're going to need a variable to point to an array of characters. I'll call it alpha. And then we're going to ask Java to set aside memory space, thus the new keyword, for 26 characters, because the English language has 26 letters. Now, if you'll remember, character values can also map to integer values. To find these, we look for an ASCII table. The value we're looking for right here is 97, the integer value of lowercase a, the first character in the English language. So let's create a little comment here and store the value 97 for later use. Now, to our for loop. Our for loop is going to run 26 times. Each time it runs, it will take the next character in the English alphabet and place it in our character array alpha. To make sure our for loop runs exactly 26 times, we should declare a counting variable and set it at 0, and say that our for loop should continue to run as long as the value of our counting variable is less than 26. Lastly, every time our for loop runs, we need to increase the value of our counting variable by 1, so that it goes up each time, and after 26 iterations, this statement will no longer be true and our loop will stop. Now, here we're going to assign the value to one of the spaces in our character array. To access one of these spaces, we use the name of the variable assigned to our array, and then a number within these two brackets to tell Java which character we would like to assign a value to. This index should be different each time we run through the loop. And this is the beauty of for loops. By starting our counting variable at 0, we can use the counting variable to map to the index of our array. Our counting variable's value as our loop runs will range from 0 to 25 on its last run. The index values of our array, because computers start counting at 0, is also 0 to 25. So, what value do we assign to each character so that our computer will learn the alphabet? Well, I like to think of it this way. The value when we run through the loop for the first time, when I equals 0, should be 97, the integer value of the character A. So, we should assign 97 plus I as the value of each character in our array. So, when we run through our loop the second time, we'll be assigning the value 97 plus 1, or 98, which is the integer value of the character B. In this instance, Java is asking us to please explicitly let it know that we would like to cast this integer value to a character and then store it. Now, to finish up our program, all we need to do is print out our alpha array. To do this, let's make use of a nifty function in an always accessible object called arrays. The arrays.toString function will convert a single dimension array, which is the kind of array that we've created here, that is capable of being converted to a string, to a string. Now if we run our program, we'll see Java's representation of the English alphabet in array form. Whew, if you followed along with that, you should give yourself a solid pat on the back. That's some heavy lifting we just did. Now, let's jump back into the theory side for the rest of this video. I misled you earlier when I led you to believe that our newly created arrays were filled with empty memory space. In fact, when we declare a new array of a primitive type, that is characters, integers, Boolean, floats, those guys, Java fills it with default values. For example, our new array of 7 characters was filled by 7 space characters, what you'd get if you press the space bar on your keyboard. Similarly, an array of integers would be filled with 7 zeros. After this video, I recommend you boot up a Java IDE and create some empty primitive arrays and print them out using println to see what the default values are. Now, we can create arrays of any object available to us. However, objects, unlike primitives, do not have default values that they set themselves to when they are initialized as part of an array. Anything that we would need to use the new keyword to create will not default initialize in an array. This is an important thing to realize. Let's say for some reason we decided that we must have 7 scanners in an array. This statement here does not create 7 scanner objects for us. It simply sets aside the memory space. We can create scanner objects and assign them to these memory spaces, but if we try and call one of these memory spaces and use a scanner specific function from it before we've assigned a scanner to the memory location, our program will crash. We'll get what's called a null reference exception, which means that Java asked the nothingness to behave like a scanner. Thanks for watching. In Java, our most basic data structure is the array, which allows us to store sequences of like-typed information and access them through a single location in memory. Sometimes, however, arrays are unwieldy, and we want to use more strongly organized data structures so that they can be easier for humans to understand and write programs around. Oftentimes, what's appropriate here is a multi-dimensional array. Multi-dimensional array is a pretty scary sounding name, but in fact the concept behind them is very basic. The idea is, what happens if we create an array of arrays? The line of code at the top of this screen shows the syntax to do just that. This line of code will create a 2-dimensional multi-dimensional array. You'll see it's very like the syntax for simply creating an array of characters under normal circumstances. But in every instance where we reference the array nature of the variable, Java is now going to need 2 pieces of information. This line of code will tell Java to create 3 arrays, each of which has enough space to store 7 characters, or 3 arrays of length 7. To cement our understanding of this concept, let's write a Java program that utilizes 2-dimensional arrays. While we can use multi-dimensional arrays to store information in abstract manners, it will probably be easiest for us to learn them by representing an actual 2-dimensional object with our 2-dimensional array. In this case, the chessboard. The classical chessboard is divided into black and white squares. It's 8 squares in width and 8 squares in height. And the program we're about to write will store in Java a virtual board with the squares correctly labeled black and white. And then at the end we'll have it print this board out to us so that we can see we wrote our program correctly. Let's begin by simply declaring and initializing the array we're going to be using. We'll use an array of characters for this task, giving the white squares the character value of capital W and the black squares the character value of capital B. Since a chessboard is an 8x8 grid, we're going to want to declare a 2-dimensional array of 8 arrays, each of which contains 8 characters. Now, in order to assign our squares their proper values, we're going to need to loop through this array to get to each individual node and give it the value we want it to have. For loops and arrays get along great because arrays always know how long they are. But a single for loop doesn't allow us to meaningfully loop through our 2-dimensional array. A for loop really just goes in one direction, and our 2-dimensional arrays have 2. To solve this, we're going to make use of nested for loops, or a for loop within a for loop. Our outer for loop will loop through each array in turn, while our inner for loop's job will be to loop through the nodes that those arrays contain. Common practice when creating for loops is to use an integer variable I for your initial for loop, and then j, k, and so on for subsequent for loops. However, because we're creating a chessboard, which is an actual object, I'm going to choose the value y for our outer loop, because what this loop is doing is iterating down the y-axis of our chessboard. As I mentioned, for loops and arrays get along great because arrays know how long they are. We could simply state that we would like this loop to run 8 times, which is the result of this statement here. But that's not good dynamic programming, because if someone was to go along and change the size of our chessboard, our program would now break. And we can write this loop such that it will work for a chessboard of any size. To do this, rather than explicitly saying our loop here should run 8 times, we should have it start by asking our array how long it is. To ask an array their length, we go array.length, and that returns an integer value. This is a 2-dimensional array, so simply calling the name of the array and then .length will get us the length of the array's outermost segment. In this case, we're asking our 2-dimensional array, how many arrays do you contain? To finish off this for loop, we simply need to increment y after it runs each time. Now, let's do something similar for our inner loop. Because this loop will be iterating through the individual elements of our rows, x for the x-axis seems an appropriate variable name to use. Because our array is currently the same length in both its segments, an 8x8 array. This statement would work for now, simply going board.length again. But once again, it's not good dynamic programming. If someone was to go through and change the size of our board to be an 8x10, this program would no longer execute properly. Instead, at the beginning of this for loop's execution, let's ask the array that we've currently accessed through the outer loop how long it individually is. This once again makes our program robust and allows us to accommodate multiple sizes for our board. On that note, let's make things even more difficult for someone inadvertently to break by storing the dimensions of our board in a separate location. We'll simply create a variable called boardDim for board dimensions, assign it the value 8, and then reference it when we create our arrays. Arrays are perfectly happy using an integer in a variable to initialize themselves, letting us create dynamically linked arrays if our program calls for it. Now, if someone wants to go to this program and scale up our chessboard, they need only to change this value here. Okay, the next step in our program is to assign character values to each node in our array. Capital B for black squares and capital W for white squares. Let's start off by writing the code if we wanted to make all of the squares white. Our double for loop will pass through each node in our two-dimensional array when it executes. So, this code in our inner for loop, each time we execute it, we're executing it in terms of one of those single two-dimensional array nodes. To get that node, we're going to need to ask our board array what is located at row Y, column X, and then we'll change the value of that node. The thing is, each time this inner loop executes, we're going to want a different value for the nodes so that we get a chessboard that is alternating white and black squares. To help us do this, let's add another variable to our program. It'll be a Boolean variable, and we'll just call it isWhite. If isWhite is true, then the next square we add will be white. If isWhite is false, the square will be black. To code that out, let's use some if statements. If isWhite, then we put a W in our square. If isWhite is false, we'd like to put a B in the square for black. To check if something is not true, we can invert any Boolean value with an exclamation point beforehand. This will work for Booleans or even conditional statements. Now, we simply need to flip the value of isWhite. Well, using our knowledge of the exclamation point operator, which flips the value of a Boolean, we can flip the value of isWhite from true to false or false to true by simply setting its value to the knotted version of itself. Unfortunately, this program is not quite perfect. It turns out that if you do this, your chessboard is going to have every single row starting with a white square, while a real chessboard alternates, with every other row starting with a different colored square. Fortunately, this loop here runs once for each row of the chessboard. So, if we were to simply add an extra flip to our isWhite Boolean value at the start of every row, we would get alternating row starts as well. If we do it like this, we need to start isWhite off being false because it's going to be immediately changed to true when this loop executes for the first time. If you followed along with that, let's go ahead and write the final bit of our program, a line of code to print out our chessboard to the screen. Actually, we're going to need a bit more than a line of code. We can use the printLine function along with arrays.toString to print the contents of a single array to the screen. But this technique won't work so well with a two-dimensional or more dimensional array. So we're going to need to use a for loop again, just like this one here, to grab each array in turn and then print them to the screen. This works pretty well because printLine will automatically carriage return or give us a new line in between each row we print. Here, let's use the conventional syntax variable I to iterate through our for loop. You'll notice that Java does not yet understand this arrays keyword. That's because arrays lives in the java.lang package. It can be kind of annoying when we call a function or a class and Java doesn't immediately know where to find it, and we have to go online and Google to locate it. If we're working in an IDE like NetBeans here, sometimes there's a shortcut to find common packages. In this case, if we right-click on the problem statement and ask NetBeans to fix imports, NetBeans will go through the common packages and see if it can figure out what we're doing. In this case, NetBeans has located the arrays class and added the import for us. Now, because we don't want to attempt to print out the contents of the two-dimensional array each time our for loop executes, which wouldn't work very well anyway, we're going to tell our printLine statement to print out the contents of board I, or the individual array within our two-dimensional array that we've accessed here. Now, let's see if we got everything right the first time through and run our program. Wow, it looks like we did. There's an alternating white and black representation of a chessboard that begins with a white square and has rows starting in the proper manner. This might not look like much now, but its significance is pretty big. We've essentially taught our program how a chessboard looks and is. This is the first step to us creating something much bigger, like a program that plays chess. Were we to create a program that plays chess, which is a little out of the scope of this video here, but we can talk about it some conceptually, we would probably want our individual squares to be able to store more information than just what color they were. For example, we would probably want them to know what piece was on them. To make this happen, we could utilize a three-dimensional array. We could create an array that looks like this so that each square could store an array that holds two pieces of information, one character for its color and another character to represent what piece it's on. So that's the basics of multi-dimensional arrays in Java. Thanks for watching. When we need a Java data structure, we should often start by asking ourselves if a simple array is sufficient. As the simplest data structure available to us, if we can write our program easily and neatly using just an array, that might be our best option to keep our program simple by extension. If you're writing code that must run absolutely as fast and memory efficiently as possible, arrays also have very little overhead. But in today's development world, where memory efficiency and speed really aren't concerns for your average program, which is going to run just memory efficient and speedily enough, sometimes we want to employ data structures with more built-in functionality, or maybe which are designed for a specific purpose. A data structure with additional functionality is the array list. One of the weaknesses of traditional arrays is that when we instantiate them, we have to give them a specific length. So we have to know how large we want our array to be. An array list is basically an array wrapped in some additional code that causes the array to increase or decrease in size to always be the size of the number of elements it contains. To see this in action, let's write a program that would actually be a little more difficult to write if we just used a standard array instead of an array list. We're going to want to begin by importing java.util. That's because java.util is where the scanner class, which we'll need to get user input, and the ArrayList class itself lives. Once we've declared a scanner, which we'll utilize some more later, it's time for us to declare our array list. Simply declaring an array list looks a lot like declaring any other object. We say what type of object we'd like to create. We give it a name. We use the new keyword because Java is going to have to set aside some memory to create this object since it's not a primitive. And then we tell Java to actually create the object. Even though we're not going to provide any arguments for our array list creation, we still need to follow it with the double parentheses. This is actually valid code that we've just written. But generally, when you create an array list, you're going to do a little bit more. The array list memory that we've created right here will actually store any single entity we place within it. That might sound really great at first, but honestly, it's not a good thing to have in our program. It's really easy to get confused if we have array lists or any data structure really that's storing just about anything. And if we feel the need to do that, we're either doing something really complicated or more likely we're not writing our code as cleanly as we should. Maybe more importantly, once we store an anything in our array list, it's very possible for us to sneak by our compiler and create code that compiles okay but breaks at runtime, causing the kind of bugs that are really bad to have in commercial software because they can break when people are actually using it. To solve this problem, we can tell our array list to only accept information of a certain type. We do this by following our array list declaration and instantiation with these double character brackets and placing a type within them. In this case, we've declared and then caused to come into being an array list that will only allow strings to be stored within it. I guess I should now tell you what type of program we're going to write. I'd like to write a program that will take an input string from the user. It will store this input string and every other input string the user has ever given it, and then print them all out each time the user inputs a new string. This would be really difficult to do with an array because if the user ever inputted one more string than the array was designed to hold, our array would Best case scenario, not accept the string. Worst case scenario, our program might crash. But our array list object will simply resize to fit the number of strings that it's currently holding. So, we're going to need a loop so that our user can input more than one string to the program. For now, let's just say while true. This is an infinite loop. It will run forever. But while we're building our program and debugging it, we can always just stop it manually. Each time our loop runs, we're going to want to use the next line function on our scanner variable to grab a new line of input from the user, which we're going to store in our array list. When we're working with object data structures, that is, data structures that have code wrapped around them and functions and methods of their own, we're generally not going to have to deal with the individual indices of memory, which can be pretty nice. Instead, we use their provided functions to add, remove, and manipulate the information within them. In this case, adding something to an array list is pretty easy. The .add function in an array list will add whatever input we give it, in our case as long as it's a string, to the end of the array that the array list contains. So this line of code right here will request a new input string from the user and then put it on the end of our array list. Once we've done that, we can simply use printline to print our array list out to the user. Printline doesn't know how to take an array list as input. Actually, it might, but we should explicitly use the toString function, which almost every object in Java implements. Now, when we run our program, we'll get prompted for some user input, and we'll see that input echoed back out at us. If we give Java some more input, we'll see our new input and the old input has been stored in our array list. So that's pretty cool. Really basic program that would be more difficult to write with a simple array. Now, array lists have a lot of power contained within them. We can turn them into arrays, create them from arrays, and all sorts of things. And if we go to the Java documentation and check under java.util for array lists, we can find all of their methodologies. Let's add a couple more features to this program so that I can walk you through some common array list methods. Array lists have a function which takes no input called clear, which will erase our array list. We can utilize this function to give our users some control over our program. Let's say that if the user inputs the string clear, we would like to erase all of the information in our array list. Well, that's a conditional statement I just made, so we're probably going to want an if statement. We need to check the item just added to our memory variable, our array list, against the string clear. The item just added to our array list will be at the very end, the last item, the item with the highest index value. Unfortunately, there's no last item function implemented for array lists, but we can essentially create one ourselves by mashing together two array list functions. First, in order to get an item from an array list, we're going to usually utilize the get function. Get is very similar to the double brackets we would utilize if we were accessing an item from a traditional array. Get is going to take an integer value and it's going to map that integer to the index of the array contained within our array list. So, to get the last item in our array list, we need to know how many items are in the array list, and then we want to subtract 1 from that value, because the last index of an array with a length of, let's say, 7 would be 6, since the array starts counting at 0. To get how many items are in our array list, we can use the size function, which takes no arguments and simply gives us an integer that is the size of the array, how many items it contains. Once again, we want to subtract 1 from that value so that we're properly accessing the last index, not the index behind it, which could contain anything. And let's wrap that whole block in some parentheses. This block of code here is going to get for us a string. We know that we can compare strings by using the dot equals method. And we can actually call that method from the string object that this block of code returns, even though we haven't assigned it a specific variable name yet. Objects exist even if we don't have a name for them, and we can call their methods and do just about anything we like with them if we've just returned them from something else. So, that's a pretty crazy statement we've just written, but as long as we've written it right, when our user enters clear to the program, we will erase the array list. Once we've written this code once, we can write very similar code to give our user different functionality options. Let's also allow our user to type in end. Currently, because we're in a while true loop with no way of getting out, we're in a infinitely looping program until we manually turn it off. But by using the break Java keyword, which will jump us out of whatever loop we're in, or function if we're in a function, we can make this an escapable loop and let the user essentially turn off our program, because once we leave this loop, there's no more code to execute and our program will end. Be careful when you're using break statements. Make sure it makes sense to do so, because they can be a little confusing if you're going through someone's code and they're breaking and jumping the control flow all over the place. So let's run this program and see what happens. We'll start by giving our program some input and building up the array list. And now, oh no, I broke it. Okay, this is actually a pretty interesting error that we made. And I actually just made this error right now recording this video. I'm going to leave it in because this is a great learning experience for us. It also shows you that even if you're an experienced programmer, you're going to make mistakes. One of the reasons that, for example, we should use typed array lists whenever we can, so that our mistakes are easier to figure out and fix. Back to the error at hand. Our program has thrown an array index out of bound exception. This means that we tried to access memory that our memory array did not have access to. Specifically, we tried to look at what was at index -1 of the array. Since arrays start at index 0, they don't have anything at index -1. Any piece of our computer's memory could be there, and programs aren't allowed to just go looking through a computer's memory because they want to, for security reasons. So, why did this happen? Why did we ask for index -1 of an array, which is never going to be a valid array index? Well, This line of code executed just fine. Our program saw our clear command, understood our first look at our array index, and cleared the array. Immediately following that, we asked our program to check again for the last item added to our array. When we did this, we executed this bit of code right here. First, we asked Java, what size is our array list? Because we just cleared our array list, Java told us the size of your array list is 0. There's nothing in it. Then we subtracted 1 from that value to get -1. And we ran memory.get on that -1 value. Thus, we asked Java to take a look at what was at index -1 of our array. At which point Java said, whoa, 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 what are you doing? It's not cool. I'm going to crash. So, how do we solve this? Well, there's a couple things we could do. We should probably just check and make sure that our arrays are not empty before we run these functions. That looks like a few more lines of code than I want to put in this video. It's not undoable by any sense of the word, and I encourage you to try and implement a better solution than this yourself. For now, just to get our program quickly up and running without crashing, let's change our pair of if blocks to an if-else statement there we go, with another if statement embedded in the else. This will prevent us from ever running both of these lines of code back to back. If our clear statement executes, if this is true, then we will not check for the second if statement. Now if we run our program and give some gibberish input to build up our array list and type in clear, we're going to properly get the response of an empty array list. We'll never hit this statement with an array of size 0 because we're always going to add a line to our array just beforehand. Now, let's cross our fingers and check that the end program works. And, in fact, it does. The break command breaks specifically out of loops and functions. So, even though we've nested it within this if and else statement, it's still going to break us out of the while loop. So that wasn't quite as clean a look into array lists as I had expected it to be, but I think that little trip up we had was a great learning experience. That's actually a pretty interesting error we ran into. Nonetheless, I hope you've seen how different data structures have different purposes. As always, thanks for watching. Welcome back. In this video, we're going to take a look at Java's map data structure. I wanted us to start with a bunch of already formatted information. So I began this video by creating a little program on my own. I would encourage you to find this program in the companion files for the course and take a look through it. Make sure you understand how it works. I'm operating on the assumption that we're not yet familiar with file input and output, so I dropped all of the data that we'd normally want to store in a file or somewhere more manageable right into the code of our program. This data is an array that I've called all names, and what it is a list of names of famous people, and their individual first and last names are also divided up. So Jane Addams comprises the first two elements of the array. her first name at all names 0, and then Adams, her last name at all names 1, and so on, with every 2 elements in the array being a single person's first and last names. This is also a good chance for me to show you a nifty little NetBeans feature that's available in most IDEs. We can talk to our IDEs often, if they support features like this, by putting instructions for them in the comments of our code. Because these instructions are commented out, they won't in any way affect the way our Java code compiles and runs. But we can talk to the IDE. This instruction here, paired with its ending instruction down here, tells NetBeans that we'd like it to section off this code so that we can use our little box over here to expand and contract the block of code. It doesn't make the code go away, it just hides it from us so that we can develop without it cluttering up our screen. Now, a very quick explanation of the program I've written to start this video off. We have an array of strings that contains the first and last names of a bunch of famous people. And the program I've written simply loops through this array and determines if it's looking at a first or a last name, and then places those names in separate arrays of their own. At the end, when we print out these arrays, we have 2 separate arrays, one of first names and one of last names. And the relationship of these arrays, because we've placed them into the 2 separate arrays in order, is that the indices of the arrays match up. So at first name 0 and last name 0, we have the first and last names of Jane Addams. What I'd like to do now is expand this program and place all of this information in a single data structure, a Java map. What maps do is basically take 2 sets of information, and while we create that map, we let it know a relationship between one set, which we'll call the keys, and the other set, which we'll call the values, such that each key maps to a value. This will allow us to ask our program questions like, given a famous person's last name, what is the first name that associates with it? To begin, I've gone ahead and imported java.util, where the map interface lives. Now, let's get rid of these print line statements, and instead, at this point in our code, when our first names and last names arrays have been set up, let's start constructing our map. Let's begin by using the map keyword. And then, as with most data structures, we need to tell Java what type of information our map is going to take. Maps take 2 sets of information, so we're actually going to have to give it 2 types, comma separated. The first information type is the information type for the map's keys. We're going to use last names as our keys because we don't want our map to store multiple values in one key. And it's much less likely that we're going to have multiple last names. Additionally, it's a lot more valuable for us to ask the first name of the famous person named Adams rather than the last name of the famous person named Jane, of which there are probably much more. Anyway, the data type of last names is string, and actually the data type of first names is string as well. Now we give our new map variable a name, and it's time to cause it to come into being, to instantiate it. To do this, we use the new keyword. And then map is not actually an object. It's what we call an interface. For the most part, we interact with interfaces and objects the same way. But we cannot simply declare an instance of an interface. Rather, interfaces are additional wrappings of functionality that we place on top of objects, much in the way that array lists add additional functionality to arrays. So, to create a new map, we need a simpler type of object which we can wrap the map interface around. A great candidate for this is the hash map. Once we've created our hash map and assigned our map variable to it, we now interact with this famous people variable just as if it was an object with all of the map functionality. Additionally, if we would like, we could call hash map only functionality on this object as well. While it's a little out of the scope of this particular video, the power of interfaces is that we can assign them to objects of different types, giving common functionalities to otherwise distinct object types. But for now, we're mostly just interested in the power and function of Java maps. You'll notice that we didn't have to explicitly tell Java what types our hash map was going to take. This is a stylistic choice, really. If we wanted to, we could explicitly declare the types that the hash map would take. But since we're only going to interact with our hash map in terms of its functionality as a map, simply protecting us from adding anything but strings when we interact with our hash map through this variable, which is currently our only way to access it, should be just fine. Once we've set up our map, it's time for us to go through and fill it with information. For this, I think a for loop will be appropriate. We're going to need to add a number of pairs of information, that is one key and one value, equal to the number of items in either of these arrays, because they have the same length. So let's just choose last names. And we'll set up a for loop that iterates through every index from I to the length of last names minus 1. These I values will map to the indexes of the last names array. And because the first names array has the same length as the last names array, the first names array as well. Now, for each I, we're going to execute our maps put function. The put function is similar to an add function. It inserts information into our map. However, this function expects two pieces of information. It expects first our key, which is the value we're currently looking at in last names, and then it expects the associated value. This is the value we're looking at in first names. Each time we execute this line of code, we'll be adding a new key value pair to our map. Once we've set up the map, because with all our information already in our program, that's all we need to do, it's time to ask it some questions. It would be perfectly possible for us to create some nice user input for this program, but I think at this point in time it would be a little tedious. So let's just ask our program some explicit questions right here and make sure we get the right responses. We use the get function to ask our map its basic question that it's designed to answer. What is the value paired with a given key? So let's ask our map, what is the value paired with Adams? Or, put in more human understandable English terms, what is the first name of the person in our map whose last name is Adams? When we run this program, we get the expected result, Jane. And let's just run it one more time to make sure we haven't made any silly mistakes. Let's see if our program answers Frank for Sinatra. And indeed it does. While it's possible for us to write a program like this simply by looping through our arrays when we get user input and finding a last name and then storing that index and getting it from first names. Our map interface essentially does that for us. Perhaps more importantly than that, when we're working with other programmers or looking at code that we didn't write just yesterday and we see a map, we understand immediately its intended purpose and what functionality it implements. In almost all cases, just writing code that works is equally important, and maybe not even as important, as writing code that works because it makes sense and will be understood by others and yourself who come across the code in the future. As always, thanks for watching. In this video, we'll learn about the all-important Java method. If you're an experienced programmer, you've probably run across functions in the past. In Java, the terms function and method are basically used interchangeably, with method being the more technically correct term that you'll see in documentation. Methods are a tool that allow us to break up the control flow of our program. They let us declare little subroutines, or sometimes we can think of them as smaller programs that we can reference in our program, so that we don't have to write absolutely all of our program's logical code in one single block. An example of a method is the .next method found in the scanner class. Rather than having to teach our scanner object how to acquire the next set of user input in this program I've written, I can simply call the next method from the class that someone else has written in the past. This turns what would probably be a couple 100-line program into the 22 lines we have right here. By writing our own methods, we can tackle complicated challenges by breaking them into much smaller and easier to manage parts. Programs that are properly modular and make use of methods are also much more human readable. Because we can give our methods our own names, our program can be much more self-explanatory and make use of a lot more English, or whatever language we are native to, words. To show you the power of methods right from the start, I've planned a pretty complicated program for us to write today. Our goal is to create a temperature conversion program. And I've set up the input portion of this program for us already. So far, this program takes 3 pieces of information from the user. A temperature type, these being F for Fahrenheit, C for Celsius, and K for Kelvin. Then it takes another temperature type. This is the type that our user would like us to convert to. Once again, Fahrenheit, Celsius, or Kelvin. And then we get from the user the value of their initial temperature. Our program with these 3 pieces of input will convert the given temperature value from Fahrenheit, Celsius, or Kelvin to Fahrenheit, Celsius, or Kelvin as the user desires. This is a challenging program for 2 reasons. First, there are 6 possible control flow cases because there are 2 sets of 3 user inputs. That means, worst case scenario, we might have to write 6 if-else blocks, which will get unwieldy pretty quick. The second challenge is doing the actual conversion. I've gone ahead and looked up the conversion math for 3 temperature conversions: Fahrenheit to Celsius, Celsius to Kelvin, and Kelvin to Fahrenheit. As you can see, while this isn't difficult math, it's certainly unwieldy, and our programs are going to look pretty crazy if we start copying and pasting formula like this all over the place. I should also note that With these three conversions, we can make any of the possible conversions this program will be asked to do, because these three conversions create a circle of conversion where we can get from any type to any other type by possibly passing through one of the interim equations. With that all said and done, let's just jump right into writing our program. The first thing we need to do is set up some control flow. As I mentioned before, there's 6 possible cases, and it might be tempting to just set up 6 if statements for each possible pairing of input and output types. That would be a little unwieldy though, and so I have a slightly different plan. Instead of handling a different case for each possible pairing of types, the first thing I'm going to do is convert whatever value our user has given us for the initial temperature value to a Celsius value. Then after I've done that, we'll convert that Celsius value to whatever type the user was originally looking for. This has the advantage of letting us deal with the 2 pieces of user input in complete isolation. It makes our program more modular because we start and finish one task before we begin the next one. So to do this initial conversion, where we take whatever the user has given us as input and convert it to a Celsius value, I'm going to utilize a switch statement. We'll be switching across the input type character variable, which tells us what type of temperature, Fahrenheit, Celsius, or Kelvin, our user has given us. Inside the switch statement, we'll be manipulating the input value, in which is stored the value of that temperature. So I guess we're going to need separate cases for each of the possible or valid input types. That is capital F for Fahrenheit, C for Celsius, K for Kelvin, and we should probably also handle a default case. Let's start off by writing that default case. We'll use system.exit, and we'll exit with code 1, which is technically an error code. System.exit basically quits our program. It tells it to stop executing, and it passes to the operating system or whatever's up in the hierarchy this code here. In our case, our program will just stop. So that's because in this default case, we only expect to enter it if the user has failed to enter F, C, or K, which are our valid inputs. Now, let's go ahead and handle each of these input types. We're going to use Celsius as our first convert to in all cases. So if our user has inputted a Celsius value, we can just go ahead and break out of this case because the value of input value is already a-okay with us. Now, what if the user has given us a Fahrenheit value? Well, let's scroll up to the top and we'll see that we have the explicit conversion from Fahrenheit values to Celsius. We can take this block of code, which I've made pretty Java friendly, and let's just change the value of this input variable to the conversion statement run on its value. So we'll replace this T placeholder with input variable. And that will properly store in this variable the Celsius equivalent of our original Fahrenheit value. We can do something similar for the Kelvin case. However, we don't have an explicit conversion from Kelvin to Celsius, but we do know how to convert Kelvin to Fahrenheit and then how to convert Fahrenheit to Celsius. So
we can get away with doing something like this, converting our Kelvin value to a Fahrenheit value, surrounding that in some parentheses, and then doing our Fahrenheit to Celsius conversion on that. Now, this is technically a functional line of code. If we run our program and enter a Kelvin input case, this will properly convert the Kelvin value to a Celsius value. But let me say that if I'm a programmer and I'm at work and I run across a line of code like this, especially a line of code like this without any comments explaining it, I am not going to be very happy. There are a whole lot of magic numbers in here. That's numbers or really information in general that's not in any way self-explanatory. Sure, we as the original programmer, at least when we write it, remember that our goal here is to convert a Kelvin value to a Celsius value, but that's really not understandable for anyone else going through this program who doesn't really have time to sit down and look through the entire thing. So, is there a better way to do this? Yes, there definitely is. Let's return to our Fahrenheit input case. This line of code is a little better than our Kelvin case simply because it contains fewer numbers, but it's still not programmer friendly by any sense of the word. So, what if in our initial implementation of this program, we could provide communication that really looked a lot nicer to a programmer? What if we, instead of printing out that equation right there, put the equation somewhere else in our program? And instead called a Fahrenheit to Celsius function. We'll just type in F to C now to keep things short. That makes a lot more sense to someone looking at our program. We can do something very similar down here for the Kelvin case. We could call a Kelvin to Celsius function if we wanted to, or if we don't even want to write that, we can call a Kelvin to Fahrenheit function on our input value, and then call this F2 Celsius function on top of that. That's what we did with all that math initially, conceptually, except that what we've done is abstracted away those numbers and put them somewhere else in our program. This is much more friendly to a programmer. And let's say we made a mistake in our math and another programmer wants to go through and check it. All they need to do is find these functions that we're about to write, and they can dive into all their dirty details there. So, of course, we do need to write these functions. When we create a new function, we're actually going to do it outside of the function or method that we're currently in. Currently, we're in our program's main method, which is a special method where the program begins its execution. So, to write our Fahrenheit to Celsius function, we're going to step out of that method and declare a brand new one. Essentially, we're teaching our program how to run a new program called F2C. For now, go ahead and use the public static keywords in front of your methods. These keywords are going to be very important once we really jump into the object-oriented nature of Java. But for now, we'll utilize them on all methods we declare. Your
standard Java method also has one more keyword before we actually give it a name. And that is the type of information this method is going to return. For example, we would like to be able to call F2C on our Kelvin to Fahrenheit function. When we do this, we're basically treating the result of our Kelvin to Fahrenheit function as a floating point variable of its own. This is a good sign that the return type we're looking for in these functions is float. What that means is when these little programs finish executing, they're going to spit out to our main method that called them a floating point value. After we name a function, we follow it with two parentheses in our function declaration, right here, that is. Between these parentheses, we're going to tell our program what information this function is going to require to run. We do that by basically creating some variables right here. We're going to want a variable that I'll just call initial val. Actually, let's call it fval because we're starting with the Fahrenheit value. And we also need to tell our program before each input variable what type of information that's going to be. That way people can't improperly call our function and pass in something like a string that wouldn't make any sense. So we're going to tell our function that in order to run, it needs to be called with a float piece of information given as input. In the functions that we wrote before they actually existed up here, you'll see that we did that. We provided input value, or the value of the temperature the user initially gave us, as input to these functions. Now, we need our F to C function, our Fahrenheit to Celsius function, to perform some computation on this fval variable right here, which will contain the user inputted temperature value. Since we're going from Fahrenheit to Celsius, we can just copy and paste this string in again and substitute f value for T. Now, it may be tempting for us to ask our function to perform this operation right here, to change the value of this variable. While we're certainly allowed to do that, it's not going to give us the result that we require. When our program hits line 27 and runs our F to C function, giving input value as its input variable, this variable is not actually going to drop down to our function's line of code. Rather, Java is simply going to copy the value of input value and store it in our new variable here. So changes we make to this f value variable will not map to our input value variable. Fortunately, we explicitly change the value of input value to be whatever this function we're writing now returns. Once we're ready to quit execution of a function, we can have it spit out any value that's equivalent to the value type that we told Java this function would return. We do that with the return keyword, followed by any statement that computes to, in our case, a floating point value. So when our F2C function run on input value returns, it will print out a floating point number equivalent to the Celsius value of our initial Fahrenheit value stored in input variable. Once we've written one of these functions, writing other similar functions becomes pretty easy. To write our Kelvin to Celsius function, we're simply going to do the same thing, but in this case, take our Kelvin to Fahrenheit function, but in this case we'll take our Kelvin to Fahrenheit conversion equation, change the name of our variable. We could call it fval if we wanted to, but kval is just more explanatory, and return that result. So that's the first half of our program, where we convert whatever the user has given us into a Celsius value. So far, this has been much more elegant than 6 if statements, but we have only written half of our program. Once we've done the Celsius conversion, we're going to want to use another switch statement, this time on output type, where the user has told us what temperature type they'd like to see the equivalent value of, or see the equivalent value in. I just noticed we missed a break statement there. And our cases are going to look very similar to our first half switch statement. However, here, instead of converting everything to Celsius, we're always going to be converting from Celsius. Once again, that means case C can simply break. In any instances where we've converted to Celsius and then no longer need to convert from Celsius, we're good to go. Now, our explicit case here is now the Celsius to Kelvin conversion. We know that formula, thanks to our nifty cheat sheet here, and we can build a function to do that pretty quick. So that function we'll call C to K. There's our variable name, and there's the logic. Once we've declared our C to K function, we can call it on input value here, since input value now stores the modified original input value, which will be a Celsius number, to convert to a Kelvin value. Similar to the way we doubled up to convert from Kelvin to Fahrenheit to Celsius when we were making everything Celsius, we can get a Fahrenheit output by getting a Kelvin value from our Celsius value input value, and then using Kelvin to Fahrenheit, the function, to convert that Kelvin value into a Fahrenheit one. And that's the second half of our program. Still only 2 real lines of code that might cause anyone to pause, and they're pretty self-explanatory. Yet, all of the logic and functionality of our program is still accessible to a curious programmer who wants to re-access them. We can finish up our program here by using println to spit out input value, which should now contain the proper conversion. Let's run this program and give some inputs and outputs to see how we did. So when we run our program, it asks what input type we're going to give it. Let's give it a Fahrenheit value. We would like to get a Celsius value. And let's see what the Celsius value of 32 degrees Fahrenheit is. And we get the output result of 0. 32 degrees Fahrenheit is 0 degrees Celsius, so that's a good sign. Let's try some more edge cases. If we attempt to convert Celsius to Celsius, we get the same value, which is what we would expect. And let's see what the Fahrenheit value of 1 degree Kelvin is. And good news, that's also the expected value there. So there you have it. We've employed functions to make an otherwise very complex and difficult to read program much more manageable. The program we've written here is somewhat complicated. It does some math and some multifunction statements. So if you weren't 100% with us the first time through, I encourage you to go back and check what tripped you up. There's also other ways to approach this problem, and if you had a stroke of inspiration, I encourage you to explore it. Thanks for watching, and I'll see you next time. Hi, in this video I'd like to take a deeper look into Java methods and also learn some really valuable things about how programming languages think about and manipulate information. To help us do this, I'd like to run an experiment of sorts. And to start that experiment off, I've written us a really basic Java program. At the core of this Java program is the method magic, which is user-defined right down here. When we come across a new Java method, there's 3 real things we should notice about it. First, we should ask, what are its input values? In the case of our method magic, this method expects only a single integer as input. Then we probably want to ask, what does this method return? In our case, method is marked to return void. Void methods don't actually return any values at all. They simply execute their code and then finish. You'll notice that when we reference magic in our main portion of our program, we don't attempt to store its return value in any location. That is, of course, because there would be no return value to store. And then the third thing to notice about our method, of course, is what does it do? For our method magic, we simply take the value that we've gotten as input and increase that value by 10. What I'd like to ask you to do right now is to take a minute and just look at this program and try and figure out exactly what the program's output will be when we reach this print line statement. The challenging question here is, what happens to the value of variable x when we run this line of code here and call our magic method? Does the variable x remain unaffected by passing it as a value to the magic method? Or does the variable x get modified by this line of code in the magic method so that instead of printing out 5, we print out the value 15? To answer this question, we simply have to run our program. And if we do that, we see that we get the value of 5, letting us know that running the magic method did not modify the value of the variable x within the context of our main method. In fact, we'll get the same output if we never run the magic method at all. So what does this tell us? This gives us a very important insight into how Java handles method inputs. To fully understand what's going on here, we need to take a deeper look into how Java variables operate. In front of us is a representation of the information stored by our variable x. That is the variable in the main method of our Java program. You'll notice that this variable has 3 core components, and let's go through them quickly. On the left-hand side, I put this variable's name, which is the keyword that we use to reference it within scope, and a memory location. Our variables point to a memory location, and in this memory location, we store the variable's value. Name and memory location we can think of as being very static. They're not really going to change for this individual variable identifier throughout the course of our program's execution. However, we can freely, and often do, change the value stored in the variable's referenced memory location. So why is this important? Well, over the course of our program, we're going to have to translate the information stored in our variable x to the information stored in the variable input that our magic method attempted to make use of. If we take a good look at how variables are set up, we quickly see that there's two possible ways to go about doing this. First, we can simply create a brand new variable named input with its own unique memory location, and then simply place as the value in that memory location the same value that we found in the memory location referenced by x. If, when we pass the variable x to a method, this is the technique that Java uses to create the variable input, we can say that Java has passed our variable x by value, because only the value is preserved across the creation of the new variable. Another option would be for us to create a brand new variable input, but instead of simply copying the value from the variable x to the variable input, we could cause input to reference the same memory location as x does. This would be called passing the variable x by reference. In this case, because both x and input would share a memory location where they stored their value, modifying the value of the variable input would also modify the value of the variable x. So, given what we've just learned about Java variables, and taking into account that executing the magic method on line 7 does not modify the value of the variable x, we can correctly conclude that Java chooses to pass variables to its methods by value rather than by reference. However, that's not really the end of the story. Or rather, this fact has implications that might not be immediately apparent to us. Were we to rewrite our program so that our magic method took character input or Boolean input or really any other primitive type, we would see the same behavior that we've been seeing already. We're modifying the value of this input variable within the scope of the magic method does not modify the value of the variable x within the scope of the main method. However, things are not always so simple. To see this, let's create a brand new method. And in its declaration, we'll have it be the same as our existing magic method, but instead of taking a single integer as input, we'll provide it as input an integer array. Remember that our array will be named as a single variable. So all we need to do to let Java know that we'd like to pass an array to the function is inform it that the variable being given is an array of a certain type. You'll also notice that we now have two methods by the name of magic within our program. This is called method overloading, and it's perfectly legitimate to do as long as Java has a way of telling the methods apart. In this case, Java can tell the methods apart because both methods are going to be given different objects as input. One of our magic methods will execute if the input given to the magic call is a single integer. And our new magic method will execute if the input given to the method is an array of integers. Now, let's write a quick for loop so that our new magic method will increment the value of every integer contained within our input array by 10. This is extremely similar to the magic method we wrote originally, except that instead of operating on a single integer, it's going to operate on any number of them. However, something that may appear weird is going to happen when we modify our main method to utilize this new implementation of the magic method. In order to make this happen, we need to make a few quick modifications to our program. Let's change our variable x from an integer to an integer array so that our program will know to utilize the newly written magic method, which runs when we give an integer array as input. We'll also need to modify our print line statement to make use of arrays.toString so that we display the value stored in the array x properly. And we'll import java.util so that Java knows about the arrays library. Now, it's time to ask ourselves another question. This question being, when we run the magic function on an integer array, will we see the same results we saw when we ran the magic function on a single integer value, a primitive type? To answer this question, all we need to do is run our program. And we'll very quickly see that the output, or the final values stored in the array x, are not the same values that we assigned to the array x initially. This lets us know that our magic method is indeed modifying these values. So this is kind of weird. Why would our magic method operate differently depending on if we gave it a single primitive type as input or if we gave it an array of primitive types as input? To answer this question, let's take a look at the variable x when it's declared to be an array of integers as opposed to just a single integer as we had it before. X as an array of integers as opposed to a single primitive type still gets a name and memory location to identify it and a place where it can live. But its value field looks drastically different than it did before. When x was just an integer, we could get away with simply storing an explicit integer value in x's value field. But as an array, x needs to be able to reference a number of different values. That's what makes it a data structure. To make this happen, arrays, and really every other element more complicated than a primitive, points to a location in memory as opposed to a single explicit value. For arrays, all we need to do is point to the 0 index of the array in memory. Then, by following from that index, we can store a number of different values that our variable x knows how to access. So why is this important? Well, let's take a look at what happens when we pass x by value into a method. As we know, when we pass a variable by value, we're telling Java to create a new variable in the context of the method that's going to have its own unique name and memory location. But this new variable, in our case input, takes the value from the old variable as its own. When we were working with primitive types, these values were completely independent. But now, input and x both have the values of the same location in memory. So, while modifying input's value would not change the value of x, modifying the location of memory that input points to does still change that location of memory when x looks at it as well. Are you still with us? If so, congratulations. That's some complicated stuff we just went over. As you become a more experienced programmer, you'll begin to internalize concepts like this, and you won't have to really think about them explicitly when you're writing day-to-day code. For now, though, there's some logic shortcuts we can use to keep from getting too tripped up. Within the context of a method, if we reference an input variable explicitly and then modify that variable, we're going to be modifying only the variable within the context of the function, as we did in our first magic method. But if we have to take an additional step to access the value that we're modifying, as we have to do when we're declaring an indice of an array, then we're probably modifying via a location of memory, or by reference. In this instance, we will potentially affect the variable that provided the value for our function variable. Remember, though, that arrays are not magically by reference. If our magic function that took an array simply attempted to set the value of our integer array to a brand new set of integer values with an all new starting memory location, we would see that we are no longer modifying the value of x when we run this function on it. This is because the creation of a new integer array caused us to explicitly change the value of input. After this line of code, input and x no longer share a value anymore. Thank you very much for watching, and I hope you learned something. Welcome. I'm pretty excited about this video. Here, we're going to take the first real steps of learning object-oriented programming in Java. So I guess the first question to ask is, what is object-oriented programming? Well, on a high level, object-oriented programming is the creation of objects, discrete code and logic entities that, while unique and separate from each other, can have complicated relationships. When we're writing object-oriented code, we begin to deal with and think about the code as though it was a collection of physical pieces or objects. To show you the power of object-oriented programming, let's take a look at the program in front of us. Java is, by its very nature, an object-oriented language. So, if we've been learning Java, we've at the very least been using objects without realizing it. The program in front of us is a very basic input-output program, the kind we've probably already written if we've been learning Java. In this program, we make use of a scanner object that we call reader. And you'll notice that we utilize reader on two lines. One line where we declare and initialize the reader, and another line in which we call the reader's next function to acquire some user input. The important thing I'd like you to notice about the relationship between these two lines of code is that when we declare reader, we provide it with some additional information besides simply the command to create a new scanner. We give it a stream to associate itself with. This is interesting because later, when we utilize reader's next function, we don't have to retell it what stream it should be reading from. Instead, that information is automatically stored and recalled by the reader object. This is the beauty of object-oriented programming, that the entities or objects we create can be constructed in such a way that not only do they know what to do with the information given them and provide us additional functionality, but also that they know exactly what information to ask us for to perform their later tasks. Let's pause quickly to make sure we have some terminology straight. This line of code here, the command new scanner and then some arguments, that command tells Java to create a new object, a new scanner object for use in our program. This object has a location in memory in which it lives, and that location is referenced by the variable reader. It would be possible for us to create multiple variables that all point towards the same scanner object. However, in the context of this simple program, reader is our only entry point to that object's location in memory. So we can often get away with referring to an object like this simply by its variable name. Lastly, different objects operate in different manners. It would be possible for us to create multiple scanner objects. They would not have the same location in memory, but they would share similar functionality. The piece of code and logic that declares what functionality an object has and how that functionality operates is called the object's class. In this case, we're creating an object of the scanner class and pointing to it with the variable reader. Now this is all well and good, and we can create a whole lot of programs simply using the default standard libraries that Java provides to us. But to really open doors for ourselves, we're going to need the ability to create custom classes of our own. So let's do that. Let's jump in and create one. Now, we could create our new class within the file we're already working in, but class declaration code is a little different and logically discrete from something like this executed main method, where the lines are executed one after another in order. Rather, the class we're going to create is going to serve more as a reference for lines of code like this. Generally, when we're working in an object-oriented language, a high-level object-oriented language like Java, we're simply going to put each and every new class we create in its own separate file. To create a new Java file for our class, we can just go over here, choose New Java Class, and then we'll just be prompted to give it a name. For this video, we're going to create a class to provide and store some basic information about a person. So we'll call it the person class, which creates person objects. When we press finish, NetBeans is pretty handy and sets up some really basic lines of code for us. It declares this class to be in our local package, which means that when we reference it from our main method, we won't have to import this class like we have to do with the standard library ones. And then NetBeans is kind enough to create our class declaration for us. This is simply a line of code that lets the Java compiler know that we're about to declare a new class. For now, we'll ignore the public keyword, but know that it's pretty necessary here. And then the class keyword, self-explanatorily, lets us know that we're about to declare a class, and then just like everything we create and need to reference at a future date, we give the class a name or a unique keyword. And now it's time to write the code to set up our person class. Remember that what we're doing here is teaching future pieces of our program how to create person objects or instances of the person class. So the code we write here is going to look very different from what we would write in a method that simply executes the lines from start to finish. The information we place within a class declaration is going to fall into one of two real categories. The first category is us telling Java what information a person should be able to store. And the second category is us teaching Java what functionality a person object should expose. Let's start with the first bit. Let's tell Java what information we'd like to store in persons. Telling Java what information to store is a lot like declaring variables in any other piece of code. Here we've given the person class two member variables. These are pieces of information that we can access in any person object. Just about everything we declare in a class declaration needs to be given a protection level. When we become more advanced Java users, we'll begin to use different protection levels. But for now, we're simply going to declare everything to be public. So, as we set it up here, every person object has a first name and a last name. Remember, these member variables are unique to each instance of a person object, so different persons do not necessarily share first and last names. To make things a little more interesting, let's also give people a birthday. We'll need to import java.util for this because we're going to use another class, the calendar class. Calendars are basically points in times or dates with a whole lot of functionality wrapped around them. The cool thing is that calendar is a class of its own. So we're placing a class within our person class. Well, strings are class too, but Java treats them a little special. Now, let's head back to our main method and see what it looks like to create a brand new person. So for now, we'll leave this line of code so we can kind of use it as a template. We'd like to create a new instance of our person class, or create a new person object. To do that, we're first going to tell Java what type of object we'd like to create. Because we've declared the person class within the package that we're using, Java will understand the person keyword now. And now we need to give a name to the variable that we will assign our new person to. We'll just call him John. Now, creating a new person is as simple as creating a new scanner. We use the new keyword to let Java know that we're creating something brand new that doesn't exist yet. And we say, create a person. This line of code will cause the person pointed to by the variable John, who we'll just think of as the person John, to come into being. Now, John already has some basic functionality just by the fact that we've declared some member variables for the person class. So even our rudimentary declaration of the person class has given John some member variables that we can work with. For example, John has a first name that we can access as a variable with the dot operator. And we can go ahead and assign a value to that variable. And we can do the same thing with John's last name. And also, of course, his birthday. Now, I mentioned that birthday was going to be a little different from first name and last name when we got to this point. While strings are technically classes in Java, Java also gives them the special privilege of being able to be assigned to an explicit value, or a string explicit. Calendars, of course, don't have this unique special privilege. So we're going to need to create a new calendar object to place within our object John. Now, calendars are one of those classes that we can assign instances of, but when we want to create a brand new one, we need to create something more specific that is also a calendar. So for this instance, we'll use a Gregorian calendar. And then let's give John a birthday. We'll have him be born in 1988, January 5th. And then to see that everything is being assigned as expected, let's simply print out John's first name and John's last name. Oops. There we go. And when we run that program, we see John Doe not really properly formatted, but printed to the screen as expected. We've successfully stored information in our object, John. If we wanted to, we could create a brand new person, Jane, who could have a first name and last name and birthday all of her own. her member variables being completely separate from John's. And if we run this program, we see that those variables are indeed unique. Now, let's get rid of Jane, and we'll just remove this for now. And let's go back to our person class and provide people with some more functionality. So the beauty of object-oriented Java is that we're already beginning to think about instances of our person class as physical objects. This makes anticipating what questions will be asked of them much easier. For example, when I meet someone new, I'm either going to want to know their first name or their full name in most cases. So wouldn't it be nice if our person stored a string full name that people could just ask of it, rather than having to individually acquire their first and their last name? Now, of course, simply adding another member variable like this is unwieldy, because the people creating a new instance of person would need to set this full name. Also, if the person's first name or last name or full name were to ever change, their full name and first name and last name might not match up properly. But what if instead of a member variable, we provide a member method? When we create methods within the context of a class, we have access to the class's member variables. We can modify them if we want, or if we're doing something like we're doing now, we can simply utilize their values, in this case to return this person's dynamically constructed full name. There's another question that I anticipate this simplified person being asked, and that is, how old are you? This will be a lot like the method we just wrote, with one exception. In order to know how old this person is, this person will need to be told what today's date is, because that's not information that this person already stores. To do this, we'll ask people to pass that information in when they call this method. And we'll simply return the difference between today's year and the birthday year of this person. Now, the syntax for getting a year from a calendar is a little wonky, but I think we should be able to follow it. We simply use this get method, which has a number of uses, and then we need to tell the method exactly what we'd like to get from it. And what we'd like to get is a calendar year. So let's make sure to save this file and jump over to our main method and make use of one of these new methods that we've just added to person instances. So we've set up John. He has a birthday. Let's ask John how old he is, right in our print line statement here. To do this, we're simply going to call John's age method, and we'll create a new calendar to pass in. And I think the new Gregorian calendar will be by default set to the current date and time. And if we run that program, we see that John is 25 years old. And since I'm recording this video in 2013, that looks all right to me. So there you have it. That's our basic introduction to object-oriented Java. Object-oriented programming allows us to explain to the computer and also ourselves very, very complicated systems. And there's a lot more for us to learn about object-oriented programming in terms of how objects fit together and the kinds of relationships they can have, and what we can do with objects to make our programs easier and easier to write. But it's all going to boil down to the basics that we just learned. Thanks for watching. Welcome. In this video, we're going to learn about a very special member we can assign to our custom classes, the constructor. To start off, let's take a look at the code in front of us. This program creates an instance of our custom class person and immediately assigns some values to person's member variables, first name, last name, and birthday. Then we utilize some of person's member functions to print out some information about the values we've just assigned. The thing is, while this is a decent program that we've just written, it's easy to see someone making a mistake writing even this simple program. For example, what if I had forgotten or simply didn't realize that birthday was one of person's member variables? If I didn't assign a birthday to a person right away and then attempted to use the .age member method, our program would crash when it attempted to access that birthday variable that had not been set to anything. This is a very reasonable mistake for a programmer to make, both in terms of not knowing that they should set this member variable to a value, and also in assuming that this member variable would have a value, because what person doesn't have a birthday? Fortunately, there's a system in place where we can demand information from the user before we allow them to even create an instance of our object. So let's jump into the code that declares the person class and set this class up so that a person can only be created if it's given all of the necessary information right from the start. To do this, we're going to use a constructor. A constructor declaration looks a lot like a normal method declaration, except for one thing. Where a normal method would have a return value, even the value null if it wasn't designed to return anything, constructors don't even have that. Also, the name of the constructor method is the same name that we've assigned to our class. However, just like normal methods, we can give constructors input. To start off, let's assume that all persons have a first name and a last name and a birthday. Otherwise, they simply shouldn't exist. When we create a new instance of the person class, and the person class has a constructor defined, we will always create an instance of the class using the person constructor. If we save this update to our person class declaration and then go back to the main method of our program, we'll see that we're going to get a compiler error if we run this code now. That's because we modified the person class to demand that our newly created constructor be used. That constructor takes three inputs, a string, and a calendar. So, instead of modifying person's member variables in these three lines of code, what we're going to want to do is pass these three variables as arguments to our constructor method. Now, as far as the main method in our program is concerned, the syntax of our program is once again valid. Of course, if we run this program, we're going to run into some troubles, because while we pass these arguments to the person constructor, we haven't yet done anything with them. Now, it needs to be the job of our person constructor here, as opposed to the main method in our Java program, to translate these parameters into the values of the person's member variables. So let's do that. Let's change our person's first name, or rather set its value, to be the variable passed in to this function. Now, this is technically correct syntax that we have here. It will do what we want it to do, but it should give us some pause. The command first name equals first name is really, really weird, and it's pretty ambiguous if you go about reading it. After all, which first name are we talking about in each of these instances? Are we talking about person.firstname, the member variable of this class, or are we talking about the first name that was passed in as arguments to the constructor method? To disambiguate this, we can do a couple of things. First off, we could simply change the name we assign to our method arguments to be something that's not identical to the local member name. But sometimes it just makes sense to explicitly ask for a first name. It can be a lot easier for the people who are going to use the constructor. When we need to explicitly tell our program then that we're using one of person's member variables, we should path to it properly. The this keyword will allow us to access the class that we're currently operating in, or rather its object instance when the program runs. So this .firstName will always reference the member variable as opposed to the one passed in as an argument. Now that we have that syntax down, we can very quickly assign the argument values to the values of our member variables. Now, when we save this file and go back to our main method and run our program, we'll get the original output, showing us that our person constructor has properly mapped these input values to the values stored in our person object. So this is pretty cool. We've modified our person class so that it's much more difficult for a programmer to make an obvious mistake and call these methods when they're bound to fail. A programmer could still get in trouble if they did something along the lines of modifying one of the member variables after our person has been created. However, there's a system in place for us to protect our classes, if we choose to, from having their members modified without going through proper protocol. Let's say that we'd like to change our person class so that the only time these members are ever changed is once, at the very beginning when the constructor calls. If you'll remember, we've been tagging all of the members of our classes with this public protection tag. Something that's tagged public is basically viewable whenever by any piece of our program that has access to its container. However, we can use a couple of other different protection tags. If we were to tag all of our member variables private, then they would only be viewable within the context of their current class. So we could still use these member variables in our person constructor and our full name and age methods. But this line of code here, where we attempt to access last name outside of the actual class declaration, would now be invalid. We can tag members private and then instead create public methods to modify their values when appropriate, and by doing so protect our objects from ever being given invalid values. Now, let's go back to talking about constructors before we wrap up here. As with normal methods, we can override constructors and have more than one option for our programmer to choose from. For example, let's say that sometimes in our program we want to create new people who have just been born. In this instance, it might make a lot of sense for us to construct a person by simply giving the first and last name to our constructor and then having the birthday be a new Gregorian calendar, which will default to today's date. If we wanted to use that constructor instead in our program, we'd simply call the constructor with only 2 string arguments, which would map to the newly created constructor that we've declared here. And when we run this program, we'll see that John Doe is now 0 years old because his birth date has been set to the current date and time. Lastly, we can give someone the option of utilizing one of our constructors or simply creating an instance of the class without doing anything, simply by declaring a constructor that is empty. Then that syntax looks just like the creation of John we had earlier. Generally, we don't want to do this though. What we want to do if we have an empty or a default constructor is to assign default values to our member variables so that at the very least we're still not breaking our program. So it might make a lot of sense for our default constructor to assign empty strings and maybe today's date to our first, last name, and birthday fields. Then, even if our programmer doesn't properly assign values to John's fields after creating them, there's still going to be some valid values to those fields to protect us from actually throwing an error when we run our program. So that's the skinny on constructors, another tool that help us protect and make more robust the code we've already written. Welcome back. In this video, we're going to explore the topic of inheritance in Java. Inheritance is a very important object-oriented concept that comes into play when we begin to declare classes that share attributes and functionality but are not exactly the same. Rather than starting with a high-level description, I think this is going to go best if we really jump right into a problem. So, to get us started, I've created a really basic Java program. In this program, we declare 2 Java classes, the book class and the poem class. Books and poems all store a number of attributes. For example, our book can have a title, an author, a publisher, and a genre. It takes all these attributes as constructor input and provides a single public method, the print method, that we can use in our main program to print out information about any books we create. The poem does something very similar. It has a couple attributes, a print method, and we set its attributes through its constructor. I whipped up a really quick main function to utilize the book and poem classes. This function creates a new book and poem and then prints them out like we see here. This program works just fine, but it's much more complicated than it needs to be. If we take a look at our book and poem classes side by side and just look at their member variables, we're going to immediately see that both book and poem share 2 member variables, title and author. And the actions they take with these member variables, namely printing them out to the screen, are performed and achieved in very similar manners. This is a good sign that book and poem should be inheriting from one common class. This becomes extra easy for us to see when we think about books and poems as the physical objects that they represent. We can make the statement that books and poems are both forms of literature. Once we've come to this conclusion that books and poems share certain fundamental attributes, the attributes of all literature, we can start to break these classes down into component parts. Our book, for example, our book class, for example, has two real pieces. It has a title and an author, which are attributes we associate with all literature. And then it has a publisher and a genre, which may not be unique only to books, but which we don't necessarily consider all pieces of literature to have. So how can we exploit this knowledge? Well, we can build our book and poem classes so that they share on a fundamental level their nature as pieces of literature. But to make this happen, we're first going to have to teach our program what a piece of literature is. To do this, we'll create a brand new class, and we'll call it literature. And we'll assign to this class the attributes that the pieces of literature we've so far declared share. In our case, books and poems are already declared pieces, share titles and authors. And that makes some logical sense to us to make the statement that all pieces of literature will have both a title and an author. From here, we'll flesh out our literature class like we would any other. We'll give it a constructor, and in this case, our constructor will take two variables, a title and an author, and assign them to the fields, much like we did with our poem and book classes. And while we're at it, let's give literature a similar print method to the one we assigned to books and poems. In fact, to save time, I'm just going to copy and paste the title and author lines from our book class. Now, if we wanted to, we could go to our main method and declare an object of the literature class. But that's not the point. That's not the reason that we've created this literature class. Rather, our goal is to make use of this literature class as a base from which to build on to declare more specific types of literature, like poems or books. To make use of our literature class, let's see how it applies to the existing poem class. Our literature class contains declarations and all of the functionality needed to manage a piece of literature's title and author. If we let Java know that there is an inheritance relationship between poems and literature, we should be able to remove all real references from title and author from this poem class. Let's first talk about this declaration of the poem class that we've modified. When we say that one class extends another, we're saying that there is a relationship between them, such that I can logically make the statement a poem is a literature. In more Java terms, we're saying that the subclass poem extends or inherits from the superclass literature. This means that when we create a poem object, it will have all of the members and functionality of the class which it extends. In our case, two of these members are title and author. The literature class declares these members and does a good job managing them throughout the class's functionality. So, we can remove these members from our poem class and we'll still be able to access them within poem's methods, because poem simply inherits their declaration from literature.
We do need to make a slight modification to get this poem class working as intended, though. When we construct an object of a class that inherits from another, by default, the constructor of the subclass is going to begin by calling the constructor of the superclass. This confuses Java as we've had it set up right now because the poem constructor takes 3 variables as input, but the literature constructor is only expecting 2. To solve this, we should explicitly call the literature constructor within our poem constructor. When we're in a subclass, we can call the methods of our superclass using the super keyword. So in this case, we're going to begin our poem constructor by simply calling the super constructor or the literature constructor and passing it the attributes that we'd like it to know about. We can do something very similar in our print method. Because our literature class, our superclass, knows how to print out a title and author already, there's no reason for the poem class to implement this functionality. Here, we'll get the same behavior from our print method if we begin it by calling super.print instead of the original explicit printing lines. Now when the poem's print method runs, it will begin by calling the superclass's print method and then finally printing out the poem's style, which is not shared across all pieces of literature. While our poem constructor and literature constructor had different names and even took different styles of input, our 2 public void print methods shared between poem and literature are exactly the same. We'll talk about this a little more later, but for now we should know that we've made use of a technique called overriding right here. When we declare that a subclass has a method that's identical to one of its superclass methods, we've overridden the superclass method. When we do this, it's a good idea to use the Java override indicator. This is an indicator to future coders and some more arcane elements of our compiling suite that this particular method is hiding a method beneath it. When we actually run our code, Java gives preferences to the lowest or subclassed version of a method. So let's see if we've declared our poem and literature relationship successfully. Let's go back to the main method of our program and see if the poem portion of this program executes as it did before. When we run this program, we get the exact same output as we did previously, which is a great sign that we've set up our poem to inherit from literature in a logical manner. Now we can jump really quickly to our book class. And we're going to do, if I can stop making typing errors, the same thing very quickly. We're going to declare that book extends the literature class, and now we'll remove references from title and author in our book class because now the literature class, the superclass, will take care of this. As with the poem class, we're going to need to explicitly call literature's constructor and pass title and author in. And then we can make use of our superclass's print method to simplify printing of our book. And once again, let's jump back to our main method and run it to make sure that we've done this successfully. There we go, the Lord of the Rings output just as we saw it before. Style-wise, this change is really great.
By adding the literature class and then subclassing it to create books and poems, we've made our book and poem classes much more bite-sized and easier for a programmer to go through and figure out what's going on. But this change is not purely stylistic. By declaring this relationship between books, poems, and literature, where books and poems inherit from the literature class, we've given ourselves actual functionality that we didn't have before. Let's take a look at that in action. If we go back to our main method, let's pretend that rather than dealing with a single book and a single poem, we're dealing with a vast network and that we need to store them in some sort of data structure. With our original implementation, this would be a real challenge. There's not a easily accessible data structure that will happily store both books and poems. We'd probably have to use two data structures or break the strong typing that is the whole point of Java. However, with our new implementation, where books and poems both inherit from literature, we can store them in the same data structure. That's because inheritance is a relationship, meaning that we can, once we've inherited from something, make claims like a book is a literature and a poem is a literature. If that's true, then in an array of literature objects should be able to store both books and poems within it. And the fact that we get no compile errors when we build this project is a really good sign that we're doing something legal. Now, for demonstration's sake, let's flesh out our array here to contain a number of books and poems. And we'll modify our main method to print out directly from the array. Now, when we utilize our subclasses as though they were objects of their superclass, we do have to be aware that we're now referencing them as objects of that superclass. For example, when we go through and acquire an element from our literature array, even if that element is a book, we still can't attempt to access things like its genre field, even if that field was public. That's because the literature class, which we're now using this object as, does not have a genre member variable. But what we can do is call methods from our superclass that are overridden by the subclasses. So when we call the literature class's print method within our loop here, Java is going to prioritize the print methods of our subclasses. That means that when we run this program, we're still going to get the specially formatted output that we have attributed to books and poems, not the simplified version that we stored in our literature class. In fact, you may sometimes see methods that exist only to be overloaded by subclasses. These methods don't do anything, and we can tag them with the abstract keyword. Of course, if a class
has methods declared abstract, it's probably a good sign that an instance of that class should never be explicitly created. If our literature's print method is abstract, we should never be declaring objects that are only a literature. We should only be using objects that are one of literature's subclasses. If we're going to go down this route, we should declare literature to be an abstract class as well. If we do this, of course, we'd have to get rid of the references to literature's super method. So I'm going to undo those changes for now. Let's take a look at a minor mistake we made when building this program initially. Initially, when creating our literature class, we declared that title and author were public member variables. As we hopefully know, we generally don't want to declare member variables public if we don't have a good reason to. It doesn't make a lot of sense for a piece of literature to change its author after it's already been declared. So really, author and title should be private member variables that are set in literature's constructor and then whose values should never change. Unfortunately, if we make this change to our literature class, we're going to limit our functionality in our poem and book classes. Let's say, for example, that we wanted to modify the print function of our poem class so that it didn't have to explicitly call the print function of the literature class. Like maybe we wanted to start it by telling us that we're declaring a poem here. Unfortunately, because we've made title and author private to the literature class, the poem class, even though it is a subclass of literature, cannot access these member variables in its explicit code. This is kind of annoying, and it seems like there should be some sort of protection setting in between private and public, where it's private for everyone except for subclasses of the class. And in fact, there is. This is the protected protection setting. And if we declare that member variables are protected, they're private, not accessible by anyone except the class and its subclasses. Just to reassure ourselves that everything we've been doing here is legitimate, let's run our program again and make sure the output looks good, which it does. After this, we should have a pretty good handle on inheritance. You can develop a lot of systems that really mimic their real-world counterparts, and you can write very elegant and functional code using inheritance and small classes that don't do a lot of complicated things in and of themselves. Thanks for watching. Welcome back. In today's video, I'd like to take a quick look at an important idea that relates to inheritance in Java. To wrap our heads around what we're going to talk about, I think it's best for us to start in an existing project and system. So let's take a look at the code we have in front of us. Here's the main method of our program, and what it does is it creates a list of objects. These objects are either of type book or poem, but we've placed them into a list of literature objects, leading us to believe that the book and poem classes must inherit from or extend the literature class. Then once we've built that array, we simply iterate through it using a for loop and call this print method on each object. At this point in time, we're dealing with the objects as literature objects, not the books or poems that they are at the lowest level. This leads us to believe that the literature class itself must implement a print method. And if we jump into the class, we'll see that indeed that is true. However, if we run our program, we quickly see that books and poems execute their print method slightly differently, displaying different information for each of them. This is explained when we look in the book and poem classes, which do indeed extend literature. But each of these classes override literature's print method to provide their own functionality. This is all well and good and is a pretty elegant solution here. But there's an interesting case that we should take a look at and discuss. Because literature is itself a class, it's perfectly valid for us to declare a new literature object, just as we could a book or a poem. If I remember correctly, literature's constructor expects first a title for the piece of literature, and then an author. And once we've created a new instance of the literature class, we could put that instance into our list of literatures, just like we've been doing with instances of the book and poem class. When we do that and run our program, we'll see literature's print method executed, and the new literature object we created will display alongside our list of books and poems. So what's the problem here? Well, depending on the true nature of the software we're trying to design, this may or may not make a lot of sense. Let's say we're doing this as part of a library system. Providing someone with just this information, that something called Java was written by some guy called Zach, without telling them if it's a book or a poem or any other information that we've decided to associate with specific types of literature, may simply be not useful at all and something that should just never be done. If this is the case, Java provides us a system to create classes that we can use for inheritance purposes, but will never be able to be legally instantiated on their own, as we've done here. If we want to mark a class to be of that type, we're going to call it a abstract class. And in the class's declaration, we simply use the abstract keyword. Once we've marked a class as abstract, it's no longer a legal operation to instantiate this class. On its face value, this is a really simple thing. And primarily a protect our code from ourselves and other programmers kind of deal. But that's not entirely true. Or rather, it is true, but it's not the only purpose of declaring a class to be abstract. Once we've told Java that we can never create an instance of just a literature, only of classes which use literature as their superclass, we're no longer as restricted when setting up the literature class. Because we've declared literature to be an abstract class, we, and Java as well, know that literature will never be instantiated on its own, only when it is a superclass of a class being instantiated. When this is the case, we can get away with not having portions of this class that most Java classes have to have. For example, we don't need to actually declare a constructor for literature. If literature was a standard Java class, Java would not be okay with this, because if we did try to instantiate literature, it would have no idea what to do. There would be no constructor to call. But because literature is abstract, we can be confident that literature's subclasses will have constructors of their own.
Of course, if we do make this change, we're going to have to get rid of the references to the literature constructor in our subclasses. So there's definitely a trade-off associated with this change. It requires more code in our subclasses to have less code in our literature superclass. In this particular instance, this trade-off probably isn't worth it because we're duplicating code between our book and poem constructors. But if the constructors for literature subclasses could be reasonably assumed to do very, very different things, not declaring a common base constructor would make a lot of sense. So, in summary, when we architect our program or a larger solution so that we have classes that make a lot of sense for architecture purposes, but should never be created all on their own, we want to declare those classes abstract. Sometimes we'll really know we've come across a class like this when certain common class functionalities, like having a constructor, just don't make sense for this class. As always, thanks for watching. Once we've achieved a level of confidence with the basics of Java, that being both the Java syntax and the basic object-oriented concepts that Java was built around, it's time for us to take a look at Java's API, the class libraries immediately and easily accessible to us when we're writing Java programs. We want to do this for a couple of reasons. First, we're going to be using these class libraries to speed up our programming and to make use of the work of programmers who have written really great stuff. If something's put in the Java API, for the most part, we can be reasonably sure that this is the best and most efficient way Java has to complete the individual task this class library is designed to do. Taking a look at the Java class libraries, or the class libraries of any programming language really, is also a great way to see how the programming language is designed to use and what optimal coding in that language should look and feel like. Today, we're going to take a look at Java's calendar class. When writing Java code, we generally use the calendar class to refer to a specific moment in time. The calendar class is actually a relatively new addition to the Java API. Previously, we generally used a class called date to perform similar functionality. If you end up working on older Java code or are writing Java code that's dealing with a SQL or MySQL database, you'll probably end up using the Java date class at least occasionally. If this happens, don't panic. Consult the Java documentation and you'll discover that there's some really great functions for swapping between calendar and date objects. To see the power of Java's calendar class, let's jump into a Java program and instantiate one. I've gone ahead and created a new program and imported java.util because that's where the calendar class lives. And I'm going to declare a new calendar object, and I'm going to call it now because our first goal is to assign the value of this calendar object to be the current moment in time. While we haven't actually looked it up in the documentation, this seems like a reasonable starting or default date for a calendar instance. So let's set up our program so that we can print out the information contained in our now object. And let's just assign the value of now to be the default value of a calendar object and see what that gives us. To do that, I suppose we're going to need to create a new calendar. Perhaps surprisingly, this basic program actually fails when we attempt to compile it. Here's our error on line 7. The error is calendar is abstract and cannot be instantiated. If you'll recall, abstract classes are those that are designed purely to be subclassed, and we can never declare an instance of an abstract class all by itself. So, what good is Java's calendar class if we can never create one? Of course, that's not a fair question, because we definitely can create calendar objects. They just have to be a specific type of calendar. We're almost always going to make use of the Gregorian calendar. But let's take a step back and assume, perhaps rightfully so, that we didn't know what calendar options were available to us. This is one of the times when working with an IDE, an integrated development environment like NetBeans here, can be really amazing. Normally at this point in time, we'd have to take a trip to the Java documentation to see exactly what subclasses of calendar are available for us to instantiate. But because our IDE knows some metadata about the packages that we've already imported, we can ask our IDE what it thinks might be a possible solution for this place in our code. If you're working in NetBeans, you can get these kind of suggestions very often by checking some of the code completion blocks. But to keep code completion from popping up all the time and making these videos pretty much unwatchable, I'm going to make use of a NetBeans shortcut on occasion. This shortcut by default is the key combination Control Space, which will prompt a code completion pop-up window for the current location of our cursor. Code completion in NetBeans is excellent. NetBeans has given us 3 possible suggestions. Here's the abstract calendar class, which we already know we don't want to use because we can't actually instantiate an abstract class. But Buddhist calendar and Gregorian calendar certainly look like subclasses of calendar. If we select Gregorian calendar, we'll see in fact that it is a subclass of calendar. So let's go ahead and attempt to create a brand new Gregorian calendar at its default settings and values. If we run this Java program, we do in fact get some output. That means 1, our syntax is okay because we compiled successfully. And 2, we can see what values Java puts in a brand new calendar object. One of the great things about Java is how extensive and demanding it is that new objects implement the toString method used by println. This means that most Java standard library objects are capable of printing themselves out in some sort of human-readable format when we ask them to. Our new calendar printed out here isn't exactly easy to read, but we can go through it and see that values have been assigned to many of its fields, and we can also see what the fields that a calendar has actually are. But let's see about getting just one piece of information from the calendar. Let's see if it is actually set to the value of today. Let's check the day, month, and year. To keep things simple, we'll just do this on 3 separate lines. And now we're going to need to get those fields from our calendar object. If our calendar represents a specific moment in time, it should have fields for day, month, and year, right? Well, if we open up our autocomplete, we can take a look at all the fields and methods available to us exposed by our calendar object. We're not actually going to find an easily accessible day, month, and year field. And this might start to disenfranchise us with calendar. But in fact, we're just not going enough levels deep. Calendar exposes the get method. And get allows us to acquire these fields that describe the specific calendar instance or moment in time. It's a function that takes an integer as a parameter. To some of us, this might look a little confusing at first. Why would we provide get with an integer to tell it what calendar field we're looking for? This integer is actually an enumerator, which we'll think about for now as a static string exposed by the calendar class itself. If we type in the calendar class name, like we wanted to get a static member variable and then go back to autocomplete, we see a list of options that we can utilize in this instance. Some of these options don't make a lot of sense. We have to remember that autocomplete is just telling us what calendar exposes. It's not giving us the solution because it has no idea what we're trying to do. For example, we wouldn't want to use our calendar instance to get its value of May. That wouldn't make any sense. But we can use our calendar instance to get the current month. Similarly, what we really want is day of the month and the current year. If I run this program, we get the output 7/20/2013. I'm recording this video on August 20th, 2013. So this is actually a little confusing because August is the 8th month of the year. Fortunately, there's a reasonable explanation for this. Unlike day of the year and year, which makes sense to store as integer variables, most implementations of calendar and calendar-like classes in most programming languages, not just Java, choose to store months as an array because in addition to a numeric value, each month also has a corresponding string, its name. Since arrays are zero indexed, our month appears, if we forget about this, to be 1 month lower than it should be. Our printline function should probably look like month plus 1. And that, you'll have to trust me on this, is today's date. So calendar has a whole lot of methods associated with it. In addition to just setting a calendar to the current point of time and reading from it with our get function, we can set calendar to points in time using the set function. We can add or subtract using negative values to point in time using the add function. And we can see if points in time are before or after other points of time using the before and after functions. If you're like me though, you'd like to know a little bit about how this calendar is really operating. Is it storing the month, day, and seconds of time in separate fields, or is there one big number that contains all of this information? If we spend some time and take a look at the methods available to us in the calendar implementation, we'll find these two methods, set time in milliseconds and its sister method, get time in milliseconds. The fact that these methods are specially set aside is a really great window, an opportunity for us to see how the calendar class really thinks. Let's begin our exploration by calling this get time in milliseconds function and printing out its output. We get a really large integer number, which is presumably the time in milliseconds since some particular point in time. If we were to do the math on this though, we would discover that this point in time is not actually the year 0. Rather, it's a time much closer than that. This point in time is referred to by the calendar class as the epoch. And it's the point in time which we start counting from when we store a time in Java in terms of how many milliseconds it's been since the epoch. Now, we could whip out our calculator and, through a pretty painstaking process, figure out exactly what this point in time was. Or we could do it in our native Java environment with a lot less pain. Let's simply change the value of our now, originally set to the default or current moment in time, to be the time when milliseconds is set to 0. We'll do this with set time in milliseconds and provide 0. When we run our program again, we get the same output fields. Here's our confirmation that milliseconds has been set to 0. And now our calendar moment in time is December 31st, 1969. So once we start adding days to our object, we'll be counting from January 1st, 1970. This point in time is referred to by the Java calendar as the epoch. So, why is this a really interesting thing for us to know? It means that we can convert our calendars to these millisecond values and then add, subtract, and I guess multiply and divide them as integer values. This allows us to use all sorts of operations on them in the native format of mathematics. Before we go, I'd like to show you one more thing, because it's a bit of syntax that you may not be familiar with and may not immediately recognize when you come across it. If you'll recall at the beginning of this video, calendar is an abstract class. We can only instantiate specific types of calendars. However, oftentimes we won't specify exactly what type of calendar we're looking for. We'll ask the calendar class to decide for ourselves. As we saw with our enums here, the calendar class, in addition to having object level methods, does provide some static methods that we use just by referencing the calendar type name. One of these methods is calendar.getInstance, which will create for us the best fit calendar that Java can figure out. In this case, it's going to be that same Gregorian calendar that we were creating already, and we'll see the earlier output. Thanks so much for watching. In this video, we're going to take an in-depth look at Java strings. Working with strings in Java can be a little confusing at first because they really are a special case. Strings have associated with them this concept of a string literal, a sequence of characters between double quotation marks that we can just put right into our Java programs, and Java understands it, just like it would understand an integer number or a single character. But unlike integers and characters and floats, Java doesn't have a primitive keyword associated with this string literal. About the closest we could get, if we wanted to, is character array. But generally, Java likes us to associate string literals with the string class. The string class in Java is special. In some ways, it's just like any other class. It has methods, and as we can see in these two lines here, it has a constructor. But we can use operators on the string class that are normally only reserved for literals and primitives. For example, we can add S1 to this string literal right here and get a meaningful result. This is not normally an option when we're dealing with a Java object. Java's decision to use objects of the string class as either string literals or genuine objects interchangeably is really powerful. It gives us way more options when manipulating text than we would otherwise. But it does come with some trade-offs. It's very important that we understand when we're dealing with a string object if we're dealing with its string literal value or with the object itself, because we can get radically different behavior. This program I've set up here is designed to illustrate one of these instances. It's a pretty simple program. Let's step through it and attempt to anticipate its output. We start off by declaring and instantiating two string objects, S1 and S2. We use the string constructor, and we'll talk about why that's important here in a moment. And we simply pass in the same string literal value to each of these new objects. Then we ask our program to print out these values just so we can compare them visually. But then we ask our program the interesting question. We ask our program to compare using the double equals sign comparison operator, S1 and S2. Before I run this program, let's take a second and ask yourself, what do you think the result of this comparison is going to be? When I do run this program, we see that Java does not believe that the comparison of S1 and S2 returns true. We get the result false. Depending on how we as people were thinking about S1 and S2 at the time, this either makes sense or is confusing. If we were thinking of S1 and S2 as string literals being compared with this operator, it would be very confusing to us why we didn't get the result true, because these string literals are the same. However, if we were thinking of S1 and S2 as the objects that they are, the result of false makes a lot more sense. Because what we're asking Java is, are these two objects the same? And they're clearly not, because they're both the result of creating two different new objects. This is why we like to use the equals method when we can in Java. Almost every object implements a dot equals method. And the dot equals method should be written for every object so that it logically compares the value of these objects. If we compare our strings using the dot equals methods, we're now comparing the string literal values they contain, and we get the result true, as opposed to the result false we got when we were trying to see if they were actually the same objects stored in the same location of memory. So what powers does this string implementation give us? Well, we know that we can add or concatenate strings together because we can manipulate them as literals. In addition to this literal manipulation, we can also make use of all the functionality provided by the string class itself. We can go to the docs to see what functionality is available for us, or we can always just check code quick completion. I should probably point out here that we can even use the string class functionalities on string literals. So a lot of these methods are pretty self-explanatory, to lowercase, to uppercase. But just to make sure we're all on the same page, let's make use of one of them. Let's use replace. Replace takes two arguments, and these arguments can either be single characters or a character sequence, of which a string qualifies. And This method simply replaces all instance of the first string or character with the second string or character. And so when we run our program, we see that we've modified its output. Most of these methods simply modify the value being returned. We can see that our program still finds that S1 equals S2 at this last line of code, showing us that the value of S1 hasn't been modified by our call to the replace method. Replace method has simply returned the modified value for our printline function to utilize. But perhaps the most interesting of the string class's methods is actually one of its static methods. This is string.format. To show you the power of string.format, I'd like to create a brand new functional class for our project. We'll call it custom printer. And so that you can see what we're doing when we set this class up, let's pre-write the code we're going to use in our main method. The idea behind the custom printer class is that we can create a new custom printer, and it will have a constructor that takes a string as input. And this input string will format or wrap around any strings that we use the custom printer to print out to our console. And we'll implement system.out.println within the custom printer. So we can just call printer.println when we want to utilize it. When we're formatting a string in Java, we're going to use some special syntax. Within our string, we can preface the characters F or D or S most commonly with a % sign. And Java understands these in terms of the string.format function, which we're about to use, to be areas in our format string where we're going to insert other information. This format string that we're going to use here will wrap any string output we create with these nice little caret brackets. This is more complicated than simply appending and prepending to a string. And we could certainly create an implementation that allowed us to add multiple pieces to our formatted strings. And we'll just get rid of that for right now because that's not going to end up working. And let's go to our custom printer implementation. We know that we're going to need a constructor which takes a format string as input. And then we're probably going to need to store this format string. So let's just have our constructor take the provided format string and store it for later use. We also declared a println function, which presumably is going to be a void function and is just going to utilize system.out.println to print something to the screen. What that something is, though, is going to be a little complicated. We need to take our given format string and replace that %s with the provided input to our println function. We do this with the awesome string.format static function, which takes a format string and then the replacing arguments as parameters. If our format string had multiple blocks to format, for example, multiple insert strings, we could provide multiple fields in string.format. It's a function that can take any number of inputs. But to keep everything simple and moving along, we're simply going to assume that our format string only has one input instance. And then once we successfully formatted this string, we'll simply print it out to the screen as we would earlier. When we run this program, we see that all our output gets properly wrapped with these caret brackets. A custom printer like this is the basis, once it's extended, of course, to take more varied input and be much more dynamic than this quick thing we created here, is the basis for anything like a logging system or a terminal system, where you see the same pieces of information wrapped around messages. We could use a custom printer like this, for example, to place dates and times after any message we send to the user, properly formatted so that they're not just tacked on at the end, but have proper spacing between them and stuff like that. I hope you all learned something about strings. The way Java handles them is really powerful, but as with most powerful things in programming, you need to understand them on a basic level before you can be sure that they're not going to come back and bite you. See you next time. Sometimes our code is going to fail. It might be our fault for making a programming error, or it might be an end user using our system in a way we didn't anticipate. Sometimes it'll even be hardware failures. And a lot of errors can't really be attributed to any one single source. But they are going to happen. And the way that our program handles the error case is often just as, if not even more important, than how it handles ideal use cases. In this video, we're going to take a look at Java exceptions. By using Java exceptions, we can detect, catch, and in some cases recover from errors that occur within our program. While we go through exceptions, there's something really important to keep in mind. Exceptions are called exceptions because they exist to handle exceptional cases. Things that we either couldn't handle or couldn't anticipate when originally writing our code. Exceptions modify the control flow of our program, but we should never use them for anything other than catching and handling or passing exceptions. If we attempt to use them to implement logic, we'll make a program that quickly becomes very confusing for us and is immediately very confusing for any other programmer who attempts to understand it. To help us explore Java exceptions, I've set up a basic program that can fail for us to play with. It's an eternal loop that does two real things. First, it takes input from the user using our scanners.next float function, and then it prints that input back out to the user. If we properly give this program floating point values as input, it will run, theoretically, forever. But if we make a mistake and give this program a string as input, the next float function will not know what to do with that, and an exception will occur. When this happens, we get all this red text in our console. This red text is actually going to the system.err for system.error stream. Let's take a look at this text. It has two important sections. The first part of this text, the bit that's not tabbed in, is the identifier for this exception. It lets us know that an exception has been thrown and the basic where, and then it tells us what type of exception has occurred. You'll notice that this exception is found in the java.util path. This looks very similar to if we were importing something into our code or directly pathing to an external library. That's because this exception that's been thrown is actually a Java object. And this piece of the exception method is letting us know exactly what type of object it is. The second bit of this exception test is what we call a stack trace. And it's basically the pieces of our program that Java has jumped through. At the very bottom of our stack trace is where the exception was originally thrown. That's scanner.java, line 909. That's not our code. That's the code written for scanner.java, presumably where the next float method lives, or code that the next float method calls. Stack traces are the layers of code. So once the input mismatch exception occurred, Java just began jumping up layers of code, or bracketed areas, until it eventually reached the top layer where our code resides. That's exception.java, the file we're in right now, and it's the top of the stack trace. Exception.java, line 11, is the last place where Java was able to handle or throw up this exception. Once line 11 was reached and the exception was still propagating upwards, there was nothing else to handle it because this is the top of our program. So the exception wound up getting printed to our system.err stream and our program terminated with result 1, which is a failure case. This is great for debugging purposes. We know right where to go to figure out what went wrong in our program. Exceptions.java, line 11. But if we were creating a program that we were looking to release for some reasonable purpose, we generally don't want our program to crash whenever a minor error occurs, especially an input error like this that's perfectly reasonable for a user to make from time to time. So let's explore how we can handle exceptions. When Java is told to throw an exception, it stops executing the current code block and begins jumping up levels until the exception is handled. That's how we got from deep within the scanner.java class to exceptions.java line 11, the piece in our code where, as far as we're concerned, the exception occurred. If our code was being executed by another block of code, because we do not handle this exception, instead of printing out to system.err right here, we'd simply throw the exception up another level, and they'd see exception.java line 11 in their stack trace. But sometimes it doesn't make sense to keep throwing an exception. Sometimes we want to handle the exception case because we know what to do with it, or because, as in the case we're dealing with right now, there's a lot nicer ways to inform the user of what went wrong than this stack trace and exception name. Additionally, if we handle this exception here, there's no reason that we can't resume our while loop as though nothing had happened. One failed case of this while loop isn't necessarily reason to terminate our program. If we're going to handle exception cases, we're going to make use of the try-catch code blocks. In any block of code where we think an exception might be thrown, and we'd like to handle the exception, we're going to wrap that line of code in a try block. For the most part, this doesn't affect how this code is executed unless an exception occurs within the try block. If an exception is thrown within the try block, instead of propagating that exception upward to the next level, the code within the following catch block is going to be immediately executed. Catch blocks require a little more information before they can execute, though. They need to know what exactly they're catching. We can catch all exceptions by simply catching anything of the exception class, but that may not be a fair thing to do. There's a lot of different schools of thought on exception handling, but generally people will agree that you should only catch and handle exceptions that you, to some degree, expected might occur. In this case, we happen to know that an input mismatch exception is thrown if we give invalid information through user input. Because we're going to be printing out a message when this exception occurs that specifically tells the user, you passed invalid input, we certainly don't want to be catching any exceptions that are not input mismatch exceptions. So now, if we actually, let's put in the new line to this code block 2. And now if we run our program with our try catch block in place, and let's quickly test that it works in the good use case as it did before. And now if we cause that input mismatch exception to be thrown by providing string input, we should see our catch block execute, and we should get the you passed invalid input response. Now, as you can see, we do get that response, but unfortunately, we're getting that response over and over and over again. We've inadvertently introduced an even worse bug. Now, instead of throwing an exception and crashing, our program just enters an infinite loop. Here's why. Our scanner object is a stream reader. That means there's a buffer of input that it picks to read from. In the normal use case, our user is adding floating point numbers to that input, and we pick one out, and then we execute and go back and wait for another. However, when a string is found in there, this line of code throws an exception, which is fine because we catch it with our catch block. Our catch block prints out the new line of text, and we go back to the beginning of the while loop. But that bad string in our reader's buffer is still there. So when we catch our exception, we need to clear out that stream. Fortunately, this is something we can handle. Once we've caught and handled our exception, let's clear our stream reader by simply grabbing its next line and doing nothing with that information. That will flush this line from the reader. If we run our program now, we'll see that it handles and recovers from a failed input where we give it a string, which is pretty cool. Let's go over a couple more things we can do with exceptions though. For one, clearing out our reader at the end of an exception case makes a lot of sense. But it might make even more sense to clear out our reader at the end of any attempted case. After all, we're entering this while loop with the assumption that there's no new line in the reader. When we'd like to always execute a case, no matter if we did or did not succeed in our try block, we can follow our catch block with the finally block. The finally block executes no matter what, whether an exception was or was not caught. And its reason for existing is so that you can put cleanup code in your system. An example of cleanup code is clearing out our reader here so that there's nothing there to confuse ourselves later or other programmers. Exceptions are more than a simple object that gets thrown. They can contain a lot of really important information. As we saw earlier, exceptions can contain a stack trace. Let's quickly modify our program so that while it still gives user-friendly you passed invalid input
information, we also print out the stack trace so that a programmer can debug our program. Generally, when we're writing finished code that a user is going to utilize, we never want a case where they're going to see something as in-depth as a stack trace. It's confusing for most computer users and can be a security risk in some instances. But as a feature in a debug mode or for developers, detailed exceptions like this can be very useful. The exception class exposes a method print stack trace, which requires as input a stream. We've been using system.out for all of our output so far, so we'll provide the print stack trace method with system.out as its stream. Now when we run our program and give it a bad string, we get our initial friendly exception text code, but we still have the stack trace so we can see exactly where our errors are coming from. As I mentioned earlier, exception handling is an extremely deep topic in modern software development. But at the end of this video, you should have a firm hand on the basics, and when you come across exceptions in code or when you're writing your own code and feel that you need exception handling, you should be well prepared. See you next time. In this video, we're going to learn some very important things about how Java has chosen to implement object-oriented programming. We're going to be exploring the object class itself. To get us started, I've written a really basic program. It utilizes a custom class called myClass and creates two instances of this class, object1 and object2. We then call a void my method on each of these objects, which simply prints out the value that we've given them to contain. Then the program compares these objects. We first compare with this comparison operator that checks to see if these are actually the same object. We know that this will not be true because we can see that the objects were instantiated completely independently of each other. They share a class, but they're two different instances of the myClass class. We then compare these objects using the .equals method, which we'll be talking about a lot in this video. When we run this program, we see that the objects are found not to be the same, which is what we would expect. We also see that the objects are found not to be equal, even though the objects were both created under the same parameters and had the exact same things done to them from their creation to this point in time. So, what does it mean when objects are found not to be equal by the .equals method? The first question we should ask ourselves is, where does this .equals method come from, or where is it implemented? If we go to the myClass class, we don't actually find a .equals method, which is pretty weird because myClass is not declared to be inheriting from any superclass, but .equals is called directly on a myClass instance. In reality, myClass, as with all Java classes, does inherit from a superclass. At the very top of every class inheritance tree, even though it's not explicitly declared in our code, is the object class. If we head to the Java docs and look up the object class, we find this page and this definition. Class object is the root of the class hierarchy. Every class has object as a superclass. All objects, even arrays, implement the methods of this class. And then if we scroll down, we get this short but very important list of methods. Because all Java objects inherit from the object class, we can safely assume that any Java object we're dealing with implements each of the methods here. Among these methods is the equals method that we were just talking about and trying to figure out where it came from. This makes it very clear to us that our my class is inheriting the .equals method from its object superclass. The definition of the equals method on the object level is very vague. It says indicates whether some other object is equal to this one. This vagueness to some degree leaves it up to us as programmers to determine on a class-by-class basis what equality really means. Let's say we come to the decision, the reasonable decision, that object 1 and object 2 should be determined equal to each other if the values they contain are identical. If we make this decision, then our current implementation of our program is not quite correct, because it's currently telling us that here object 1 and object 2 are not the same. In order to change this, we're going to need to override the equals method in my class. Overriding an object class method is no more difficult than overriding the method for any other superclass. We simply declare an identical method, and this more specific method will be used when appropriate, when we're dealing with a myClass object. It's important for us to notice that the equals method does not take a myClass object as input. It takes any object as input. So before we can go ahead and compare this object's value with the value of our current myClass object, we need to protect ourselves and make sure that the object given as input is actually a myClass object. To do this, let's check some bad cases in which we would simply go ahead and return false without even comparing the inner values of these objects. If we've been given an object that hasn't actually been instantiated, or a pointer, or a null pointer, we simply want to return false because our instantiated myClass object is not equivalent to nothing at all. The more difficult question is this object we've been given an instance of myClass? Let's check the opposite of that. Let's check to see if object is not an instance of myClass. The instance of keyword lets us see what classes an object has within its repertoire. And if this statement does not evaluate to true, we simply want to return false because we'd be comparing a myClass object with a class that is not a myClass object. Once we've made it through these hoops successfully, it's safe for us to assume that we can cast this object to a myClass object. And now we can simply compare the value fields they contain and return that value. For this implementation to work, we will have to make value public. And then let's save this and jump back into our main method. When we run this method, we now see that object 1 and object 2 are found to be equal to each other. The object class declares a number of methods. In addition to equals, some important methods are hashcode and toString. We're not going to implement hashcode in this video because it requires us to do a little more math than is really wieldy. But I would very much recommend you check out how hashcode works by going to the documentation and exploring it. For now, let's just know that an object's hashcode method should return an integer value that describes this object. In all instances,
If two objects are found to be equal through the equals method, their hash code functions should also return the same integer value. If two objects are not equals as far as the equals method is concerned, their hash code functions should return different values. At this point in time, we should be familiar with the toString method. This is also a method in the object class, meaning that we can call toString on any single object. But in our custom objects, until we've overridden toString, it's probably not going to return meaningful human readable information. As you learn Java, I highly recommend implementing equals and toString even on the small little test classes you write while learning. It's a great habit to get into and keeps you thinking about object-oriented programming in the same way that Java does. When we create finalized software projects where we have public classes that other programmers may someday be using, we should be very careful that all of our classes properly implement these methods in an understandable manner, because Java programmers will expect to be able to utilize these methods to manipulate and understand our classes. Thanks for watching. Welcome back. In this video, I'd like to take a very quick look at the primitive classes available to us in Java. In Java, we often say that strings are special because they have a literal interpretation identified by these double quotation marks, but we still interact with them primarily through the string class, rather than a string primitive type, which is not actually available to us. Your standard Java primitive, however, we generally interact with through its primitive typing. However, we do have available to us for every primitive type a corresponding primitive class. These are the integer, character, float classes, etc. For the most part, the explicit uses of these classes, where we create an instance of them and then call methods on that instance, are not very useful unless we're overriding them to create a class of our own. The options given to us by an instance of the character class, the methods it exposes, are primarily conversion methods, which would happen automatically or that we could simply cast to. Compare to is sometimes useful though. Compare to returns an integer value, 0 if the given other character is equivalent, and less than 0 or greater than 0, depending on which side of the integer conversion scale the two characters fall in relation to each other. However, we may very oftentimes find ourselves using the static methods of these primitive classes to manipulate or get information from instances of the primitive types. For example, if I want to know if our character C is lowercase, I can certainly convert it to an integer value, check an ASCII table, and then see if that integer value falls between the range of lowercase characters. But that's a whole lot of work. And the character primitive class provides a static function for me, is lowercase, which will tell me if a character is lowercase or not. That's really the gist of primitive functions. We can interact with the other literal types and their primitive types in the same manner that we would interact with strings by using a class, if we so choose. When we don't need the functionality of a primitive class, we should continue using primitive types. The syntax highlighting and kind of universal look across languages makes them much more friendly for programmers to work with. Thanks for watching. Welcome back. This should be an exciting video. Today we're going to take a look at writing to files using Java. The program in front of us declares a mathematical sequence, or the first 50 numbers of the mathematical sequence, in which each number is the sum of the two previous numbers. When we run this program, we see these 50 numbers printed out to our system.out stream, and we can view them in our console. But when we close this console for good, these numbers are lost. Our goal for today is to get these numbers printing out to a file rather than the system.out stream. In a file, they could be preserved. To help us with this task, we're going to make use of the java.io library, I/O standing for input and output. And we're going to utilize a class that lives in this library, the file writer. Let's declare a new file writer. And for reasons that will become apparent a little later on, let's have this file writer be explicitly set to null. Once we've done that, we can go ahead and instantiate it. In order to write to a file, we're going to need to know two important things. First, of course, we're going to need to know what to write to the file. And second, our file writer is going to have to know what file it should write to. When we're using a file writer, we associate it with a specific file. So we pass into its constructor the name of the file we would like it to write to. Our file writer is capable of creating a file if none exists. So we should just pick a name that ends with .txt so that our operating system knows we're creating a text file. Even though we've called file writer's constructor with valid arguments, NetBeans is still letting us know that we'll get a compiler error in this code. It's telling us there's an unreported exception, an I/O exception, that can be thrown here. Many exceptions in Java are marked as handled exceptions. These are exceptions that a function explicitly states it may throw. File writer is a function that explicitly states that it can throw an I/O exception. So, as far as Java is concerned, it is an error for our code not to explicitly handle this possible exception. To handle this, of course, we're simply going to wrap the portions of our code where we use our file writer with a try catch block. That catches I/O exceptions. If we do catch an I/O exception, it's probably a good time to print out to the error stream. And we'll just give a helpful message. And then our program will be finished terminating, or finished running, and will terminate because it's reached the end of the main method. With that exception caught, our instantiation of file writer is now valid and legal. So let's put it to use. We no longer need our program to print out to our console, so I'll comment out this line of code. And we're going to do the same logical thing with our file writer. File writer doesn't have a print line statement, but it does have the write method. Each time our for each loop executes, we'd like to write this number to our file. Unfortunately, the write method doesn't know how to take a long as input. It can take a string and it can take an integer. So let's use the static string class method value of to acquire the value of our long number to print out to our file. So we should have all the pieces of a successful program here. We have
declared and instantiated our file writer, giving it a file name, and then we've looped through our Fibonacci sequence of numbers and told our file writer to write each of these numbers to out.txt. The question is, though, where is out.txt? We haven't given the file writer a full system path, just the name of a file. We know that the file writer is capable of creating this file if it does not exist, but where in our system's directories will this file writer choose to create that file? To answer this question, we need to know where NetBeans is creating the .jar file for our compiled program. To find this out, we can open the console window and build our program. Here, NetBeans will tell us where it's creating all its files. For me, it's a folder writing to files. And if we navigate to that folder, we'll see our project files. One of these files is dist for distributable. And this is where our jar file is compiled to. Jar files are as close as we're going to get to an executable with raw Java code. Because Java code must be interpreted by the Java virtual machine, we can't actually create Java executables. But in most operating systems where Java is installed, we can run a jar file by simply double-clicking it, like a executable could be run. We can also tell the Java virtual machine to boot up and run a jar file using the Java command line -jar command, followed of course by the name of the file we would like it to execute. When I submitted that command, the Java virtual machine interpreted and executed our writing to files.jar program. It looks like it worked because a new file was created in this directory. This is the working directory, and until we move it, it's where our jar file is executing from, or where the command that executed the jar file is executing from. So that's where our file writer chose to create out.txt. Unfortunately, when we open up out.txt, there's nothing for us to see, leading us to believe that our file writing probably didn't work. So what went wrong? Well, there's an important piece to using a file writer that we failed to take into account. When our file writer is created, it opens a file. And whenever we open a file, we should make sure that in the end, we close it. This is pretty easy to do from a code standpoint. We simply call the close method on our file writer. Here's a familiar error message though. Out.close can also report an IO exception. We could put out.close within another try-catch block and handle this IO exception. But if our file cannot be closed, that's a sign that something is very seriously wrong. In this case, it might be appropriate for that exception to keep propagating upwards, and us to pass it on to a more robust piece of code, rather than our fairly contained writing to files program. This will happen by default if we don't handle this exception. But we do need to let Java know that this exception propagating upwards from our current code is a possibility. When we declare our main method, we can also let Java know what exception types might be thrown by this method. Here, we tell Java that under some circumstances, our main method may not execute perfectly and will instead throw an IO exception. Now, anyone who calls the main method of writing to files will need to handle this exception themselves. If we build our Java program and then execute it again,
we'll see that out.txt has been properly printed to. Unfortunately, we forgot to put new lines in our output, so there's no distinguishing spacing between the numbers. When we write, let's append to each number \r\n, a new line escape character syntax that's going to be visible to just about every operating system and environment. It's time again to build, run, and take a look at out.txt, which now is starting to look pretty useful. So that was our initial stated goal, to print this Fibonacci sequence out to a file. A few quick things before we're finished here though. Let's take a look at what happens if we run our program again, and then take a look at our output text file. The text file looks the same as it does before, which may or may not be expected. It seems like it's kind of a toss-up if FileWriter would clear this file and write brand new text, which is what it appears to have done, or if it would have put the text appended after the existing text in the file. By default, our FileWriter will clear a file before it writes to it anew. But we can toggle this behavior through a parameter in the FileWriter constructor. If we set its append behavior to be true, build our project, run our project, and take a look at out.txt, we'll see twice as much information as was there before. Our text is now appended at the end. Lastly, there's a lot of different writers available to us in Java. FileWriter is just one of them. I decided to show it to you here because it's pretty simple. It takes some text and it prints it to a file. Very often, however, you'll see FileWriter wrapped around by the buffered writer class. And the declaration of the buffered writer class will look like this, where a buffer writer is created and given a file writer as its input. The buffered writer is pretty cool because what it does is intelligently take all the commands you give it and attempt to write to a file in the most efficient way possible. This program we've just written here is, from our point of view, going to do the same thing as our existing program has been doing. However, in instances where we make many small writes, like this one, buffered writer can be significantly faster. Because, where appropriate, it will intelligently collect the right commands we give it and perform them in the proper blocks to maximize efficiency. For this reason, very often you'll see Java code that looks like this instead of the file writer being used in isolation. See you next time. A common task we'll need to perform as programmers is reading input from a file. In this video, we're going to take a quick look at how to acquire text input from files. Before we start though, a quick note. I've gone ahead and told Java that sometimes our main method is simply going to throw IO exceptions. Our file writer and file reader object here both can create a number of IO exceptions for a number of reasons, like if they can't connect to the files they're supposed to. When writing actual programs for actual applications, we always want to make sure to catch and handle our exceptions in a reasonable manner, only throwing them upwards if it's truly necessary. But we're just going to throw everything here because we're doing this to learn, and we don't want to be bogged down right now wrapping all of our code in try-catch blocks. So, about the code we already have. I've declared for us a file writer and a file reader object. File reader is a sister class to file writer. It's capable of, believe it or not, reading text input from files. And
It's constructed in a very similar manner. It expects to be given a file to be associated with it throughout its life when it's constructed. Rather than simply giving our file reader and writer paths to these files, I've chosen to create file objects. The Java file object is simply a reference to an existing file, and we tell that file what file it references when it's created. In this program, we're going to be using inputfile.txt, which contains some information. And we're going to be using outputfile.txt, which currently contains no information. Our goal is to move the information from input file to that output file. File writer and file reader both have methods that are going to be useful to us here. Our file writer has the write method, which we know can be used to put information into a file. Similarly, the file reader has the read method, which will allow us to acquire information from a file. If we simply call these methods in sequence and run our program, we'll see that information is actually taken from input file and put into our output file. Unfortunately, only one character appears in our output file, the first character of the input file text. It would appear that our file reader's read method only acquires the smallest acquirable piece of text information. That's not a problem for us though, because we are programmers. We can simply loop through using the in.read method to acquire all of the information available to us in that input file. However, we can make life a little easier on ourselves by also wrapping our file reader with a buffered reader class. Similar to the way we can wrap file writers with buffered writers, we can wrap file readers with a buffered reader. Which will allow us to collect varying lengths of input at any given time. Even more so than wrapping our file writers, it's almost always a good idea to wrap our file readers. The buffered reader also serves to protect the file reader from files that are too large for the file reader to hold in memory at one time. This doesn't happen very often, but when it does happen, it can be a pretty confusing bug. And because the buffered reader only looks at portions of the file at one time, it's protected from that instance. Our buffered reader is also going to let us use the next line method so that we can collect information from our input file on a line-by-line basis instead of a character-by-character basis. Either way though, our while loop is going to look pretty similar. The only real challenge here is that we need to know when to stop looking for information in our input file. To figure this out, we're actually going to put some functional code in the conditional portion of our while loop. We're going to assign a value to this new input string variable, and that value is going to be in.nextLine. The reason we want to do this assignment in the conditional portion of our while loop is so that we can then check what value was assigned to new input. Because if new input was assigned no value at all, it means that we've reached the end of our file. Oh, and the method is readLine, not nextLine. If new input does have a value, if the variable is not null, then we know that we've read in legitimate text from our file. An entire line of legitimate text, actually, because we're using the readLine method. If this is the case, we should add this new line of text to our input string. And
when we're finished executing our while loop, when new input is assigned the value null because there's nothing else for our reader to read, we should print out this string that we've been building. Now, because our buffered reader's readLine method specifically reads lines of text, it doesn't append the end line character at the end of them. So we'll have to do that on our own. So we've executed this program. Let's go to our directory and see what's been copied over to output file. And there we go. Input file and output file now have identical contents. That's really all there is to basic file reading in Java. A couple other things to note though. Just as we can wrap a file reader with a buffered reader, we can if we import java.util, wrap a buffered reader with a scanner. This would allow us to use the scanner class's methodologies to acquire only portions of the text we were reading that match certain patterns. It's also important to note that the file reader and its wrapping classes are only appropriate when we're reading text from a Java file. If we want to read binary information, we're going to use different classes. More on that when you learn about serializing objects in Java. Thanks for watching. Oftentimes, when we're dealing with information outside of our actual code, we're dealing with human-readable text that we've gotten from a file or are writing to a file or an input or an output stream. But sometimes human-readable text just isn't convenient, and we'd like to use information that's more computer-friendly. Through a process called serialization, we can take some Java objects and convert them to a binary stream that we can transfer across programs. This is not a human-friendly approach. As we'll see in this video, a serialized object looks like complete gibberish to us. But another Java program that knows about that object's class can recreate an object from that serialized information. Not all Java objects, however, can be serialized. In order for us to serialize an object, it needs to be marked as an object that can be serialized. And it needs to only contain members that themselves can be serialized. For some objects, those that depend on external references or those that simply haven't had all of their members marked as serializable, serialization is just not appropriate. The class in front of us, though, is a prime candidate for serialization. Its members are a number of strings and integers, both of which are classes that Java has marked as serializable. But in order for us to transform a char object into a binary representation, we need to let Java know that the char as well is serializable. We're going to need the IO library for this, and then we're going to let Java know that our char object implements serializable. This is telling Java, yes, in fact, all the elements of the char object can be converted to binary representations. We should never tell Java that an object implements serializable unless we've looked at the object and thought it out and determined that this is a safe assumption to make. So we've now marked char as a serializable class, but that is of course the easy part of this video. Our next goal is to make use of this new functionality, to create a char object, serialize it, print it out to a file, and then read it back. To do this, we're going to create two new Java classes. One to serialize our object and print it to a file, and another class to deserialize our object and read it from a file. In both of these classes, we're going to create main methods so that we can run our classes as separate Java programs. Let's begin in the serialize class. The first thing we're going to need is an object for us to serialize. So let's go ahead and instantiate a new char object. Char takes 4 strings and an integers for its variables. It takes a vehicle identification number, make, model, color, and then a year. So we'll give it a number, a make, a model, a color, and a year. Once we've created our car, it's time to open up a file and serialize that car for output. When we open up a file in Java, we're going to use some different managers depending on if we'd like to write to this file formatted text output or if we're just planning on writing raw binary information. Because serialized objects are binary information, we're going to use a file output stream to write this information. File output stream is created with a file name to associate itself with. Because we're writing raw binary information, it's not that important that we specify this as a text file. We can specify it to be really whatever we would like. Our operating system really isn't going to know what to do with this file if it tries to open it anyway. We're going to want to surround all of this information in a try-catch block, because whenever we're dealing with external files, exceptions can definitely be thrown. If we do catch an exception, let's just simply print an error message. And noticing we're having to add a lot of imports here, let's just import the entirety of the java.io library. Now, I think we're good to move along. We've created our file output stream. And this stream is pretty good, but we can wrap it with another stream that's more specialized for the act of serializing a Java object. This is the object output stream. And we can construct an object output stream by simply wrapping it around an existing file output stream. Once we've created this object output stream and associated it with a file, serializing our object and writing it to this file becomes extremely easy. We simply need to use the write object method and provide as the object to be written our char. Once we write this object to our file, we should be responsible and close our output stream. And now I think we're good to run our program and see what happens. We have multiple main methods in this Java project. So as far as NetBeans is concerned, when we run our program, we should make sure to right-click on the class whose main method we want to enter with and run that file specifically. When we run this program, we don't really get any meaningful output because we didn't ask for any. At least an error wasn't thrown. But when we head to our directory in which this project lives, we'll see a new file, serialized.dat. If we edit this file with Notepad, it looks pretty ridiculous. This is certainly not human readable format. But there are some words or fragments of words that we recognize. It certainly looks like the correct object was serialized. Let's now head to our other class and attempt to write a method that will pull this car out from that file that we've written its serialized information to. Once again, we're going to need a car object, but this time we're not going to initialize it with a constructor value. Rather, we're going to set its value to be the object we read back from our file. The syntax we're going to use in our deserializer is going to look very similar to the syntax we have used in our serialize class main method. So actually, I'm just going to copy this over so that we can see the mirrored similarities as we build our deserialize main method. Oh, you know what? Made kind of a irresponsible error in this serialize method. We closed our object output stream, but we did not also close the file output stream. Now, this isn't really a big deal because our program immediately opened these files, performed its functionality, and upon terminating, Java destroyed these objects, and the files knew that nothing else was pointing to them. So our operating system is aware that these files are closed and can now be freely written to. But in a program that continues for a long time or even indefinitely, not closing a file can have some very weird consequences. When we're nesting file input or output classes like we've done here, we're generally going to close our files in the reverse order that we accessed them. In this case, it wouldn't make sense for us to call outfile.close before out.close because our object output stream for a brief moment there would be referencing a file that it could no longer access because the inner file output stream had closed. With that out of the way, we've copied our code over, and now we're going to make some modifications to it. So instead of serializing our object to a file, we are now reading the serialized object from a file. So instead of a file output stream, we're going to use its sister class, file input stream. I guess I should probably import java.io again. We'll want to be referencing the same file name here. And let's intelligently name our variables. In a similar manner, we're going to wrap this file input stream with an object input stream instead of an object output stream, still referencing the same file. Of course, this time we have no interest in writing an object to this file. And that's good because our input stream does not have the permissions or the know-how to write to this file. What it can do, however, is read an object from the file. Read object doesn't take any parameters. It's simply going to read whatever object happens to be in that file. And when it reads that object, we want to assign that object to our char C. Of course, read object only knows it's going to acquire an object from the file. It has no idea what type of object that will be. One of the weaknesses of serialization is that we really are forced to take a leap of faith and cast this object to the expected type. Once we've done that, it's simply time to close our file readers in reverse order. And there's now another type of handled exception being thrown, the class not found exception, which is thrown if our read object method fails. So let's catch this exception. Class not found exception. And to keep things simple and moving, we'll just throw or print out an error message like we did with the previous exception. Now, we need a way to tell if our program worked or not. So, at the very end, let's attempt to print out our char's information using its custom toString function. NetBeans is letting us know that this variable might not be initialized at this point in time. Some programming languages will let us make this mistake, and our char might not have been initialized because this try block could have failed. To let NetBeans know that we're aware of this case, or rather to let Java know that we're aware of this case, we should initialize our char C. We can simply initialize it to the value null. Now, it's time for our moment of truth. Let's execute this main method. When we run our file, in our console, we get the output a 2000 green Nissan Altima with this PIN number. That's the same car that we declared in our other main method and serialized to the file. Clearly, we have been successful. Serialization of objects is one of the things that Java does really elegantly and really well. It's an extremely powerful tool that can make one of the most difficult and frustrating tasks of modern programming, transferring information between logically separate entities of code, much, much easier than it otherwise would be. Sometimes we'll write programs that are all about raw functionality, but very often we'll be writing programs who are going to be used by ourselves or other users who would like interacting with them to be a streamlined procedure. NetBeans, for example, is a powerful program that offers us a lot of functionality. And we access this functionality through a graphical user interface, these menus and buttons provided by NetBeans. In theory, NetBeans could have chosen to operate as simply a command line program. But in order to use NetBeans like that, we would have to memorize or look up a large library of specific commands for every action we wanted to take. A powerful and well-written application has a streamlined interface that guides us towards the important functionality and makes it easy for us to access. The Java Development Kit contains within it a Java extension library, the Swing library, which makes it very easy for us to wrap our own code in graphical user interfaces like NetBeans has. To start us off on this track today, we're simply going to write a program that will open up a new GUI window. At the heart of these Swing Java GUIs is the JFrame class. This will be, in our case right here, the actual window object that our operating system will handle and that we could move around our screen. And we can create a new JFrame just like we might create any other object. If we'd like, we can even pass some parameters to this JFrame's creation. If we just give it a string parameter, we'll be telling the JFrame what to present as its name. Once we've declared a JFrame, though, it's simply going to exist in Java's memory like any other object. It won't present itself to the user until we explicitly tell it to. This is simply a function call, though, to the setVisible function, and where we assign that value to true. Pretty easy, right? There's one more thing we should do before we make a JFrame visible, and that's to call this pack method. When we create more complicated frames, they may contain a lot of information, and in a GUI, much of this information takes up visible space. The pack method basically pre-builds the physical relationships between the objects in our frame and ensures that it doesn't behave oddly when it actually appears visible to the user. So this is a really simple program we've written so far. Only 3 lines of code and no real thought required on our part. When we run this program, it might at first appear that nothing has happened, but in fact, something has. In the top left-hand corner of my screen, a new window has appeared. And if I click on the right parts of this window, I can, in theory, drag it around, or we can just resize the window. This is a fully fledged window that our operating system can now handle us moving around, and it even supports dynamic resizing. You'll see that our header, which I've spelled wrong there, has also been appended to our window. There we go. That's fixed. So that's super basic. Let's see what else we can do with our existing JFrame. When our JFrame appeared, it was very small and hard to see. A program window of that minimum size is really never going to be useful to anyone. So let's see what powers frame gives us in terms of setting the window size. We're very often going to use the setPreferredSize method to apply a size to our JFrame. There is also a setSize method, but this method sometimes isn't going to give us exactly what we expect it to. Because our JFrame right now is set to be resizable, it's not appropriate for us to explicitly assign a size to it. Rather, we should instruct it that given no other input from the user, meaning resizing of the JFrame, the JFrame should be a certain size. We can store, manipulate, and create size information using the dimension class. To construct a new dimension, we can simply give a width and a height. So let's set our JFrame's preferred size, the size it would like to be until we stretch it at all, to be 400 by 400. Dimension lives in another library, so we'll have to import that library. And then we should be able to build and compile our project, and once again, open up our new GUI. So now we get a nice square GUI to start with. However, it's still pretty useless. There's nothing contained within this GUI. So before we end here, let's take a quick look at what it looks like from a programming standpoint to add elements to our GUI. Quite possibly the simplest element that we could put inside a JFrame is a JLabel. Labels are responsible for containing text. And instantiating them is extremely simple. We simply tell them what text they should contain. Of course, in more complicated programs and GUIs, this text can become dynamic and changing. But for now, let's just get some text to display. Simply declaring that we have a JLabel is not enough. We have not yet associated this label object in any way with our existing frame. Our frame, as you can probably tell by the vast array of methods and members it exposes, has a whole lot of components. And we need to know in which of these components to place our new JLabel. One of the components within our JFrame is the content pane. That's the area that we visibly see inside that window where things normally go in a program's GUI. So that seems like a reasonable place for us to add a new component. In this case, our label. Let's once again build our program, kill the old instance, and run our program. There we go. Now we have text in our GUI. We've successfully added an element to the content of our JFrame window. One thing that's kind of annoying is that our program has been continuing to run even after we close the associated GUI. That's a little silly. When I press this X on the NetBeans GUI, NetBeans closes itself and stops running as a process on my system. We can instruct our frame to terminate the associated process by using its setDefaultClose operation method. This method has return type void and takes an integer as a value. This integer is an enumerator, and there's lots of options available to us. All of these options are statically declared by the JFrame class. And the one we're probably looking for here is exitOnClose, which will exit our application when we close our window. Build, run, terminate, and there goes our process, not quietly running in the background anymore. That's our super basic introduction to GUIs in Java. Creating a GUI is complicated, exciting because it's visual and immediate, and also really powerful. One of the things that defines truly amazing software programs is their GUI and their user experience. Before we write this introduction off as done though, I'd like to show you something that's a bit heavy on the technical side, but is probably really good to see here. As our program stands right now, it's functional, but were we to extend it, we might eventually run into some very odd and very confusing issues. What we've done now flies in the face of the recommended practices when creating a new GUI. These recommended practices are in place to protect us from some very low-level issues that can occur when our programs become multi-threaded. What does that mean that our program is multi-threaded? Well, when we create our GUI, when we cause it to come into being, our program goes from performing a single task, simply executing the main method from start to finish, to performing multiple tasks, because now, in addition to executing this code here, it's also managing that new window we've created and any functionality performed by that window. To protect ourselves from the complexities of multi-threaded code, it's recommended that we create our new swing GUI by allowing one of the swing utilities to construct this GUI for us asynchronously. In order to make this happen, we're actually going to need to pull all the code we've written out of our main method and place it in one place where we can reference it from our main method, a new function. And we can just paste all of this code back in to our new function. Now, let's take a look at how Swing recommends we cause our GUI to come into being. As I said, Swing, the Swing package, provides us some functionality that will perform the vast amount of this work and thinking for us. The Swing Utilities class has a static invoke later method that will create our GUI when no other threads really need to be processing right now, or when all of the other thinking is done for a bit. This invoke later method expects us to pass a runnable object to it. So we're going to have to create for ourselves one of those. Runnable objects are those that can be converted into a thread of their own. They have a method that we're going to override that's called run. And the Swing Utilities invoke later method will call our runnables run method when appropriate. When that occurs, all we want it to do is to call our make GUI method and begin executing that code that we've just tested out will create a GUI. Oh, and we'll add our override notation to be good Java programmers and pass our new runnable object to the Swing Utilities invoke later method. And we've forgotten a semicolon somewhere. I've forgotten a semicolon somewhere. There we go. Run. Now, the functionality is exactly the same. And what we've done could be arguably overkill for a program this small. But it's really good for us to take a look at what we should expect to see in a larger software project where things like multi-threading could become a concern. We went through this a bit quick, so let's stop and take a look right here. What we've done in this bit of code is created an anonymous class. While it looks like we've created a new runnable object, we've really created a new subclass of the runnable object with its own special overridden version of the run method, and just put that right in the middle of our code. This is a powerful methodology that allows us to cut down on the amount of code needed. Of course, if we overuse it, our code can quickly become very complicated for us or another programmer to read and understand. Thanks for watching. The Java programming language, a graphical user interface extension library like Swing, and a development environment, a powerful one like NetBeans, can be a really strong combo. Today, we're going to take a look at creating GUIs using a GUI editor like the one found in NetBeans. To follow along, I highly recommend you utilize the NetBeans IDE for this video. So to get started, let's create a Java application like we would any other. Give it a name and we're good to go. But we're going to start off by simply deleting the default Java file that NetBeans provides to us. And instead we're going to ask NetBeans to create a new file. We're going to ask it to create for us a JFrame. We'll give this JFrame a name, keep it in the same package, and when we have NetBeans create this file, even though it's a .java file, the window that pops up looks really different for us. In fact, our file is still just Java code. If we click up here back to source, we can see the Java code that comprises our file. There's actually a whole lot of code in this file if we expand it out, and it's all been generated for us by the NetBeans GUI editor. Changes we make to this Java file will affect our design file and vice versa. From this design file, we have access to a drag and drop editor, and we can also edit the properties of individual elements without having to jump into our Java code. Eventually, in pretty much any application we'd ever create, we're going to have to drop into our Java code to provide back-end programming functionality to the pieces we put into our editor. For now though, let's just take a quick look at how the editor works. I'd like to set up the framework for a password protection dialog. This isn't going to be too complicated, so we'll make our JFrame a little smaller than it is right now. And let's take a look at some of the Swing controls available to us. There's a whole lot of them. And in fact, courtesy of NetBeans, we can use some other GUI extension systems as well. Let's just stick with Swing and stay pretty basic. Label is about as basic as you can get, and our password dialog is going to need some text. That should do. And there we go. I guess we can make our JFrame a little bigger. Now, a password dialog is also going to need some user interaction. We're going to need to get a password from the user, but also their username. To get the username, we have to decide between a couple of options. Text area might seem like a good one. It lets the user put text in a box. Unlike the label, which only we, the developers, can edit, the user can click on our box and type some text into it. Unfortunately, this box is pretty big, and if we click on it and try and make it smaller, we're going to get scroll bars to allow the user to bounce around its size. We could modify the default sizes of this box and when the scroll bars appear by changing any number of its properties, which we can access from this editor. But a much simpler solution would be to simply use a text field. which doesn't have all of the multi-line functionality of our box. Oops. And I guess we should put a label next to our text field, and you'll notice that the graphical editor helps me line things up. If I properly double click within fields like the label, I can edit their text right here. One of the cool things about modern GUIs is that there's some really specialized controls. One of these is the password field. In many ways, it's going to act just like our text field here, except that it's going to replace whatever text the user puts in there visually with dots, so that someone looking over their shoulder can't learn their password. Oops. If you fail to double click within an editable element, it brings you back to the source, which is what I just did there. We're going to want to edit these two components that our user can place text in so that they don't appear to our user initially as having these default values. We can try and double click like I just did there, or we can just go edit the properties of our controls. Here, the text value of our text field can be modified to be nothing at all to start out with. And we can do the same thing with our password. You'll notice that the text value of our password actually has text in it, but it just displays as a bunch of dots. But we as programmers can access this value to validate our user's password. There's a whole lot of other options in here. We can do things like changing the font. And the foreground and backward ground colors and giving it borders and all that. The important thing to realize is when we access these elements within our source code, all of this methodology is also available to us through raw Java. That's all I really wanted to show you in this quick video. Just the raw power and how quickly we set up a GUI window for this system using the NetBeans graphical editor. And I guess before we close the video out, we should probably run our program so that you can see that it actually does exist. And that the user can put values into these fields. Of course, we haven't written any back-end code to do anything useful with them yet. But the GUI itself is up and working. There's nothing magical happening here. If we jump into the source of this code and drop down to its main method, we'll see the code where the GUI is actually created and displayed to the user right here. See you next time. One of the best things about working in Java is how powerful its GUI extension libraries are, and just how quickly we can get a program up and running that not only has functional code, but also a slick, professional-looking user interface to back it up and help anyone interact with our program. That's what we're going to be doing today, connecting this interface for basic username and password validation with some back-end code that we're going to write that will actually check two text fields to see if they're the ones we're looking for. To start us off, we have this basic GUI with a text field where someone can put a username and a password field where someone can put a password name that will just show up as stars. The source code for this GUI is so far completely auto-generated. we haven't touched it at all yet. It's just reflecting the design decisions we've made here. Before we can start writing backend code to do our username password validation, our user is going to need a way to tell us that they've put in a username and password and they'd like it to be validated. This seems like a good job for the all-powerful button. So let's add a button to our GUI, and we'll change its text to be submit. User will click it to submit their information. And now, when this button is clicked, we'd like to perform some programming logic. We want to check the username and password fields. And for this video, because we're just learning and doing things simple and easily, we'll just check them against some hard-coded text. The question is, how do we get from GUI to functional Java code? Generally, we're going to do this through the event-driven programming model, where the interactions that our user has with the GUI determine what Java code is executed, what back-end logic occurs. Another way to think of this is that we can set up pieces of our Java code, or methods, to listen for specific GUI-related events to occur, and then execute when they do. You'll notice that our GUI components, or controls, like our button, have a field here under their properties called events. These are all the things that could occur in relation to our control here. In theory, we could bind each one of these events to a method in our Java source code. And when this particular event occurred, whether because of user interaction or other code we wrote, our related Java method would be called. To let users click on our button and perform some coded action, we're going to be assigning an event handler to our action performed event. If we click on this field, we get an option already. Our GUI designer is suggesting we add a handler, JButton1ActionPerformed. That's kind of an awful name for a method that's going to be sitting in our code. JButton1 is pretty nondescript. JButton1 has been chosen though because it is the variable name assigned to our JButton when it's created in the actual Java code. If we scroll down, we'll see this actual declaration down here. And I'm sure we can change these settings, but NetBeans is letting me know that we probably shouldn't modify this directly because the designer is going to be modifying it too. So we'll just change the name of our button from the undescriptive JButton1 to submit button. When we make that change, we'll see that NetBeans has updated our source code, and now there's a submit button object bouncing around. This is a variable that starts with a capital letter, so we'll make one more change there. And now the suggested action performed by NetBeans is submit button action performed. When we head down to our source code, we'll see that an event has been created and linked with our JButton. In this massive block of generated code that NetBeans has created to mimic our GUI that we've been creating through their tools, if we search for our submit button action performed method, we'll actually see it added to the generated code here. It's been added as the final call of this action listener placed on our submit button. Our action listener, of course, has one job and one job only, and that's to see if our button has been clicked. If it's been clicked, it's going to call our submit button action performed method. So here we can put some good old functional Java code. We need to do two things. We need to check the value of the password field, and we need to check the value of the username field. Passed into our submit button action performed method is only this action event. And while there's a lot of interesting and useful methodology attached to this event, the context of the action that caused our method to be called, it's not going to give us what we really need here. What we really need here is our password field and our text field, which fortunately are private members of our current class. Let's start with the username. That's jtextfield1, which we should probably rename when we get the chance, but we'll just roll with it for now because we only have one text field. If we remember, in the editor, under properties, this text field had a text property, which we've gotten rid of the text in because we don't want our username text field to start with any text. It's blank so that users know to put their own information in there. But it stands to reason if that's the property exposed to us in the designer, there should be a related property exposed by the object itself. And there is, getText. When we call getText, of course, we return the text currently stored in our text field. And we'll make our super secret username the very creative word username. This is, of course, a conditional statement, and we're going to want to make another conditional statement in addition. We want to ask our program if the text field and our password field which is going to expose a similar method, getPassword in this case, both equal the hard-coded string. And our secret password will be Java. Put an if in front of our conditional statement, some parentheses, and we're good to go. So now we need to give our users some indication whether or not they've succeeded in providing the proper username and password. Actually, before we go any further, getPassword actually returns a character array, not a string. So this comparison isn't going to work very well. To keep things simple, let's just assign this password value to a string. And then we're good to utilize it as a string. Okay, what to do if the user has successfully input a good username and a good password? Well, I think it would be cool if we showed a pop-up dialog here. JOption pane provides us with the method show message dialog, which is a pretty cool way to impart really important, really immediate information to the user. It'll show a pop-up box, and it's pretty lightweight and easy to use. You may have to fix imports on this one. The only heavyweight information our message dialog needs to create itself is a GUI component to attach itself to be its parent. We could acquire the button through our action event, but that doesn't make a lot of sense because the dialog is not tied just to the button. It's really tied to the entirety of what this GUI is about, which is validating a username and password. So it'd be nice if we could tie this dialog box to the JFrame itself, the GUI's top level element. And in fact, we can. If we zoom up a bit to check exactly where we're writing code, we'll see that we're in a class, myGUI, that extends the JFrame class. This entire class is associated with the JFrame we're working with. So, to pass this JFrame as a variable to our showMessages dialog method, we simply use the this keyword. And now we just type in a message to show the user on password and username validation. So let's run our program and see what we've built. Here's the dialog, which there we go, which we've seen before and which we expect. Here's our valid username. I've typed in our valid password, Java. And when we hit submit, we get the pop-up dialog box, which we can move freely of our JFrame. Just to test things out, let's put in some gobbledygook, and we get nothing, no matter how many times we click. And a good username and no password also gets us nothing. Pretty cool. Of course, we've only just scratched the surface of what is possible with Java GUIs, and of course Java itself. The thing to take away from this is, well, two things really. One, creating Java GUIs for our programs is easy and in many cases painless. Sometimes the event handling model that GUIs to some degree force us to implement can even make creating our Java programs that are heavily reliant on user interaction easier than it otherwise would be. The other important thing that I cannot stress enough is that even though the GUI designer is awesome, it's possible for us to create this exact same project by simply sitting down and writing the Java code here. I'm not saying we shouldn't use the GUI designer because there's a lot of code and a lot of well-written code that's been generated for us by the GUI designer, and that can save us a whole lot of time. But there's absolutely no magic happening here at all. This is all Java code making use of the Swing extension library. When we would like to store information that has a structure that is meaningful to our program, but we would also like this information to be to some degree human readable and sometimes even human editable, we very often turn to the language XML. Java provides us powerful tools for manipulating, reading, and writing XML raw text and files. However, as is the case with many powerful tools, there's a bit of a knowledge overhead for us to learn how to use them. So, in this video, we're going to accomplish a very simple task to get ourselves started on the road to learning how Java interacts with XML. We're simply going to read in the XML information from this file. This file lives in the current directory of our Java project. So when we run this Java program, it will be able to access cars.xml without any additional pathing required. Before we get started, notice there's a whole lot of inputs necessary for this program. These transform inputs are not necessary for anything we're going to write. I've written us a function that will print our XML document to the console window if we successfully load it. If you're following along in the code with this video, I'd recommend importing these transform imports from the start. And then, as we use additional functionality, go ahead and use NetBeans right-click Fix Imports to see exactly what libraries the tools we're utilizing are coming from. So let's get started. Our end goal here really is to have an object of the document class that contains the information in our cars.xml file. Once we have this document object, all we need to do to see that information in our console window is to call this print.xml document function on the document. Unfortunately, creating this document is not as simple as simply saying dom equals new document. Rather, we need to create it in a structured and procedural manner that will properly preserve the parsable nature of our XML file. To do this, we're going to make use of two additional classes. One of these classes will be the document builder class, which, believe it or not, will take care of the responsibility of actually building our document for us. The document builder class exists as a separate entity from the document object, so that we as programmers can logically separate the methodology we can perform on the document itself and the additional range of methodology needed to create that document in the first place. Similar to the document class, we don't just instantiate document builders willy-nilly. Instead, there's a third class we're going to utilize to get our document builder. This is the document builder factory class. And this class contains a static method, new instance. This method call right here will instantiate a document builder factory for us to work from. Once we have our document builder factory, we can now acquire for ourselves a new document builder. To do this, we're going to call the factory's new document builder method, starting to make some sense here. Finally, we need to instruct our document builder to build us a document object, and that this object should mirror the structure of our cars.xml file. We've already declared our document object, so we simply need to instantiate it with a value now. That value we'll acquire from the builders.parse method. One of this method's parameters is a string, which references a file name. If we had a referenced file object in our Java program, we could also use that. So, I guess it's time to see if our code works. We've acquired a document builder factory using document builder factory's static method that creates a brand new instance. With that document builder factory, we've created a new document builder who will be able to intelligently parse our XML file. In parsing our XML file, the document builder understands the nature of the information contained within and is able to store it in our XML document or document object model element. When we run this program now, we get as output the raw text view of that original XML document. Because there's so many steps to loading an XML file like this, I wanted to put it in its own video, so that later down the road, when we as programmers learn about manipulating and reading valuable information from XML, we're not bogged down with all the syntax we've learned here. See you next time. The document class provides an easy way for us to store formatted information in an object. In the program in front of us, we've read in information from a cars.xml file into our Java document object. Here's what that file looks like. The root node of this file is the cars node. And contained within this node are two owners, Billy and Jane, each of which have a number of cars within them. The information stored within these car elements is mirrored by the information that can be stored by this Java class we have. Our goal in this video is going to be to take the car information from cars.xml for only a specific owner, in this case, Jane, and store this information in our custom car class so that we can utilize the car class's toString override to print all of Jane's cars to our console in a nicely formatted manner. With the code we have already set up, our document object mirrors the information stored in cars.xml in the same format. So we simply need to figure out how to ask this document the question, what cars does Jane own? In order to figure out how to write our code, we're going to need to know a little bit of XML terminology. We're going to be dealing with the terms element and node throughout this video. In XML, an element is an entity that has a start and end tag, and that element also contains all of the information within it. This highlighted piece of our XML document is the element owner with attribute name equals Jane. When our document object returns us information, though, it will often return the information in terms of nodes. Nodes are the building blocks of XML documents, and we can almost think of it as an inheritance relationship, where all elements are nodes, but not all nodes are elements. Nodes can be much simpler and smaller than an entire XML element. So, in the pursuit of finding all the cars owned by Jane, let's see what functionality our XML document provides for us right off the bat. If we take a look at code completion to quickly scan through our list of methods we can call from our document, we're going to see this method getDocumentElement, which returns an element for us. This is probably a good way to start. This method returns the top level element in our XML. In this case, we're going to get the cars element, which contains all of the information that we're going to need. It also contains some information we don't need, like Billy's cars, but we'll parse that out after we've accessed it. Once we've imported the right libraries, we can directly reference the concept of an XML element within our code using the element class. And we can create a new element object and assign its value to the root element of our XML document. Of course, we need to go deeper. The root level of our XML document is not directly useful to us. We need the information contained within it. We only really want the information from this owner node, but because of the way XML parsing works, it probably makes sense for us to first acquire both of these owner nodes and then find the one that we're really interested in. To acquire both of these nodes, we can call a method on the XML element we've just created, the root element of our XML document. XML elements can contain within them other elements. In this case, our root element contains a number of owner elements. The method getElementsByTagName allows us to collect a number of these inner elements. The tag name of an XML element is just what you would expect, the name we gave to this section of our XML. In this case, if we ask for all the elements with tag name owner contained within our document's root element, we're going to further narrow down the amount of XML we're working with, getting closer to the small section we desire. Now, we're no longer dealing with our root node at all. We only have its contents. What's returned by this method is not a single element, though. There's two distinct elements in this section, even at the highest level. Two owners, Billy and Jane. So, getElementsByTagName doesn't return a single element. Instead, it returns a node list object, which, believe it or not, is a collection of XML nodes. Now, it's time for us to really narrow down our search. Our node list contains multiple owners, but we only want an owner if the attribute name associated with that owner happens to be Jane. In order to find this particular element, if it exists, we're simply going to loop through our node list, checking the attributes of each element it contains. Owners list is not a traditional array. It's a node list, its own kind of object, so we can't use normal array syntax on it. Fortunately, it exposes methods to us that mimic normal array syntax. For example, the getLength method will tell us how many objects are in this owners list. Similarly, when we attempt to create a new element and assign that value to the currently looped through portion of owners list, we're not going to be able to use the normal syntax we would for an array. Once again, though, owners list provides us a method to do the same thing. The item method provides or asks for an index as input. Owners list, though, is a node list. While elements are nodes, not all nodes are elements. So we need to make a decision here. We could check the nature of the objects that are returned by this function and assure ourselves that they are in fact XML elements. But to keep things moving, we're just going to assume that our XML was properly formatted. And we're simply going to let Java know that the node returned by this method is in fact an element. It has a start tag and a closing tag and can contain other elements and nodes within it. Once we've successfully got an element from our list of owners, it's now time to check and see if this is the owner that we're looking for. So we're going to need a conditional statement. XML elements expose to us the getAttribute method. And the attribute that we're interested in is the name attribute. So This bit of code right here will ask the current owner, what is the value of your name attribute? If that value is equal to Jane, then we know we have accessed the right XML element. Within Jane's XML element, we now only have a number of char elements. So it's once again time to create a node list and populate it with these chars. Rather than using the top level document though, we now need to call this method on Jane, our current owner. If we were to use the top level document, we would get all chars in the document, even, what was his name? Billy's. This main method is getting a little intense. This is about as far as I'm willing to go in one method. We're already a couple of levels deep in our code. And it's not exactly simple code we've been writing. I think it's time for us to parse out the next bit into its own method. Let's simply declare that we're going to have a method print chars. And this chars will take a node list of char elements to print. Now, leaving our main method, we'll declare our new chars list. Because we're in the static, or because we're in the entry class of our program, and this method is being called by the static main method, it should probably be a static class. And all it's going to do is print to our console, so void is an appropriate return type. We already know it's going to take a node list, chars, as input. Once we've entered this function, we know we have a list of char XML elements at our disposal. But in order to print each one out, we're going to have to loop through them. We've already looped through a list, a XML node list in our program already. So we're going to be using some very, very similar syntax. Here's our loop from earlier. Let's take a look at what needs to change for this new code. Well, we're no longer looping through owner's list. We have a new node list to loop through, the chars node list. We know that chars are still elements, so our casting shortcut here is still appropriate. But we probably want to rename the variable we're using for each char we loop through from owner to something like char. Each time we loop through a char, we're going to be creating a new char object and storing the information in that char's XML in this actual Java object. So, in addition to accessing the char XML, let's also declare a char object and just instantiate it to be a new char. Let's actually name our XML element representation of the char node, so that we don't get it confused with our char object. Now, we're going to build up the values stored within the char object by reading them from our char node. If we jump back to the XML quickly and take a look at the information stored in the char node, we'll see that it stores make, model, year, and color as XML nodes within the char element. The vehicle identification number is actually an attribute. Let's start with the easy pieces. Make, model, and color are all strings stored in the char class, and they all happen to be nodes within the char element. We already know how to access nodes within an element. We're simply going to use char node and then get elements by tag name again. If we get all the elements with the tag name of color, we should return a list that contains only a single element, the element we're interested in that tells us the color of our car. Unfortunately, we do have a list here, so we can't manipulate that element directly until we pull it from the list. Once again, though, we know how to do this. If we're confident that our XML is properly formatted, we know we've achieved a list with exactly one item in it. So if we get the item at the 0th index of that list, that will be the XML element that we're looking for. Color stored in this XML element, though, isn't an attribute. It's inner text. So we're going to need to take a look at what methods XML element exposes to us and see if there's an appropriate one to acquire that inner text. And there is. Get text content will give us all of the inner text that's not actually part of XML element tags. In this case, it's going to give us the color of our cars. We're going to do pretty much the exact same thing for make and model. The only thing we're going to have to change is the keyword we provide when looking for the elements. Now, it's not enough just to acquire this information, we need to store it. Fortunately, all of the attributes of our car object are public, so we can freely assign them values after we've created our car. If these were private fields without setters, we'd probably have to do this information before constructing our car object and then pass them through to a constructor that it would hopefully have. Now, we can continue using the same general strategy for our car's year. But we should note that as far as our car Java object is concerned, year is an integer. But as far as our XML element is concerned, year, just like anything else, is a text content string. Fortunately, converting a string to an integer, as long as it's well formed, which is an assumption that we'll make here, isn't too difficult. We're simply going to use the integer class and call its parseInt method, which will do its best to convert a string value to an integer. Oh, right. And we'll assign that to our car object's year field. That leaves only one more field for us. Car object has a vehicle identification number field. This field is not actually an integer. Vehicle identification numbers can contain letters, so this value is stored as a string. It's going to be a little different for us to get, though, because rather than being an inner element, it's actually an attribute of the car element itself. Once again, though, we know how to acquire an attribute from our car node. We're simply going to get the attribute with name fin and assign that to our car object. With all of this done, our car object should be fully built with reasonable values in all of its members. Now, it's time to use the car object for the reason it exists, this overridden toString function. For each car we loop through, let's now call car object's toString function and print that result out to our console. Oops, looks like I've forgotten to give our method a name. I think we decided to call it print cars. And also, we're looking for year here, not model. Once we've made those changes, we should be good to compile our program. And now, hopefully when we run it, it's going to print out all of Jane's cars, making use of our Java car object's overridden toString method to nicely format the output. When we run this program, we get 2 cars printed as output. And if we go to our XML and take a look at the cars assigned to Jane, we'll see that this information does indeed match the information stored in these cars. The XML and Java combination is really powerful. XML is human readable. We can understand it and even make modifications to it as people. But it also contains really valuable information in terms of how it is structured that programming languages like Java can understand as well. The program we've written here, while it does have its quirks and knowledge we must have to write it, is much, much easier to write and far, far easier for a programmer to understand and maintain than a similar program reading from a raw text file would probably be. See you next time. Being able to read XML information is all well and good, but for the language to be truly useful to us, our Java programs probably need to be able to write out XML information as well. The program in front of us is a bare bones model of a program that both reads from and writes to the same XML file. Its main method is extremely simple. It takes a file and then it reads XML from that file, storing it in an XML document tree object. Then this program calls writeXML document to write the XML back out to the same file. Currently, the method that reads in the XML has been implemented for us. However, the method to write out the XML is not yet complete. Let's see what needs to happen for us to write XML information to a document. Because of the way an XML document is stored, we need to convert it to a different format before it's really feasible for us to print it out to a file in the same formatting that we got the original XML. To do this, we're going to make use of an XML specific class called the transformer. As with a number of the classes we deal with when dealing with XML in the document model, transformers are best created using a factory. In this case, that factory is called the transformer factory, and like many factories, it exposes the new instance method, allowing us to create one when we need it. To get our new transformer, which will allow us to convert our document object into something streamable that we can send to a file, we're simply going to call our transformers factory's new transformer method. Now, before our transformer can transform our XML document into something else, it's going to need to know what we would like it to convert our XML document's information to. This class is the streamResult class. It's the target for the information stored within our current document. The stream is a raw binary information pump that can be sent to any number of targets. In this case, our target is going to be the destination file provided to this function. Our transformer, though, is not automatically linked with our XML document, and it expects us to reference our XML document in a unique manner. This is as a DOM source object. Notice that our source object here is being paired with a result object. The transformer, when we provide it both of these objects, will know to convert one to the other. Now, to create our document model source object, we simply need to pass in our XML document. Finally, when all that setup is complete, we can execute the functional piece of code. Let's grab our transformer and ask it to transform our source, our document model object, to a streamable result targeted at our destination file. When we run this program, we'll get some XML in our file, but you'll have to trust me when I say this, this is the same XML we had before, which is to be expected, seeing as we read in the XML and then printed it right back out. To really test if our program is working, we're going to need to make some changes to our document object within the Java code, and then see if we can print those changes out to this file. Let's change the names of the car's owners. Let's transfer the deals to all of these cars to an owner called Mike. The power of the XML input-output system is that in between loading and writing our XML document, we can freely modify this document object stored in memory, and the changes we make to the object in Java memory will then be written out to our permanent XML file. So let's begin making some changes. We're going to use getElementsByTagName to get all of the owner elements in our XML document. This will return a node list, and we'll call it owners. To convert the names of all of these owners to Mike, we're going to have to loop through this list. As a refresher, we can get the number of items in the list by calling owners, the node list, getLength function. And to access the item that we're currently iterating through, we'll use the owner's item function and pass in our iterating variable I to get the item at that index. Let's store this value in a variable so that we can use it easily. And once again, we'll just assume that our XML is well formatted and inform Java that we are in fact dealing with a fully fledged XML element at this point. XML elements expose a number of methods that allow us to modify them. One of these elements is the setAttribute element, or method, and that's what we'll be using here. SetAttribute takes two strings as input. First, it wants to know what attribute we'd like to modify. We're going to be modifying the name attribute. It's the only attribute available to us here. And we're going to assign its value to Mike. When we run our program now and check our XML file, we'll see that Mike is now the owner of all these cars. It might make sense now to combine these two XML elements so that Mike is only a single owner, not split into two. That's a little bit out of the scope for this tutorial video, but it's an interesting question and one I encourage you to reflect on and maybe take a shot at right now. See you next time.